Hey everyone, and welcome to Machine Learning and AI, Support Vector Machines in Python. Support vector machines are one of the most powerful machine learning models around, and this topic has been one that students have requested ever since I started making courses. These days, everyone seems to be talking about deep learning, but in fact there was a time when support vector machines were seen as superior to neural networks. One of the things you'll learn about in this course is that a support vector machine actually is a neural network and actually looks very similar intuitively. The toughest obstacle to overcome when you're learning about support vector machines is that they are so theoretical. This theory very easily scares a lot of people away, and it might feel like learning about support vector machines is beyond your ability. In this course, we take a very methodical, step-by-step approach to build up all the theory you need to understand for how the SVM really works. We are going to use logistic regression as our starting point, which is one of the very first things you learn about as a student of machine learning. So if you want to understand this course, that's all you really need. Just have a good intuition about logistic regression, and by extension, have a good understanding of the geometry of lines, planes, and hyperplanes. If you recognize this picture, and you are motivated to succeed, then you can learn about SVMs. For those of you who are thinking, oh, theory is not for me, I don't want to learn about SVMs, well, there's still a lot of material in this course for you too. A lot of people ask me, lazy programmer, I don't really want to know the ins and outs of the model, I just want to use the model. And in this course, there will be not just one, but two full sections devoted to just the practical aspects of how to make effective use of the SVM. We'll do end-to-end examples of real, practical machine learning applications such as image recognition, spam detection, medical diagnosis, and regression analysis. Thanks for listening, and I'll see you in the next lecture. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I want to talk about the objectives for this course. This course, although it seems like just a regular part of my supervised machine learning series, is very unique. To explain why, let me explain the flow of a typical machine learning or deep learning course that I teach. Usually we have a series of related topics. Say we're studying neural networks. The topics might be making predictions using a neural network, training a neural network, adding regularization to a neural network, and so forth. For each topic, we will always proceed from theory to code. What that means is, first we'll have a discussion about what the topic is, why it's important, how it works, and we'll derive everything step by step. Then, once you have a full theoretical understanding of how that thing works, we implement that thing in code. That lets you practice what you learned and really reinforces your understanding. You can also check the results and observe for yourself that what we've been studying really works in the real world on real data. So we always follow the same pattern. First we do a little theory, then we implement that theory in code. Then we do a little more theory, then we implement that new theory in code. What is unique about this course is that this is not how this course will work. With SVM, things are very imbalanced. There is a huge amount of theory to discuss, but not really that much code. Well, the coding component can be quite a challenge, but that depends on how far you want to go. What is unique about this course is that there will be multiple major sections of the course that will contain nothing but theory. This is not because these sections simply lack practical coding exercises. It's simply that there do not exist any coding exercises that can be done. This course will contain as many coding exercises as possible, but it's important for you to understand that when studying the SVM, coding is not your central concern. Remember, the SVM is heavily imbalanced with a lot more theory than code. This is just inherent in the nature of the SVM. So if you're taking this course, then you're taking it with the understanding that to learn about SVM means to learn the theory. Also keep in mind that this course is just about one model, the SVM. That means we'll be looking at just one implementation or close to one implementation. Because of all the theory you have to learn in order to understand that one implementation, it won't be trivial. So even though there is just one implementation, it will take you a very long time to get there. Now, if you are a student who is only concerned about how to use the SVM, then this course is still for you. We are going to have sections in this course devoted solely to making use of the SVM effectively, which do not contain any theory at all. So if that's what you're looking for, then that is still contained in this course. In particular, we are going to start off with the Beginner's Corner, which just focuses on how to use the SVM. We're going to apply the SVM to common tasks such as image recognition, medical diagnosis, spam detection, and regression analysis. We'll also discuss how to effectively choose the SVM hyperparameters. So if you've read the scikit-learn documentation and you have zero idea of what any of those options means, then you can take this course to get some insight on how to choose those hyperparameters in a sensible way. In addition, there will be a second Beginner's Corner section where we discuss some topics beyond the fundamental SVM theory. This is more intermediate than beginner, but relative to the rest of this course, this is still beginner focused. In particular, it's about taking the results of SVM theory and applying it. One of the things you'll learn is that SVMs might not scale well to large datasets, and so one method of circumventing this problem is to create approximations to the SVM. The approximations to SVM turn out to be neural networks, and so in this section, we'll explore various neural network architectures that try to mimic what the SVM does, but in a scalable way. If you are an expert, this will be useful for you too, because it offers a more intuitive alternative picture for how SVMs work. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I'm going to give you an outline for this course. As mentioned, this course will focus mostly on theory, but will contain some coding components as well. The first section is the Beginner's Corner, which is almost exclusively coding. This is all about just how to use the SVM and how to choose SVM hyperparameters. If you've already taken my free course on the NumPy stack and machine learning basics, then this should be a good next step. We'll cover some practical applications of the SVM, such as image recognition, spam detection, medical diagnosis, and regression analysis. In the section after that, we'll start developing the necessary theory for the SVM by reviewing logistic regression. Both SVM and logistic regression are linear classifiers, but the theory behind logistic regression is much simpler. We'll study logistic regression with the SVM in mind, only focusing on the parts which will become useful when we move on to the SVM. One of the most important concepts we'll review is the equation for a hyperplane and the geometry related to that. Once we've reviewed logistic regression and linear classification, we'll develop the theory behind the SVM. We'll start by looking at the linear SVM. This means it's essentially the same equation as logistic regression, just a hyperplane, but the way that this hyperplane is found is totally different. This is what makes the SVM special. You'll learn about the concept of margins and the fact that the SVM is particularly known for being a maximum margin classifier. One important thing you'll learn in this section is that typical machine learning methods, such as gradient descent, are not the tool of choice for the SVM. Instead, we borrow concepts from the field of convex optimization, and in particular, quadratic programming. It's fine if you have no idea what that is, because we are going to explain that from scratch. If you've had some exposure to linear programming in the past, then that's even better. From our perspective, they're essentially the same thing. After we've developed the theory behind the linear SVM, we'll begin talking about how to convert that theory into a nonlinear SVM. To do this, we need another concept from convex optimization called duality. Luckily, these concepts go hand in hand with linear programming and quadratic programming, so if you've had some exposure to that in the past, then you should be comfortable with this. Even if you haven't, we will still derive everything from scratch, so there is no opportunity for you to miss any steps. If you've ever learned about Lagrange multipliers, specifically from an undergraduate calculus course, then you're in luck. Duality really is just an extension of that. After we've learned about what duality is, that will bring us to what is called the dual problem of SVMs. This probably sounds like a foreign language to you right now, but fear not, you will learn what all these terms mean just by taking this course. The dual problem of SVMs is what opens up a whole new world of opportunity for us. We can now make use of something called the kernel trick. Specifically, kernels are efficient ways of implicitly calculating feature transformations. So if you're used to doing feature expansions with features like square terms and interaction terms, you'll see how the kernel trick can take care of all that automatically, without any extra work or computation. Interestingly, all of the topics we've just outlined are entirely based on theory. As I mentioned earlier, this course is packed with theory. That's just the nature of the SVM. But luckily, learning about the kernel trick was the last step. After that, we'll discuss various implementations, including the most popular one, the SMO algorithm. SMO is interesting because it's not the only algorithm that can be used to train an SVM, but it's the most efficient one that we know of. It's what the popular library libsvm uses. It's also highly non-trivial. If you look at the scikit-learn implementation, you'll notice it doesn't actually implement any SVM code. It just calls libsvm. SMO was invented by a computer scientist named John C. Platt, who is currently a principal scientist at Google. The next thing we'll do in this course is talk about neural networks. Neural networks and SVMs almost go hand in hand, historically speaking. For a time, SVMs were a little better than neural networks in terms of performance, but of course, we know that these days, deep learning is winning the machine learning race. It is interesting that SVMs can actually be thought of as neural networks. In this course, we'll look at several neural network approximations to SVMs. In particular, we'll discuss the RBF network, as well as try to create a mashup between an SVM and a standard feed-forward neural network. One thing you'll learn throughout this course is that SVMs do not scale well to large datasets, and hence, sometimes approximations are necessary in order to apply an SVM-like approach to bigger problems. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I'm going to discuss where to get the code for this course. As usual, the code for this course can be downloaded from my GitHub page, github.com/lazyprogrammer/machine-learning-examples. In order to get the code, please don't try to copy and paste it from the web page itself. Use Git instead. I've seen students do this in the past and it frequently causes errors. So just use the command git clone and then my GitHub URL. Also, I would recommend not forking the repo, as this makes it harder to get updates, and I'm updating the repo pretty much constantly, so you don't want to be stuck with an old version. In addition, some students have been confused by forked repos in the past, thinking they had found the correct repo for the course when in fact they had not. So for the sake of future students, please do not create your own fork. And if you're a student searching for the code right now, please double check that you have the correct GitHub URL and not someone else's out-of-date fork. For the data in this course, we'll be mostly using the MNIST dataset. We've used this dataset many times in many other courses, so you probably have it already. If you don't have it, and this is the first course of mine you are taking, here's where you can get it. Go to kaggle.com/c/digit-recognizer. Note that you don't actually have to type this URL out manually. It is easier to simply Google it by searching for Kaggle MNIST, or just copy and paste the link, which has been provided in the code files in the course repo. The relevant file for this course is train.csv. You'll want to place it in the folder called Large Files, which sits adjacent to the class folder. If you haven't yet created the folder Large Files, you should do so once you've cloned the course repository. At this point, you might also want to grab the spam detection dataset, whose URL you can find in the file svmspam.py. As with MNIST, you'll want to place the CSV that you download in the folder Large Files, adjacent to the class folder. As most of you know, one of my #1 rules for learning is to write your own code. Machine learning is all about programming. This is not a philosophy course. Everything you learn in this course involves hands-on work. So whether you are deriving equations or writing code to implement those equations, you're going to be very hands-on. You should never find yourself asking, how would such and such work theoretically? If you ever have a question like that, it is always better to answer it just by writing some code and doing an experiment. Machine learning is about experimentation, not philosophy. Remember that the pattern we are always going to follow is to go from theory to code. First, we discuss what we are doing, that's the theory. Then we implement that thing in code, that's the code. So you should never be confused about what we are doing in the code, because we are always just doing the thing that we just talked about. Sometimes I come across students who try to start the course by watching a lecture in the middle of the course. Usually they end up lost. I don't want you to get lost. So most of the time, if you want to make sense of what you're watching, you have to watch the lectures in order. The lectures build on each other and they tell a story. If you don't watch them in order, it's kind of like trying to read a book by picking random pages in the book. Of course, if you're looking for something specific, that might be a good strategy, but for most of you, that's not going to be the case. And remember that whatever we're doing in the code is not coming from nowhere. We're just doing what we said we were going to do in the previous lecture. Ideally, you're always trying to code by yourself, so if you want some tips for how to get started with that, I would recommend watching How to Code by Yourself in the appendix. Finally, I want to remind you that whatever coding environment you use, it is 100% your choice. A lot of people tell me they like Jupyter Notebook. Well, if you like Notebook, then you should be using Notebook. Remember that Python code is Python code, no matter where it is. There's no difference between Python code in Jupyter Notebook and Python code in the console. The same Python code would work the same in both environments. Remember that in these videos, all you're seeing is just code on the screen. There's no difference between me using a text editor or even putting the code in slides. You can't touch it or interact with it anyway. So it doesn't matter what I use, because that's not suggestive of what you should use. If you find the terminal very scary or intimidating, then maybe you don't want to use it. That's okay. Of course, the terminal is actually very useful, so I would recommend working your way up to being comfortable with it. But for this course, when you're writing Python code, you can choose your own environment. The same code works everywhere. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I'm going to introduce you to the first section of this course, the Beginner's Corner. The Beginner's Corner is a section of the course devoted to beginners, as you can probably tell by its name. In this class, it's all about how to use the SVM on data, assuming that you have the SVM code already at hand, for example, using scikit-learn. The reason I like to have these sections is so that you don't forget what the ultimate goal of an SVM is, to actually use it on data to do classification or regression. It's also good for beginner students who don't yet have the skills or background knowledge to understand the rest of the course. These students may not know why the theory is important, or it might simply be too difficult for them and they may get frustrated trying to learn it, or perhaps they simply don't care. Now obviously, if you are not a beginner and you already know how to use the SVM in scikit-learn, and you want to jump straight to the theory, then you should skip this section. There's no need for you to do the beginner's corner if you are not a beginner. So this section of the course is all about the practical aspects of SVM. How do you use it on data? Once we get through this, the rest of this course is going to be mostly theoretical, since that's what the SVM is all about. So what are the examples we're going to look at in this section? First, we're going to look at how to use the SVM for an image classification problem. Specifically, we're going to work on the MNIST dataset, which is a dataset of handwritten digits. This is a very practical problem since it's exactly how we would perform a task like handwriting recognition, or in other words, converting images of handwriting into characters stored on your computer. As you may recall, the MNIST dataset is a standard benchmark in machine learning. So if you know the history of deep learning, then you know that MNIST plays an important role. SVM is known for performing well on the MNIST dataset. The next example we're going to look at is medical diagnosis. Specifically, we're going to be looking at the breast cancer dataset. I think any reasonable person knows why medical diagnosis is a practical real-world application of machine learning. In recent years, we've created AIs that can diagnose some diseases on par with and even better than human experts. Imagine going to the doctor and having someone diagnose you with superhuman capabilities. We're going to use measurements such as radius, texture, perimeter, concavity, and fractal dimension to determine whether or not we should diagnose the patient with cancer. The next example we're going to look at is regression. So the theory behind support vector machines is applicable to both classification and regression, which makes SVMs pretty flexible. The dataset we're going to look at is the concrete compressive strength dataset. So basically, we want to predict the compressive strength of concrete. We're going to use attributes such as the amount of cement, water, and superplasticizer it has, and its age. Now, if you don't know what any of these things mean, well, that's the beauty of machine learning. Machine learning models don't care what superplasticizer is. All the SVM sees is a bunch of numbers. It doesn't care where those numbers came from. If you're not familiar with concepts such as all data is the same and machine learning is nothing but a geometry problem, please let me know on the Q&A and I will sort that out for you. Now, as you can imagine, if you are a civil engineer or your work is in the construction industry, then being able to predict the strength of concrete is probably very important for you. So this is yet another very practical, real-world problem that can be solved with machine learning. So we're going to do a handful of practical, relevant applications of the SVM. While we do these examples, we'll learn about some of the nuances behind the SVM. For example, how long does the SVM take to train and make predictions? Even though computers are getting faster and faster, there might be scenarios where an algorithm doesn't scale to large datasets. We'll also learn about some of the options that we have when we're using the SVM. These are called hyperparameters. One example of this is that we can choose whether we want a linear model or a nonlinear model. As you may recall, you can think of this as the types of features we're extracting from the data. You might automatically assume that nonlinear is better, but as you'll see, this may not necessarily be the case. Later in the course, you'll see that the capability of SVMs to be nonlinear models is one of the central concepts of SVM theory, and it's what makes SVM so powerful. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to look at the classic machine learning problem of classifying handwritten digits. To start, what you'll need to do, if you haven't already done so from one of my previous classes, is download the data. To do this, you'll want to go to the URL kaggle.com/c/digit-recognizer. Now, of course, you don't have to type this URL manually, since the URL is already provided for you in the code file we're about to look at. At this point, I'm sure most of you already know what MNIST is, but just in case you don't, It's a classic machine learning benchmark dataset. That means when scientists publish a paper introducing their fancy new algorithm, they're going to report that algorithm's performance on this very dataset. By the way, once you've downloaded the data, specifically train.csv, you'll want to put it in a folder called large files, which is adjacent to the class folder. If large files doesn't exist, then you can create it. So what is MNIST? MNIST is a set of images of handwritten digits. Each image is of size 28 by 28, and each image is grayscale. That means for each of the 784 pixels in the image, we're going to have a value between 0 and 255 inclusive. By the way, 28 times 28 is 784, in case you're wondering where we got that number. But remember, a single sample input into a machine learning algorithm is a feature vector, which means we have to turn each image into a one-dimensional array. So we go from a 28 by 28 matrix into a one-dimensional array of length 784. To do this, each image is simply flattened into an array. So the first 28 input features represent the first row of pixels, the second 28 input features represent the second row of pixels, and so on. Another thing we want to do is scale the data. Image pixels are integers between 0 and 255, but this scale doesn't work well for some machine learning algorithms, SVM being one of them. We can say that SVM is scale sensitive. Normally, with SVM, we're going to do something like scale the inputs between a min and a max, or to have mean 0 and variance 1. Since we know the pixel values are bounded, it's easier to scale between 0 and 1. That just means we divide by 255. Next, we are going to look at the code. First, let's look at the main script svm mnist.py. As you can see, it's very short. In fact, what you see here is really nothing new if you've already done my Machine Learning Basics prerequisite section. All we're doing is the same basic steps of every machine learning script. We load in the data, we create the model, we fit the model, and then we evaluate the model. To load in the data, we're calling a function called getKaggleMNIST, which we'll take a look at later. To create the model, we're creating an object of type SVC, which we imported from scikit-learn. To fit the model, we just call the fit function and pass in the training data. To evaluate the model, we call the score function, which returns the accuracy. Note that we're evaluating the accuracy for both the train and test set to help us detect any possible overfitting. Finally, note how I'm timing each step. This is going to be very important, as you'll see very soon. Next, let's take a look at the function getKaggleMNIST. As you can see, it's also quite simple. We use pandas to read the CSV file into a data frame, and then call .values to get a NumPy array representation. Then we shuffle the data. Then we split the data into train and test sets. Everything up to the last 1,000 samples are train, everything else is test. As you can see, we're scaling the data to be between 0 and 1 by dividing by 255, the maximum possible pixel value. Alternatively, you can use scikit-learn's standard scaler to make the data have mean 0 and variance 1. So let's run svm-mnist.py and see what we get. Alright, so one thing you might have noticed is that this takes surprisingly long. Usually with scikit-learn models, training happens pretty instantly. Well, if you're used to training deep neural networks, then probably you're used to things taking even longer than this. But relative to the other models in scikit-learn, this certainly isn't fast. This is something we'll explore more in the advanced sections of the course. By the way, also note how the evaluation steps also take quite a long time. This is a hint to us that making predictions, also sometimes called inference, takes a long time. Again, we'll talk about why this is later in the course. but just keep that in mind for now. This is unusual because for models like deep neural networks, inference is very fast compared to training. Yet for the SVM, it seems that all of these steps take some time. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to apply the SVM to perform spam detection. The dataset we'll be looking at is the SMS spam collection dataset. You can find it on this Kaggle URL. As usual, please do not try to type this into your browser manually because I've seen some students try to do this in the past. You can either Google it or you can copy and paste the URL from the code file in the course repo, which is svmspam.py. But try not to look at the rest of the file since I want you to try to do this whole example on your own as an exercise. So the dataset comes in the form of a CSV with two columns, V1 and V2. I'm not really sure why they named the columns this way, but that's what they did. V1 refers to the labels, which can either be ham or spam. V2 refers to the actual text message content. Also note that you have to be logged into Kaggle in order to download this data. So if you get an error when you're trying to download the CSV, try logging in first. So here is a basic outline of what we're going to do. And by the way, if you're not that familiar with machine learning, this is what we're going to do in pretty much every script in this course, and even 99% of the scripts in other courses. It's always this same basic outline. So number 1, load in the data. I think this goes without saying. Number 2, apply a machine learning algorithm on the data. If we are studying a particular algorithm, then that's the algorithm you'd want to apply. Step 3 is look at the accuracy. Remember, all we want to know is, how good is this classifier? Of course, between step 1 and step 2, you have to now process the data. Luckily, there are some built-in classes in scikit-learn that let you do this directly on text. So there's a class called tf-idf vectorizer that automatically transforms your data into tf-idf format. There's also count vectorizer that just does raw counts. So the feature is just how many times that word appeared in that document. The API for these is very similar to unsupervised machine learning models. So you can call the fit function, and then you have the transform function, or you can do it all at the same time using the fit transform function. Note that they take in sentences, which is a list of strings, where each string is a document in the dataset. In this case, an SMS text message. Next, let's look at the code. The relevant file for this lecture is svmspam.py in the course repo. First, we have all the imports. And by the way, if you don't have word cloud installed, which is the last import, then installing it is very simple. Just do pip install word cloud. Next, I'm going to load in the data. As usual, since we have a CSV, we're going to use the pandas read CSV function. Notice I've put the spam.csv file into a folder called large files, which is adjacent to the class folder. So if you want to put spam.csv somewhere else, you're welcome to, but you have to change this path appropriately. Also notice I'm passing in a special encoding here called ISO 8859-1. Knowing what this is isn't important, but the reason why we need it is because the CSV contains some invalid characters. So if you try to use the default encoding, you're going to get an error that there's a character that's not valid UTF-8. Generally, when you're working with text, you're going to come across invalid characters, especially these days with the existence of emojis and other non-standard symbols. And now for some reason, after you load in this CSV, you're going to see some extra columns that are just empty. So what we're going to do is clean up this data frame a little bit by dropping these columns. Next, we're going to rename the columns we kept, which are currently just V1 and V2, which are not really descriptive names. So we're going to rename them to labels and data. Next, we're going to create a new column called blabels, which assigns a value of 0 to ham and a value of 1 to spam. We're also going to extract this column as a NumPy array. Note that you probably don't need to do this since, last I remember, scikit-learn accepts data frames and series as input arguments, and it allows your labels to be strings. But if you were to write your own model, you'd want the labels to be represented numerically, so in general, it's good practice to do this. Next, we're going to create our X matrix, which is the input features for every sample. For this experiment, I'm going to use the TF-IDF vectorizer from scikit-learn, which creates a feature value called the term frequency inverse document frequency. And it's exactly as it sounds. If you imagine that each row is a document, which are the samples, and each column is a word, which are the features, then X of document and word would be defined as follows. It is equal to the number of times this particular word appears, divided by the number of documents that this word appears in. Now, in reality, there might be some logs and some other transformations in there, but this is the basic idea, so let's keep it simple. Of course, you are welcome to read up on TF-IDF if you are curious. The motivation behind using TF-IDF is that some words like the, a, and to will appear very frequently, and they are not words that are generally helpful in classifying documents. The reason they are not helpful is because they are such common words. Probably all documents contain these words. In other words, because they appear so often, their feature values, if we were to use the raw count, would be very high and would overshadow less frequent words, which are probably more unique and more helpful. Therefore, we try to normalize it by dividing by the document frequency. Now, at the same time, it turns out that raw counts actually work quite well too, so you're encouraged to give those a try at your leisure. Notice how I'm passing in this decode error argument set to ignore. This is because, as I mentioned earlier, if any invalid UTF-8 characters are found, we want to just ignore them. Next, we call train test split to split up the data into train and test. You don't strictly need to do this, but again, it's usually good practice. You could even do cross-validation so you can calculate on average how well the model does on the validation set. That's probably a more accurate measure than just one train test split. So now that we have our data, training the model and evaluating the model is super simple. We just call the object's constructor, we call the fit function, and then we call the score function for both train and test. So in this example, because we have access to the raw data, there's some interesting stuff we can do. I have this visualization function here. What this is going to do is create a word cloud. Basically, that's a picture where more frequent words appear larger and less frequent words appear smaller. So for each of the classes, we'll be able to see what are the most common words in a spam message, what are the most common words in a ham message. So this function takes in a label which can either be ham or spam. We then grab only the rows that contain that label, and we loop through the data column. We keep a running string of each message we encounter and just concatenate them together. This is because that's what the word cloud expects to get as input. Once we create the word cloud, we use matplotlib to show it. Next, let's do a simple analysis to figure out what our model is getting wrong. This shouldn't be too many since we're getting about 98–99% accuracy. So we create a new column called predictions, and we set it to the predictions generated by our trained model. Next, I'm creating a variable called sneaky spam. It's sneaky spam because it's able to bypass our spam filter. So to do this, I need to filter the data frame by selecting any rows where the prediction is 0, but the true label is 1. Note how we use the element-wise AND operation here. So if you didn't know how to do this, now you know. Then we loop through the data field and print each message. Next, we have another variable, which I'm calling not actually spam, since these are messages that our spam classifier detects as spam, but are actually legitimate messages. It's the same process as before, except we switch the 1 with the 0. Let's now run this and look at the results. Alright, so the test accuracy is about 98%, which is pretty good. Now we can look at our word clouds. So for spam messages, some of the words are text, free, call, now, mobile. So that makes sense. And for not spam messages, some of the words are will, love, got, now, need. So those are pretty generic words, but I think overall it makes sense. All right, and now here's some misclassified examples. So these are the things that should be spam. And if you read these, they are definitely spam. Now here are some of the things that should not be spam, but were classified as spam. All right, so it's actually understandable why these would be classified as spam. They contain words like message and reply and morphine. So I think these examples definitely suggest that we could build a better classifier. So perhaps you could do that by choosing better hyperparameters or using a different version of TF-IDF. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to do a medical diagnosis problem using the SVM model. And we're also going to take this opportunity to explore a few more of the options you have when you're using the SVM. So let's take a quick look at the documentation. There are a lot of options here, but if we just look at the first few, the first one we see is just a big letter C. By default, it's set to 1.0. Of course, I don't expect you to know what this means, and it's just a number, but we'll learn about this later in the course. The next argument is kernel. This is the one I want to pay attention to in this lecture. As you can see, we have a set of predefined options such as linear, poly, RBF, and sigmoid. In this course, I assume you've had at least some exposure to machine learning, and so understanding most of these is probably pretty intuitive. First, we know that linear means the function we're going to be using as our model will be a line or a hyperplane. As we know from linear regression, sometimes a line just isn't good enough to fit the actual data. And so we can make our model more expressive by using polynomial terms in addition to linear terms. So that's the difference between linear and poly. By the way, the same thinking applies to both classification and regression. They are just two different geometrical problems. Now, if you've had exposure to neural networks in deep learning, then you already know what a sigmoid is. You also already know that this sigmoid function is what makes neural networks nonlinear, which is what makes them powerful. The only option you maybe haven't seen before is the RBF kernel, which also happens to be the default. The RBF kernel goes hand in hand with SVMs, and we'll learn all about them later in this course. All you need to know now is that, like the polynomial and sigmoid options, the RBF kernel also gives us a nonlinear model. Alright, so let's look at our medical diagnosis code. The relevant file for this lecture is svmmedical.py. As you can see, this is just another very short, basic Python script. It's the same usual steps. Load in the data, create the model, fit the model, and evaluate the model. First, let's consider loading in the data. You'll recall that this is the same dataset we used in the machine learning basics prerequisite. It's nice because we don't have to download anything external, since this dataset comes with scikit-learn. All we have to do is call the function load breast cancer. Now, since we've already looked at the data previously, we're not going to do that again here. Instead, we want to use the principles that all data is the same and machine learning is nothing but a geometry problem. Remember, it doesn't matter what the data represents, because that in no way changes how the algorithm works. Well, one thing that's important to remember is that all the input features are real valued variables, so we're going to want to scale them. Remember that we previously looked at all the names of the data variables, so if you're interested in that, just go back to my free course to review it. Basically, these are all just physical measurements such as radius, perimeter, area, and so forth. And the goal is to create a binary classifier that predicts whether the diagnosis is malignant or benign. So as usual, we're going to do a train test split, and then we're going to create a standard scalar object to standardize the data. The next thing we're going to do is instantiate our model. First, we're going to try the linear kernel, and then we're going to compare it to the RBF kernel, which is the default. Once we have our model, all we need to do is call the fit function on xtrain and ytrain, and then call the score function on the train set and the test set. So let's run this and see what we get. So as you can see, we do pretty good, even with just a linear model. Let's do this again, but with the default RBF kernel. So as you can see, we get results that are on par with the linear model. What this might suggest is that a linear model is good enough. Of course, you could use cross-validation and run a statistical test to answer that more definitively. But let this be a reminder to you. Just because you can use models that are more expressive than linear models does not mean that you always should. Sometimes a linear model can offer better performance, both in terms of running time and in terms of generalization ability. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to do another important supervised machine learning problem called a regression. As you recall, regression tries to fit a curve or a surface to a set of data points. So let's first talk a little bit about the data, and then we'll look at the code. This dataset is called the concrete compressive strength dataset, and the basic idea is you want to predict how strong a sample of concrete is based on some measurements. If we look at the documentation, we can see that all of the input variables are real valued. We have variables named cement, blast furnace slag, fly ash, and so on. One key point is that it tells us what the units of these measurements are, kilograms per meters cubed, so we can infer that these measurements are densities. How much of this substance in terms of mass can we find per unit volume? Another key point is, if you're like me and you're not a civil engineer, then you have zero idea what any of these variables actually are. You probably don't know what fly ash is, or looks like, or even how to buy it if you wanted to have some. Does that matter? Of course not. Machine learning models work on numbers. They only see numbers, and they don't know anything about the meaning of those numbers. We've discussed this before, but it's nice to repeat it once in a while, that machine learning is nothing but a geometry problem. Alright, so now we have a basic understanding of the data. Let's move on to the code. First, we are going to load in the data. Luckily, Pandas already comes with a function named readExcel that can read XLS files into a data frame. Next, since the spreadsheet comes with very long and complicated column names, it's going to be simpler for us to just turn them into numbers. So we're going to reassign the column names to integers starting from 0. Next, we're going to grab our input data x and our targets y. As per the documentation, the first 8 columns, now labeled 0 to 7, are the inputs, and the last column at index 8 is the target. Remember that we can call the .values attribute to get a NumPy array representation of this data. Next, we're going to create our train test split, 33% test and 67% train. Next, we're going to scale the data. Since the data is all real-valued continuous data, we're going to normalize it to have mean 0 and variance 1. We're also going to scale the target data. If you're not sure why this would be useful, then try removing it and comparing the results. Finally, we're going to fit and evaluate our model. You'll notice that the model is now called SVR rather than SVC. You can remember this easily because C stands for classification and R stands for regression. We're also going to take this opportunity to try out different kernels again. So let's run this and look at the results. Okay, so we get about 58.7 for the train score and 54.8 for the test score. By the way, it's important to remember that this score is not a classification accuracy because we are now doing regression. This number is the R-square, which is the square of the correlation coefficient. A value of 1 is the maximum, but 0 is not the minimum. And R-squared of 0 would just mean that our model performs just as well as predicting the mean of the targets for every sample. In fact, it's possible to get an R-square that's negative if your model is very bad. In that case, simply predicting the mean would be more accurate than using a model. Okay, so let's run this code again using the polynomial kernel. I wanted to use this kernel because it should remind you of polynomial regression, which we discussed in my linear regression course. Remember that an infinite Taylor series can be used to approximate arbitrary functions, so it would be reasonable to think that a polynomial kernel might be a good choice. So as you can see, our score improves. Let's now run this code one last time using the RBF kernel. Alright, so as you can see, our score improves once again. So at this point, you might conclude that RBF kernels seem to be quite useful tools. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss a topic called cross-validation. If we look at the documentation for the SVM again, we see that there are lots of options. Sometimes we refer to these options as hyperparameters, because they're not parameters of the model, but they are parameters of our system which affect how the model will perform. We can see that there are quite a few options here. C, which is a penalty parameter. You'll learn exactly what that means if you make it through the rest of this course. Kernel, which we've played around with a little bit in the previous exercises. Degree, which lets us choose the degree of the polynomial if we choose a polynomial kernel. Gamma, a kernel coefficient. So there are lots of hyperparameters here. How can we possibly test them all out to determine what's best? Well, the reality is we can't. But we can choose a subset of hyperparameters to try out and compare the results of those amongst each other. Now, how do we do this correctly? The basic idea behind cross-validation is this. We don't want to split the train and test data just once, because maybe the result we achieve on the test data is simply due to chance. Therefore, we'd like to have some statistical measure of how well our model performs. To that end, what we want to do is split the data randomly into k parts. That's why this is sometimes called k-fold cross-validation. What we do is pick one of the k parts to be the validation set and the rest to be the train set. Then we pick another one of the k parts to be the validation set and the rest to be the train set. So in the end, every one of these k parts has the opportunity to be part of the validation set and the rest will be the train set. And of course, this also means we'll be doing k different rounds and calculating k different accuracies. Alright, so what we do is calculate the validation accuracy in each of these k cases, and then take the mean and standard deviation. Using these statistical measurements, we can decide which set of hyperparameter choices is the best. One thing we can also do, if you want to take things further, is to treat each of the accuracies as a sample and do a statistical hypothesis test like a t-test. Then you can determine whether the result you got is statistically significant. We're not going to do that in this course, but you can feel free to ask about it on the Q&A if you are interested. So let's get to the code. The relevant file for this lecture is crossval.py. It might surprise you to see that this code is extremely short. In fact, the actual code takes up less space than the imports. The central item here is this new import, crossval_. This is going to return an array containing the validation accuracy for each of the k folds. The first step is, as always, to load in the data. As before, we're going to use the breast cancer dataset. Now for this example, we're only going to look at one hyperparameter c, the strength of the penalty term. We're going to test out 4 different values, 0.5, 1, 5, and 10. By the way, can you think of what this might look like if we wanted to test multiple different hyperparameters? Well, in that case, we would need a nested for loop. Each for loop would loop through the different possibilities for that particular hyperparameter. We call this type of hyperparameter search a grid search, since you can imagine each hyperparameter taking up an axis on a grid and then searching through regularly spaced intervals on that grid. You might also realize that such a search would be quite slow because you have a geometric increase for each hyperparameter you want to test. If you have n different values for m different hyperparameters, then the time complexity of your search would be O of n to the power m. In any case, let's move on to the rest of the code. You'll realize right away that we have one problem. In the previous code examples, we did a train test split by calling a function to split up the data. The problem with this is that it splits up the data only once, whereas for cross-validation, we want to split up the data a different way k times. So instead, the function crossval_score actually takes in the full dataset and splits up the data for us internally. However, this causes us another problem. Recall that we would like to scale our input data, but we don't just want to scale the training data and the validation data together. We would rather scale the validation data with respect to the mean and standard deviation of the training data. The problem is, on each round of cross-validation, what is considered the training data is going to be different. So in the previous scripts, we called fit transform on the train data and just transform on the test data. And the problem is we can't do that now because the splitting of the train and test data happens inside the function crossval_score. So I hope you understand why this is a problem. Luckily, scikit-learn provides us with a tool to handle this problem called a pipeline. When you create a pipeline, scikit-learn automatically knows that fitting should only be done on the train data and not on the test data. So what we're doing here is creating a pipeline with two objects. This is represented by a list of tuples. The first entry in the tuple is the name of the object, which you can name whatever you want, and the second entry is the object itself. In this case, the first object is the standard scalar, and the second object is the SVC, where we pass in the current value of C. Next, we can call crossval_score. Usually, the first argument of crossval_score would be the model SVC itself, but it can also accept pipelines of models, so that's why we can pass in the pipeline variable. The second argument is the input data, the third argument is the targets, and the fourth argument is the number of folds, what we've been referring to as k. This outputs a NumPy array of scores, after which we can print out the mean and standard deviation. So let's run this and see what we get. Alright, so according to our experiment, it looks like a value of C equals 5 is best, since it gives us an average validation accuracy of about 97.9%. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to conclude and summarize everything we learned in this section, the Beginner's Corner. This section was for beginners, and so it was all about how to use the SVM, but didn't contain any theory about how or why it actually works. Of course, that's what the rest of this course is about, and that material is more advanced, so it's for students who are not beginners. At the same time, I think this section answered a lot of questions many people have about machine learning, such as how to train a model on your data, how to make predictions on future data, and how to evaluate your model. All of these are important steps in any machine learning analysis. You also got to see that the SVM works quite well for a variety of common machine learning problems, such as recognizing handwritten digits and medical diagnosis, which are both classification problems. We also got to see the SVM work for a regression problem, which is not something that's often covered in courses about SVMs. We got to review important concepts, such as all data is the same, and machine learning is nothing but geometry. Most of us are not medical experts or civil engineers, yet we were able to build classifiers that could accurately perform medical diagnosis and predict the compressive strength of concrete. In fact, most of us could probably not explain what any of the input features mean. And that's the beauty of machine learning. It's not a semantic problem, it's a geometry problem. It's not knowledge-based, it's math-based. In fact, even if you are a medical expert, the chances that you are also a civil engineer are exceedingly small. In other words, even if you did become a knowledge-based expert, a machine learning model is easily still more flexible than you because it can also handle data from other fields in which you are not an expert. I want to end this section by answering a common question I get from beginners, which is how can I get my data into the right format in the first place? You'll notice that our data came neatly packaged as a CSV or Excel spreadsheet, or in the case of the breast cancer dataset, a NumPy array from a built-in scikit-learn function. The common pattern in all these cases is that the data exists in the form of a table, or to be more precise, a table of numbers. Where do these tables of numbers come from? How do you collect the data? Well, let's start with an obvious example, a medical experiment. Your job is to select a number of candidates for your experiment. Then, suppose you are able to recruit 10 of your peers to be subjects. You can ask each of them, what is your height? What is your weight? What is your blood pressure? And so forth. Obviously, you would ask them questions that you want to be features in your dataset. So I can say, John, how tall are you? Okay, 6 feet. John, what's your weight? Okay, 200 pounds. John, what's your blood pressure? Okay, 120/80. Then I can ask my next subject, Mary, how tall are you? Okay, 5 feet. Mary, what's your weight? Okay, 100 pounds. Mary, what's your blood pressure? Okay, 115/75. Then you could write down the answers in your Excel spreadsheet, assuming you know how to use Microsoft Excel, or whatever other spreadsheet software you use. And there you have it. That's how you can build an Excel spreadsheet for your dataset. Simply ask your subjects for a measurement, or measure it yourself and then write it down. Very easy. Another common scenario is when you collect data electronically. Suppose you have a website which contains a database full of user information, such as which products they viewed, the time they spend looking at each product, which products they purchased in the past, and so forth. Then you might need to use your SQL skills in order to query your database and get the data out in the right format. Another question you might have is, well, how do I build a website that collects such data? Well, then you need to be an expert in building websites or web applications. In other words, you might consider these things to be a matter of everyday programming, not of machine learning. Machine learning is more concerned with the theoretical aspects of modeling, how to build and deploy such a model, and how to evaluate its effectiveness. If what you're concerned about is how to write code to retrieve or process the data, you are probably more interested in regular basic programming. But the moral of the story is, if you want to know how to work with databases, then you should take a course on databases. If you want to know how to build a web application, then you should take a course on how to build web applications. All of these are just basic programming skills, and not what you would normally consider to be part of machine learning. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to review some ideas behind linear classification, and most importantly, the geometrical aspects of it. You always hear me say machine learning is nothing but a geometry problem. If you don't know what that means by now, then you're probably in big trouble, but hopefully this lecture will get you up to speed. So what do I mean machine learning is a geometry problem? Let's use one of my favorite examples, predicting who will pass my math exam. As inputs, I'm going to ask my students two questions. Number one, how many hours did you spend studying? And number two, how many hours did you spend playing video games? I'm going to collect some data, plot it on a grid, and of course, since this is my training data, it's going to come with labels, or in other words, colors. In this example, yellow dots are students who passed, and purple dots are students who did not pass. As you can see, it's easy to separate these two groups by a line. Students who studied a lot and didn't spend a lot of time playing video games passed. Conversely, students who played a lot of video games but didn't study a lot did not pass. The main takeaway from this example is that this is always going to be the geometry of a linear classifier, no matter what the problem is. It doesn't matter if I'm trying to predict whether or not students will pass my exam, or whether or not an email is spam or not spam, or whether or not a handwritten character is a 1 or a 2. These are all classification problems, and we can picture them as different colored dots on a grid separated by a line. Now, of course, one question you might have is, what if the data is not separable by a line? In that case, we'll need to use nonlinear methods, but we'll get to that later. Another key point is, while this example has 2 input dimensions, real-world problems might have many more. In those cases, the object that separates the different colors are called planes or hyperplanes. Of course, you can't visualize things beyond 2 or 3 dimensions, so it's not as if we can look at a picture of a 100-dimensional object. That just doesn't make sense. Luckily, 2 dimensions is all we need to develop our intuition, and all of the equations we derive in this course are dimension invariant, meaning the same equations apply no matter how many dimensions we're working in. Now, I'm sure most of you know that geometry isn't simply looking at pictures. Geometry is a field of mathematics, so we're going to have to deal with equations. We would like to know, what is the equation for a line, plane, or hyperplane? What are some of its properties? In the rest of this lecture, that's what we are going to review. You may recall from your grade school studies that the equation for a line is y equals mx plus b. In this equation, x represents the horizontal coordinate and y represents the vertical coordinate. M is the slope and b is the y-intercept. In this course, we don't want to use the letter y here because in machine learning, we usually use the letter y to represent the target. So in our case, we want to call the horizontal axis x1 and the vertical axis x2. This is convenient also if we have more than 2 dimensions. We can just call them x3, x4, x5, and so forth. So now, the equation of our line becomes x2 equals m times x1 plus b. Another form you may have encountered in your studies is ax1 plus bx2 plus c equals 0. Of course, this is easy to transform back into the previous form by using some simple algebraic manipulation. We can see that m prime equals minus a over b, and b prime equals minus c over b. And this is where I've set x2 equals to m prime x1 plus b prime, and I've renamed what used to be b into b prime so that they don't conflict with this new b. But this is still too elementary. What we eventually want to do is get to the form w transpose x plus b equals 0. In this equation, both w and x are vectors, while b is a scalar. Note how this version of the equation is dimension invariant. It doesn't matter what the dimensionality of w and x are, as long as they are the same. This equation still works and still represents a line, plane, or hyperplane. So what are the vectors x and w? Well, we can represent them in terms of their scalar components. So if x and w are both two-dimensional, then x is a vector containing the components x1 and x2, and w is a vector containing the components w1 and w2. Again, this is very easy to convert into the form we had before. If we just expand out the dot product, we get w1 times x1 plus w2 times x2 plus b equals 0. And if we compare this to what we had before, which was a prime x1 plus b prime x2 plus c prime equals 0, then we see that a prime equals w1, b prime equals w2, and c prime equals b. And of course, I put the prime symbol on our old equation so that we don't get the two different b's confused. Alright, so now we're in business. We can represent a line, plane, or hyperplane in the form of w transpose x plus b equals 0, which is the same form you're probably familiar with if you studied linear regression or logistic regression in the past. The next question is, what happens if we plug in different numbers into this equation? Well, let's suppose I have a line represented by the equation above, where w equals 1, 1, and b equals minus 1. Now suppose I plug in a value of x equals 0, 1 into this equation. What is the result? Well, the result is 1 times 0 plus 1 times 1 minus 1, which is equal to 0. Now suppose I plug in a value of x equals 1, 0 into this equation. What is the result? The result is 1 times 1 plus 1 times 0 minus 1 equals 0. My question for you now is, why did I get 0 in both these cases? The answer is because these values of x fall on the line. In fact, this is the very definition of a line. A line is simply made up of the set of all x vectors that satisfy this particular equation. And of course, using that logic, I can work backwards as well. If I find some vector x that satisfies this equation, then I can conclude that this data point x falls on the line. My next question for you is, what if I plug in a data point x into the left-hand side expression that does not fall on the line? Let's try one. Let's say x equals 1, 2. In this case, I would get 1 times 1 plus 1 times 2 minus 1 equals 2. Let's try another one. Let's say x equals 0, 0. In this case, I would get 1 times 0 plus 1 times 0 minus 1, which is equal to minus 1. Interesting. I noticed that all the data points that I can pass into this equation, which are on one side of the line, give me a positive number. All the data points on the other side of the line give me a negative number. And of course, let's not forget that all the points that lie directly on the line give me 0. In fact, these simple observations are what form the basis of my machine learning classifier. That's why I always say, machine learning might sound magical to some people, but in reality, it can be as simple as high school geometry. If you recall, this is the exact scenario we started with when we discussed our hypothetical classification problem. We have some red dots and we have some blue dots, and these are our training data. If we can find a line that separates the different colors, then we are done. We have our machine learning model. we can use our model to make new predictions. Suppose we have a new test point. Of course, you and I can simply look at this and tell right away that this should be classified as yellow, which means pass. But how do we do this in a computer? Well, that's simple. We just use our equations from before. We just say, given our test point x, if W transpose x plus B is greater than 0, then we predict fail. Otherwise, we predict pass. In pseudocode, this is just as simple. I can just turn this into an if statement. If W.x plus B is greater than 0, return +1, else return -1. Alternatively, I could just use NumPy's sign function to do this in one line. So I return np.sign of W.x plus B. As a side note, if you're familiar with logistic regression and neural networks, you're probably used to using 0 and 1 as your targets. SVM is one of those weird machine learning models where it's more convenient to use +1 and -1 instead. So for the rest of this course, when we talk about logistic regression, we'll be using 0 and 1. But when we start talking about SVM, we'll be going back to +1 and -1. Hey everyone, and welcome back to this class, Support Vector Machines in Python. It's important to remember how W relates to the geometric picture. In particular, W is called a normal vector to the plane, which means it is perpendicular to the plane. In 2 dimensions, it is perpendicular to the line. Now, some of you might ask, why is this true? To demonstrate how this might be, suppose I'm working in 3 dimensions, and suppose I begin by assuming that I have some normal vector, W equals ABC. Now suppose I also have some fixed point on the plane, P0 equals X0, Y0, Z0. By the way, note that I've switched from using the X1, X2 notation just for this example only, since it's easier to write XYZ without any subscripts to differentiate coordinates. Now, suppose I have another arbitrary point on this plane, P equals XYZ. So pretend that P0 is a fixed point, but P is a variable point which I can move around anywhere I want on the plane. Using my definitions of these quantities, what can I do? Well, there's one thing I know is true. I know that the vector P minus P0 lies parallel to the plane, because I've defined it in this way. Both points are directly on the plane itself, and therefore the difference between those vectors is parallel to the plane. The vector W I've defined to be perpendicular to the plane, since by definition, that's what a normal vector is. So an important point so far is that this vector W, which is normal to the plane, has nothing to do with the equation of the plane itself. I've simply defined some vector which I said is normal to the plane. Okay, so I know that if I have 2 vectors which are perpendicular to each other, then when I take the dot product, the answer should be 0. So let me calculate that. I get ABC dot x minus x0, y minus y0, and z minus z0, and this all equals to 0. So let's see what happens if I multiply this out. I get ax plus by plus zz minus all of ax naught plus by naught plus zz naught equals 0. Now remember that the point p naught is a fixed point, meaning it's just a set of numbers that satisfy the fact that it's a point on the plane. So what if I replace that whole term with a single number? Let's call it d. Now I have ax plus by plus cz plus d equals 0. In fact, this is the same equation I had before for the equation of a plane. And therefore, we can conclude that just by looking at the coefficients of x, y, and z, I can get the normal vector, or in other words, a vector which is perpendicular to the plane. And of course, this carries over to any number of dimensions. If I have a hyperplane defined by the equation W transpose x plus b equals 0, then I know automatically that W is a vector which is perpendicular to the hyperplane. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to review the basics of logistic regression. Although logistic regression isn't the topic of this course, I find that it provides good intuition for a lot of the things we're going to see in SVM theory. If you've never studied logistic regression before, then of course you're going to be more lost than others. So in that case, I would strongly recommend making use of the Q&A in order to fix any deficiencies in your background knowledge. If you have studied logistic regression before, then you're in a good place since you'll find that a lot of the concepts in this course will come naturally to you. So what is logistic regression? Logistic regression is a linear classifier, just like the one we studied in the last lecture. The difference is logistic regression adds some useful theoretical constructs on top of just the basic line or plane. And also, something we haven't discussed yet is, how do we even find this line or plane in the first place? As usual, we start with the form W transpose X plus B. At this point, we can give these variables names as per the conventions of logistic regression. W is referred to as the weight vector, hence why we use the letter W to represent it. X is referred to as the input vector, or vector of input features. B is called the bias term. Previously, when we looked at the geometry of linear classifiers, we looked at the expression W transpose X plus B to see if it was greater than 0, less than 0, or equal to 0. In logistic regression, we're going to do something a little different, but in the end you'll understand that they are actually really the same thing. So in logistic regression, we pass the expression W transpose X plus B into what is called the sigmoid function. The sigmoid function is defined as follows. The sigmoid of z is equal to 1 divided by 1 plus the exponent of minus z. This, by the way, is also sometimes called the logistic function, hence the term logistic regression. So what happens when I pass W transpose X plus B into the sigmoid function? Well, the sigmoid function has this S shape, which of course you're familiar with if you've studied neural networks. As you can see, the three situations we've described above can be mapped to the sigmoid output. If the input expression is greater than 0, then we'll always get a number between 0.5 and 1. If the input expression is less than 0, then we'll always get a number between 0 and 0.5. If the input expression is equal to 0, then we'll get exactly 0.5. The convenient thing about this mapping is that we can interpret the output as a probability. We can say that the probability that y equals 1 given x is equal to the sigmoid of W transpose X plus B. And remember that for logistic regression, y, the target, also called the label, will always be 0 or 1. So the probability that y equals 0 given x is just 1 minus this other probability, since both these probabilities must sum to 1, since they are the only two possible outcomes. In pseudocode, this is easy to implement. Since the labels are just 0 and 1, we can round the output of the sigmoid using np.round. Let's summarize everything we've discussed so far. We've spent this lecture going from a generic linear classifier to logistic regression, specifically looking at how to make predictions. For a generic linear classifier, we're looking at the expression W transpose X plus B. For logistic regression, we're looking at the probability that y equals 1 given x, which is equal to the sigmoid of W transpose X plus B. For a generic linear classifier, if the expression is greater than 0, we predict class 1. If it's less than 0, we predict class 0. If it's exactly 0, then we fall directly on the line. For logistic regression, if the probability that y equals 1 given x is greater than 0.5, we predict class 1. If it's less than 0.5, we predict class 0. If it's exactly 0.5, then we fall directly on the line. At this point, we've been talking about x and y as a generic input vector and target, but we know that we're going to have actual data to work with when we're running an experiment. So let's pretend I have this table of student data, and I want to use this data to build a model that can actually tell me whether or not a student will pass my math exam. So in this example, Alice studied for 8 hours and played video games for 0 hours. She passes. This gives me an input vector of 8, 0, and a target of y equals 1. Bob studied for 0 hours and played video games for 20 hours. He fails. This gives me an input vector of 0, 20, and a target of y equals 0. Pretty basic. To discuss this more generally, what I'm going to have is a set of n training samples, x1, y1, x2, y2, all the way up to xn, yn. The question now is, how can I use these training samples in order to build my model? In other words, how do I actually find the weight vector w and the bias term b? The answer is to first build up a loss function and then minimize it. Oftentimes, people try to automatically use the squared error loss function. If I let y hat equals p of y equals 1 given x, then they'll do something like sum over all the i's from 1 to n and add up the squared error between yi and y hat I. However, this is not the correct loss function for classification. Instead, for logistic regression, we use the cross-entropy loss function. It's equal to the sum over I equals 1 to n of yi times log of y hat I plus 1 minus yi times log of 1 minus y hat I. Now, it might not seem obvious at first, but this loss function, just like the squared error, encourages the y's to be close to the y hats. So how can we gain some intuition for that? Well, you can just plug some numbers in. If y equals 1 and y hat equals 1, then the loss is 0, which is of course good. If y equals 1 and y hat equals 0, then the loss is infinity, which is of course bad. And any y hat in between 0 and 1 will give me some number between 0 and infinity. In other words, if I'm exactly right, my loss is 0, and if I'm exactly wrong, then my loss is infinity, and everything in between is a finite loss. As a side note for more advanced students, you may want to recall 2 facts. Fact number 1 is that this loss function is convex, so the answer we find will always be a global minimum. Fact number 2 is that the theoretical reasoning behind why the cross-entropy loss function is the correct loss function to use is grounded in probability. We can show that this is equivalent to simply doing maximum likelihood estimation, although we won't since that's not important for this course. Once we have the loss function, the next step is always to figure out how to minimize it. That's how we're going to find w and b. If you recall, this is a process called training or fitting. With logistic regression, the simplest way to minimize our loss function is through a method called gradient descent. In its most basic form, it looks like this. We do a loop that goes until the loss converges to its minimum, and in each iteration, we take a small step in the direction of the gradient of the loss with respect to the parameters in question. As stated earlier, in this course we are not too concerned with how to actually derive this gradient or how to implement it in code, since it's not relevant to the theory behind SVMs. So this is as far as we need to go. All you need to know is that this is just some expression, and by doing this over and over again, we go down the gradient and find the minimum. Let's summarize this lecture since it's been quite long already. This lecture was all about taking a generic linear classifier and turning it into logistic regression. The logistic regression framework is quite useful since it allows us to make probabilistic predictions with our model. More importantly, it gives us a way to train the model, or in other words, find its weight vector and bias. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to look more closely at this loss function for logistic regression. You'll notice something strange about this model. As you recall, in order to achieve zero loss, we discovered that our predictions must be exactly correct. If the target is 0, then the output of the logistic regression must be exactly 0. If the target is 1, then the output of logistic regression must be exactly 1. Here's why this is strange. Remember that the output of logistic regression comes from the output of a sigmoid. How can we get a 1 or a 0 from this function? Well, this function only gives us 1 or 0 if the input is plus infinity or minus infinity. Since our inputs x are fixed, the only way to achieve infinity from this expression is if the values in w are infinity. Intuitively, you should be able to see why infinite weights are not good. Here's another way to think of this problem. Consider the line x1 plus x2 equals 0. This is a simple line that goes to the origin at a 45-degree angle downwards. Now multiply this entire thing by 10. We get 10 times x1 plus 10 times x2 equals 0, or the vector 10, 10 dotted with the vector x1, x2, meaning w equals 10, 10. Now wait a minute. We can see that this gives us exactly the same line. Now multiply this thing by 1 million. Again, the same line. So what is the problem? Well, it's that a line is not uniquely defined. There are multiple values of w and b that could give us the same line. This is problematic because, as we showed earlier, if we try to really minimize the logistic regression loss, our weights will just go closer and closer to infinity. Technically, these all represent the same line, so we don't really gain anything. In fact, we lose because values that are too large can lead to numerical instability. The answer to this is regularization. The idea behind regularization is that we want to penalize weights that are large in order to avoid the situation where they go towards infinity. To do this, we just add a regularization term to our original loss, which is equal to a constant times the squared magnitude of the weights. Normally, we only penalize the weights and not the bias term, since the bias term moves the line away from the origin if that's necessary according to the data. At this point, you might be thinking, the lazy programmer is crazy. We already learned this stuff in the logistic regression course, so what is the point of all this? As you'll see later in this course, this idea of the loss being made up of two parts will actually become a central piece in SVM theory. So it's important to recognize the basic form of this equation, and when you see it again later, you'll have a sense of familiarity and comfort, since you know it's something you've dealt with before. So just to reiterate, our loss is now the sum of two terms. One of these terms penalizes the error of our model. So if we get the prediction wrong, then our error increases. And if we get the prediction right, our error decreases. The other term penalizes large weights via the squared magnitude of the weights multiplied by a constant. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to further explore this idea of regularization. In particular, why does logistic regression want to find infinite weights? Let's consider a very basic classification problem. We have one data point at 1, 1 with the label 1, and one data point at -1, -1 with the label 0. As usual, our separating line is just a 45-degree line going downward to the right. Remember, the weights are not uniquely determined by this line, but let's say they are 1, 1 with a bias of 0. In this case, the logit, which is the input to the sigmoid, is 2. This is for the data point 1, 1. So sigmoid of 2 gives us a posterior probability of 88%. What about the data point on the opposite side? For the other data point, -1, -1, we get a logit of -2, which gives us a posterior probability that y equals 1 of 12%. Of course, this just means that p of y equals 0 given x is 88%. Ideally, logistic regression wants these probabilities to be 100%. This makes sense because this is the training data. The label is in fact deterministic. We know with 100% probability what the labels are because we were told what they are. Of course, we can just increase the posterior probability of our predictions by increasing the value of the weights proportionally so that the line itself doesn't change. So if our line can be represented by 1, 1, then we can just change the weights to 1 trillion and 1 trillion, and we would achieve a much lower cost and much stronger posterior probabilities, very close to 100%. In this lecture, we don't want to do that because we already know about regularization. In this lecture, I want to consider a new scenario. Let's compare different data points. Suppose I have a data point at 2, 2. Now my logit is 4, which gives me a prediction probability of 98.2%. That seems interesting. Just by going further away from the line, my probability jumped by 10%. Now suppose I have another data point at 3, 3. My logit is now 6, which gives me a prediction probability of 99.6%. So that's interesting. Even though 2, 2 is the same distance away from 1, 1 as it is from 3, 3, the jump in probability is much smaller going from 1, 1 to 2, 2 as it is for going from 2, 2 to 3, 3. Of course, this is just due to the nature of the sigmoid. As you can see, the closer we are to the center, the smaller the change we need in the input to cause a big change in the output. As you go away from the center, even large changes in the input yield only small changes in the output. So what does this mean for data points in relation to the line? Well, it means that data points which are further away from the line yield more confident predictions, whereas data points which are close to the line yield more ambiguous predictions. Data points which lie directly on the line yield the most ambiguous predictions, since we don't know either way whether the data point should be classified as 0 or 1. We're 50% certain that it should belong to either class. Let's look at this picture again, but not in terms of different data points. Let's consider different lines. From this picture, we can see that both lines perfectly separate the training points. However, it's obvious that one line provides better separation than the other. Which one? Well, it's the one that's far away from all the training points. Even though the other line separates the two colors, it gets very close to the training points. It seems more likely to misclassify points that are not in the training set. In terms of what we discussed in this lecture, it would seem that this line is not ideal because it has low confidence about some of the training points, when there is no reason for that to be the case. The line on the left looks like a much better fit and is more confident in its predictions on the training data. Let's elaborate on this point a little more, specifically why the bad line is so bad. If we look at this orange test point on the right, we can see why this line isn't very good. This test point is very close to the rest of the purple dots, yet much further away from yellow. This line classifies the test point as yellow, which is probably not right. Let's consider another line which could be considered bad. This is the same line as the previous good line, except shifted much closer to the purple side. As you can see, we still achieve 100% training accuracy. The problem is, using our intuition about the confidence of predictions, we can see that with this line, we would be much more confident about predictions near the yellow dots as opposed to the purple dots. But why should we be? We don't have any reason to believe that the yellow dots are more correct than the purple dots. Why not move the line closer to the yellow side? Of course, we have no reason to do either, and so perhaps in the middle is the best place. This is a very important theme to understand for SVM, so if you have an intuition for this, then SVM will also be very intuitive. To summarize this lecture, we took a closer look at how logistic regression assigns probabilities to data points in terms of where they are in relation to the separating line or hyperplane. We found that the model is very confident in its predictions that are very far away from the line, and less confident in its predictions that are very close to the line. Later, we'll see that one of the things SVM tries to do is adjust its line so that it's far away as possible from all the training points. Intuitively, this makes sense because, as I mentioned earlier, we are in reality 100% confident about the labels of our training data, and so we should adjust our line to increase our confidence in our training predictions. How do we make this adjustment? By placing the line as far away from all the training points as possible. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to review one final concept from logistic regression, which is how we can use our linear model to handle nonlinear problems. If you've taken my courses before, then you know my favorite examples for this are the classic XOR and donut problems. They are two-dimensional nonlinear problems that can't be solved naively by linear models. In other words, there is no line we can find that can separate the two colors on these grids. One way we can solve this problem is using our knowledge of the data to do feature engineering. To review, feature engineering can be as basic as simply using your domain knowledge in whatever field you work in to handpick useful features. For example, if you're an expert in molecular biology, then you would be very good at picking useful features for molecular biology problems. If you are an expert in finance, then you would be very good at picking useful features for financial problems. In machine learning, this is often a non-ideal solution, since it kind of defeats the purpose of what many people believe machine learning should be, an automated learning program that doesn't require human input. At the same time, handpicking features is often a useful solution, so in practical terms, one can't disregard its utility. In this lecture, we'll look at some hand-picked features which, at the same time, are easy to incorporate into automated solutions. You'll see what I mean by that at the end of this lecture. Let's start with the donut problem. In the donut problem, it's clear that we can't draw a line between the two classes. At the same time, we know that it's very easy to separate these two classes. If the inner circle has radius r1 and the outer circle has radius r2, then the distance of each data point from the origin should be the only feature required to discriminate between the two classes. For the sake of this example, let's suppose r1 equals 5 and r2 equals 10. So, given some data vector x, which contains the components x1 and x2, how can we find the distance to the origin? Well, using our high school math skills, we can calculate this as r equals the square root of x1 squared plus x2 squared. To build a simple classifier out of this, maybe we could do something like, if r is greater than 7.5, predict class 1, otherwise predict class 0. Now, theoretically, we could just make a new feature x3 equal to the square root of x1 squared plus x2 squared. But this level of feature engineering isn't desirable. Remember, we like more simple solutions because we want to automate this process. So the first step towards a simpler solution would be to not take the square root at all. Perhaps we could set x3 equal to x1 squared plus x2 squared. But we can go even further than that. Instead, let's just make one new feature x3 equal to x1 squared and another new feature x4 equal to x2 squared. Now this is taking on a more generic form. Using these new features, we can build a linear classifier, which looks a lot like what we had before. In our example, we would like x1 squared plus x2 squared equals 7.5 squared to be our decision boundary. This should be easy to convert into a linear classifier. Let's use our new symbols x3 and x4 and move 7.5 squared to the other side. Then we get x3 plus x4 minus 7.5 squared equals 0 as our line, also called the decision boundary. Now our classifier again takes the form of w transpose x plus b, where w is 1, 1, b is minus 7.5 squared, and x is x3, x4. For the donut problem, one thing you might want to do is actually include the original features as well, x1 and x2. So our full classifier would be a model of the form w1, w2, w3, w4, and then x being x1, x2, x1 squared, and x2 squared. Why might we want to do this? Well, suppose the donuts are not centered at the origin, but rather some arbitrary point AB. Now, to calculate the radius, we'd have to use the formula r equals the square root of x1 minus a squared plus x2 minus b squared. And if you expand this out, you get a new expression x1 squared minus 2ax1 plus a squared plus x2 squared minus 2bx2 plus b squared. As you can see, this contains both square terms and linear terms. So in order to create a classifier that can handle more generic problems, it's better to include the original features as well. Let's move on to the XOR problem. Suppose our data lies in the points 1, 1, minus 1, 1, 1, minus 1, and minus 1, minus 1. In this case, x1 squared and x2 squared are not good features because 1 squared is the same as minus 1 squared. They both just give you 1. These would in fact be very useless features. Instead, a better feature might be x1 times x2, which is often referred to as an interaction term because it measures the effect of two different features interacting with each other. In this example, it's easy to see how this helps. Both 1, 1 and minus 1, minus 1 belong to the same class. When we multiply these two components together, we get plus 1. On the other hand, both minus 1, 1 and 1, minus 1 belong to the same class as each other. When we multiply these two components together, we get minus 1. Therefore, our decision rule again is very simple. If x1, x2 is greater than 0, predict class 1, otherwise predict class 0. Now, unlike the donut problem, there's no need to simplify this feature further. It's easy to see again why this yields a linear classifier. If we let x3 equal to x1 times x2, and the full feature vector x equal to x1, x2, x3, then we can again put our classifier in the form of w transpose x plus b. In this case, w equals 0, 0, 1, and b equals 0. And here again, I've decided to keep the x1 and x2 terms in the feature vector from the start, since you already know why keeping them is useful. To combine what we've learned so far, what we often do in reality is this. Instead of testing each individual combination of quadratic terms, such as x1 squared, x2 squared, or x1, x2, to see if they work, we simply include them all. This is what we mean by automatic machine learning. Instead of having to try different features manually, we simply say, let's apply a polynomial feature expansion. There is one tiny problem with this, however. Suppose we have more input features, say 3. Now we have more quadratic terms, x1 squared, x2 squared, x3 squared, as well as x1, x2, x1, x3, and x2, x3. What if we have 4 features? Then we have x1 squared, x2 squared, x3 squared, and x4 squared, as well as all the interaction terms, x1, x2, x1, x3, x1, x4, x2, x3, x2, x4, and x3, x4. So it seems like the number of terms we have to deal with is growing very fast. Now, what if we increase the degree of the polynomial? Suppose we want to work with polynomials of degree 3. Then we have, for the degree 3 terms, x1 cubed, x2 cubed, x1 squared times x2, and x1 times x2 squared. But don't forget, we still have the degree 2 terms, x1 squared, x2 squared, and x1 times x2. And if you want to see how quickly this can grow, try it with a degree 4 or a degree 5 polynomial, keeping in mind that you still have to include all the lower degree terms. So what's the point of learning about all this stuff? Well, one of the key features of the SVM is that it does all this and more. In fact, it does so much more elegantly than what we saw here, without exploding the dimensionality of our dataset, but you'll just have to wait and see exactly why that is. If you did the beginner's corner, you already got a taste of this, because we use the polynomial kernel in our examples. So we are at least aware of the fact that SVM has the capability to use a polynomial feature expansion. Just exactly how it does that, well, you'll have to wait and see. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this section of the course, we reviewed linear classification with logistic regression as our primary motivating example. First, we noted that it's very important to view everything we're doing as a geometry problem. What we're doing is industry invariant. It doesn't matter what your practical application is, the geometry of this problem is the same. It doesn't matter if you're doing medicine, finance, insurance, whatever. Of course, we already covered how to apply SVMs to actual data in the beginner's corner, so I think we've moved beyond that at this point. We saw that a machine learning linear classifier can be expressed in the form of W transpose X plus B. This allows us to review some of the central entities in a linear classifier, namely W, the weight vector, X, the input vector, and B, the bias. We learned that the weight vector is perpendicular to the separating hyperplane, which is an important geometrical fact that will become useful later. We learned how a line helps us represent a classifier's decision rule. In particular, if W transpose X plus B is greater than 0, we predict class 1. If it's less than 0, then we predict class minus 1 or 0 depending on what convention you use. Next, we reviewed logistic regression. Logistic regression is a good linear model to review because it introduces us to many important objects that we need to describe what we're doing. First, we have our training set, which consists of pairs of x's and y's, where xi is the input vector and yi is the target or label. The output of logistic regression is a probability, which allows us to express how confident we are in a model's prediction. We built up a loss function which gives us an objective that, if we minimize this objective with respect to W and B, we have found precisely the W and B that provides good separation between the classes in our dataset. After further investigating the loss function, we realized one major problem. It encourages the weights of our model to go to infinity. Of course, weights at infinity are no good, and so we like to introduce regularization to discourage the weights from getting too large. The primary goal of looking at regularization was to recognize that the loss is ultimately the sum of two different terms. One penalizes the classification error, whereas the other penalizes large weights. If you're comfortable with this, then you'll be very comfortable when you see it again in the context of SVM. Another thing we looked at is the model's confidence in its predictions, in terms of where the data points lie with respect to the decision boundary. We saw that points very close to the line have probabilities closer to 50%, whereas points very far from the line have probabilities closer to 0 or 100%. We were introduced to the notion that It might be a good idea to find a line, plane, or hyperplane such that it's as far away as possible from the training examples. Next, we discussed polynomial feature expansions, which help us solve nonlinear problems such as the donut and XOR. Now, while the donut and XOR might seem overly simplistic, it is reasonable to assume that many real-world problems will have nonlinear decision boundaries. One problem with the polynomial feature expansion is that the number of features grows very large very fast. I alluded to the fact that SVM is going to help us solve this problem efficiently somehow. In the next section of this course, we'll start looking at SVMs, and we'll see how this theory all ties together to give us our first look at the SVM model. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I'm going to introduce this next section of the course and also give you an outline of what you're about to learn. So far, what we've done in this course is review logistic regression, placing special emphasis on the parts which are relevant to when we study SVM. In particular, we looked at the equation for a hyperplane and how the weight vector also happens to be normal to the hyperplane. We looked at the idea that the magnitude of the weight vector is unconstrained unless we use regularization. We looked at the concept of prediction confidence and how there are two ways to be more confident about a prediction. The first way is to simply have bigger weights, which we know in some way is not ideal. The second way is to have the data points be further away from the line, which seems like a more reasonable objective. In this section, we'll see how the SVM handles these issues. First, we'll look at the scenario in which the data is perfectly linearly separable. As you know, we can always picture this as two clouds separated by a line. This nice linear separability is necessary to develop both the theory and intuition for the SVM. We'll introduce the idea that the SVM is a maximum margin classifier, and we'll see how exactly we define margins later in this section. Once we've defined what we mean by margin, we'll set up our objective, which of course our SVM will then solve. Importantly, our objective is not one that can be solved by conventional methods, such as gradient descent. Instead, we need to employ the optimization method known as quadratic programming. If you've never heard of that before, you need not worry because I'm going to explain exactly what that means. Quadratic programming is nearly a separate topic from machine learning, and so students studying machine learning would usually not be studying methods for solving quadratic programs. Instead, we would be happy to use library functions to do that for us. This is just like how you would probably not write a function to invert a matrix or a sample from a Gaussian. They're just on a different level of the hierarchy of responsibility, not usually something the machine learning student would concern themselves with. Once we've established the basic theory behind the linear SVM, we'll reintroduce the idea that some data points might be misclassified. We'll see how this gives us what is called the soft margin SVM, and in a way acts like a regularizer. We'll see that this gives us an objective that looks a lot like regularized logistic regression. Finally, we'll discuss the loss function for the SVM, which is closely related to the logistic regression's cross-entropy loss, and this will help us paint an overall picture of how different loss functions are chosen for different classification models. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss the basic ideas behind the linear SVM, more focused on intuition rather than precision. This lecture is also going to be used to set up some basic definitions. In the next few lectures, we'll build on this by being more rigorous. So to start with, you recall from the previous section that one of our central concerns in linear classification is determining which line is the best line. Our definition of the best line is the line that is furthest away from all the training data. Of course, we always imagine that our data consists of two linearly separable clouds. In some resources, these are referred to as convex hulls, which you can think of as a polygon that is made up of the outermost data points from each class. In this course, we won't require the concept of convex hulls for our derivations, so I'm just going to refer to them as clouds. At the same time, it's nice to know about the terminology you might see in your external research. So these two polygons are the convex hulls. Now, in this picture, the line that best fits between these two clouds is a line that goes right in the middle, the red line. This is better than the other two lines. The green line is a terrible line because it doesn't even separate the data from the two classes. The blue line separates the data, but it gets too close to the training points. The red line is right in the middle. But at this point, I want to define what I mean by middle more clearly. In this example, you can see that there are 2 points in each class that are closest to the other class. These 2 points are right at the edge of each cloud. And these 2 points are the points that give us the shortest line to the decision boundary. By middle, I mean I want my line to be right in the middle of this connecting line and perpendicular to it. What does this do? Well, it maximizes the distance between all of the points on either side of the line to the line itself. Let's consider what would happen if I move this line. Now it's shifted over towards one class. And sure, I've put this line further away from some of the points, but I've also decreased the distance between the line and some of the other points. Therefore, this line is not ideal. In other words, we can summarize this in one statement. We don't just want to maximize the distance between the line and any point. We want to maximize the minimum distance between the line over all points. I can sort of write this informally as follows. So let dist of I be the distance between the line and data point I. The minimum distance between the line and any point is the min over I from 1 to n of dist I. Let's call that min dist. My goal then is to maximize min dist. So you can see we end up with this maximum min structure. In SVM theory, we refer to this distance as a margin. That's why the SVM is also referred to as a maximum margin classifier. Intuitively, from a machine learning perspective, what we want to do is find some equation that represents the margin. If we can do that, then we can treat it like an objective function and use some optimization algorithm to maximize this objective. In other words, I have some objective j, which I want to maximize with respect to the parameters w and b. And of course, j is a function of both the training data and the model parameters. Another fact I want us to remember at this point is that a line is not uniquely defined. If we can define some line with w transpose x plus b equals 0, then we can define the same line with 2w and 2b, or 10w and 10b. They all give us the same line. At this point, it may not be at all clear how the idea of scaling w and b could be related to the margin, but that's what we'll be talking about in the next lecture. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to start looking at the linear SVM more precisely. In particular, we're going to start off by more rigorously defining margins. Intuitively, we can think of the margin as the distance between a data point and the separating hyperplane, and we analogously think of it as the classifier's confidence in its prediction on that data point. Now we are going to take these ideas further. The first term I want to define is the functional margin. Let's recall some facts about linear classification. Given some training example x of I, if w transpose x of I plus b is greater than 0 and y of I is plus 1, then our prediction is correct. Conversely, if w transpose xi plus b is less than 0 and y of I is minus 1, then again our prediction is correct. If the sign of w transpose xi plus b is reversed, then our prediction is incorrect. But remember, we are currently only interested in linearly separable problems, so let's assume our predictions are all correct. So how can I combine these two facts into one equation? Well, I can say that if y of I times w transpose x of I plus b is greater than 0, then my prediction is correct. The next thing I want to recall is this idea of prediction confidence. If this expression, y of I times w transpose x of I plus b, is bigger, then my prediction is more confident. If it's closer to 0, then my prediction is less confident. Well, why not simply give this quantity a name? This is what we call the functional margin. We'll use the symbol gamma hat of I to be the functional margin with respect to the training point I. Additionally, we can define the functional margin of the parameters w and b with respect to the entire training set S as the minimum functional margin over all n training points. At this point, it might seem like we're defining these things for no reason, but just bear with me for now. It's all going to come together soon. It's important to remember that since a line is not uniquely defined, and the parameters w and b can be scaled arbitrarily, then the functional margin is dependent on the scale of w and b. In other words, the functional margin does not represent the distance between a line and a data point. So the question now is, what kind of expression do I get if I do want to know the distance between the line and a data point? This quantity, after all, is what I intuitively think of as a margin. So let's define that next. The distance between the line and a data point is in fact known as the geometric margin. Let's call this gamma I. At this point, we don't know what the expression should be for gamma I, but we can use our knowledge of geometry to derive it. Let's consider some data point A. The perpendicular line segment from A to the line meets the line at point B. In other words, the vector BA is normal to the line. From this, we can derive two facts. First, the length of BA is simply gamma I. Second, the unit vector for BA can be expressed in terms of W. As you recall, the vector W is also normal to the line, and so W divided by the magnitude of W is the unit vector pointing in the same direction as BA, so their unit vectors are the same. Therefore, the vector BA is equal to gamma I times W divided by the magnitude of W. Next, we can denote the origin as O, so that the vector OA is simply the data point xi. What about OB? The vector OB is simply a point on the line. Of course, OB, BA, and OA form a triangle, so we can express OB in terms of BA and OA. In particular, OB is equal to OA minus BA, which is equal to x of I minus gamma I times W divided by the magnitude of W. The next thing to realize is that, as per the rules of geometry, since the vector OB lies on the line, that means W dotted with OB plus B must equal 0. This is just due to the definition of a line. What does this give me? Well, it gives me an equation where it looks like I can isolate gamma I. So let's try that. First, I can multiply W transpose by each term in the brackets. Now it looks like I have this strange W trans W term, which you might not know what to do with right away. But let's consider the definition of a dot product. The dot product between W and itself is just the sum over the squared components. But if you think about it, this is also related to the magnitude of W. As you recall, the magnitude of W can be expressed as the square root of the sum over these squared components. In other words, W transpose W is just the magnitude of W squared. So I can rewrite my expression as W transpose Xi minus gamma I times the magnitude of W plus B equals 0. Finally, I can isolate gamma I using simple algebra to get that gamma I is equal to the unit vector for W transpose X of I plus B divided by the magnitude of W. At this point, we have to remember that we only derive the above expression for a gamma on one side of the line. Of course, if we took a data point on the other side of the line, the direction of the line segment from the line to the data point would be reversed. Intuitively, we can just write down the answer, but if this confuses you, then of course you should feel free to go back and derive it from scratch. So to correct for the fact that data points can be on either side of the line, our final expression for the geometric margin becomes yi times the expression we had before. Now, if you look at this expression carefully, you'll notice two things. First, you can see that this expression is invariant to the scale of W and B. This is because we always divide by the magnitude of W. Of course, this makes complete sense because the geometric margin represents an actual distance in space. This distance can't increase or decrease depending on the scale of W and B. Second, you will notice that this expression has a very simple relationship to the functional margin. The geometric margin is just the functional margin divided by the magnitude of W. This will come in handy later, so you'll want to remember this relationship. The final definition we want to state, which may seem somewhat trivial, is to define the geometric margin of the parameters W and B with respect to the entire training set S. This is analogous to what we did for the functional margin earlier. As you probably expected, this is just the min over the geometric margin with respect to each individual training point. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to build on what we discussed in the previous lecture in order to derive the SVM objective. To recap, what we've done so far is to define both the functional and geometric margins. The geometric margin represents actual distances between the data points and the hyperplane, whereas the functional margin is more like a confidence value representing how confident we are in the model's predictions. To do this, we're going to break our objective down into two parts. The first part is simply to repeat what we stated earlier. We want to maximize the margin. Of course, by margin, we mean the geometric margin, which represents the actual distances in space. It wouldn't make sense to maximize the functional margin, since that would simply require making the magnitudes of W and B very large. The second part is to ensure our model correctly classifies all the training points. In order to do this, we can express it as a set of constraints. We can say for all data points from the positive class, we would like that W transpose Xi plus B is greater than 0. And for all the data points from the negative class, we would like W transpose Xi plus B less than 0. And if you recall, it is easy to combine these two constraints into one by saying y of I times W transpose X of I plus B is greater than 0. Of course, this is incomplete. What we would like to do is enforce a stronger constraint, that y of I times W transpose X of I plus B is greater than or equal to gamma hat, the functional margin. Why? Well, we don't simply want the confidence in our model predictions to be greater than 0. By definition, they must be greater than or equal to the margin. Otherwise, the margin would cease to be the margin in the first place. At the same time, by having gamma appear in the constraints, this connects the first part of our objective to the second part. To state our problem more concisely, we want to maximize gamma subject to the constraint y of I times w transpose x of I plus b is greater than or equal to gamma hat for all I from 1 to n. As a side note, if you're still somewhat new to machine learning or computer science, you've probably never seen a problem like this before. It looks a little unusual because a machine learning problem doesn't usually consist of more than one expression to optimize, as it does when we're talking about logistic regression or neural networks. At this point, I want you to just hold that thought for a while and we'll come back to it later. Just know that problems of this form appear commonly in computer science and in other fields, such as operations research, so just know that they are well studied. As another side note, you can see that these constraints are simply a result of the definition of the functional margin. If you recall, the functional margin for a training point is y of I times w transpose x of I plus b, and the functional margin with respect to the training set is gamma hat, which is equal to the minimum of all the individual gamma hats. Therefore, by definition, gamma hat is less than or equal to all the gamma hat i's. And we can just replace gamma hat I with the actual expression for gamma hat I, and we get the inequality constraints we saw earlier. Note that in this expression, we can also replace gamma with gamma hat so that only gamma hat appears. This is somewhat more convenient, but still inconvenient. There are two things of note here. First, if you recall, I said that problems of this form have been well studied in the past. In fact, entire software packages exist to solve problems of this form. Unfortunately, the expression above is not solvable by such standard software packages. You'll see why that is later on in this course. So just know for now that this expression is not ideal. If you are familiar with these types of problems, then you'll know that we would like the objective we want to maximize or minimize to be in the form of a linear or quadratic function. The second thing to note is that this objective still does not constrain the magnitude of w and b. It might look like the objective increases when the magnitude of w decreases, but keep in mind that it's still equal to the geometric margin, which is invariant to the magnitude of w. So as the problem is currently stated, there's nothing stopping us from simply making w and b very large. Here's what we can do. Since the functional margin gamma hat is somewhat of an arbitrary number, let's set it equal to 1. Let's see what consequences this has on our geometric picture. Actually, what we're going to do is start from the geometric picture and then see how the functional margin becomes 1 as a consequence. So everything we're about to do is self-consistent. First, we're going to look at this picture again where we have these 2 points, one from each class, which are the closest points connecting the 2 clouds. Our separating line is right in the middle. Now what we can do is define 2 new lines. I'll call the line that goes to the positive point the positive margin line, and it is given by the equation w transpose x plus b equals +1. I'll call the line that goes through the negative point the negative margin line, and it is given by the equation w transpose x plus b equals -1. Now, one question you might have is, how do I know the number on the right-hand side is equal to plus or minus 1? Well, it's the same reason that I know that w and b can be scaled arbitrarily. I've simply defined the line to be this way. In other words, I can really put any constant on the right-hand side that I want because I can scale w and b however I want. I'm just making them +1 and -1 for my convenience. Next, we'll see how this leads us to a functional margin of 1. First, let's call the point on the positive side x plus and the point on the negative side x minus. Consider the vector x plus minus x minus. We know that this vector is parallel to the vector w, since they are both normal to the line. Using this fact, I can find the distance between x plus and x minus. Let's start with the equations for the margin lines. Since x plus is on the positive margin line, I know that w transpose x plus b is equal to 1. And since x minus is on the negative margin line, I know that w transpose x minus plus b is equal to minus 1. Now I can subtract these two equations to get w transpose x plus b minus w transpose x minus b is equal to 1 minus minus 1. Simplifying, I get that w transpose times x plus minus x minus is equal to 2. Since w and the difference vector x plus and x minus are parallel, I know this is the same as saying the magnitude of w times the magnitude of x plus minus x minus is equal to 2. This means that the distance between the positive point and the negative point is 2 over the magnitude of w. And of course, since the line is in the middle, the distance between the line and either of these points is 1 over the magnitude of w. And of course, that is equal to gamma. Finally, I can recall that gamma is just gamma hat divided by the magnitude of w, which confirms the fact that the functional margin gamma hat is fixed to 1 as we originally suggested. Now that was a big digression, but hopefully you haven't forgotten that our goal is to find a solvable objective for our problem. The funny thing about fixing the functional margin is that it now leaves us to maximize the geometric margin in terms of the magnitude of w. So let's take the same objective we had before, but replace the functional margin gamma hat with 1. Now we get that we want to maximize over w and b 1 over the magnitude of w, subject to the constraints y of I times w transpose x of I plus b is greater than or equal to 1 for all I from 1 to n. Now this has an interesting form. Using basic algebra, we can reason that maximizing 1 over the magnitude of w is the same as minimizing just the magnitude of w, which is the same as minimizing the magnitude of w squared, which is the same as minimizing 1/2 times the magnitude of w squared. The reason we add the 1/2 is because it makes taking the derivative more convenient later on. And so finally, we end up with the problem stated as minimize over w and b 1/2 the magnitude of w squared, subject to the constraints y of I times w transpose x of I plus b is greater than or equal to 1 for all I from 1 to n. And if you recall, the magnitude of w squared is simply the expression w1 squared plus w2 squared all the way up to wd squared, which is a quadratic expression. And as I mentioned earlier, such a problem is completely solvable by standard software packages. These types of problems are called quadratic programs, which we'll explain more in depth, just at a high level, in the next lecture. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to go a little more in depth on this idea of quadratic programs, since most of you have probably never heard of them before. The first thing I want to discuss is the name. It seems like a weird name, quadratic program. What does this have to do with programming, you might ask? When you hear the word program, you might think of computer program. However, these two uses of the word program are not equivalent. The concept behind quadratic programs, and as we'll also discuss, linear programs, were discovered long before actual computer programs were invented. Linear programs were studied as far back as the time of Fourier, and the fundamental algorithms behind linear programming were discovered around World War II. The idea behind this lecture is I'm going to share with you some simple examples of linear and quadratic programs to boost your confidence in knowing that not only do problems of this type exist, they are common and readily solvable by standard software. First, let's start with a simple linear programming problem. Let's pretend we are Apple. We're selling two iPhones, the iPhone X and the iPhone XS. Our goal is to determine how many of each phone to produce each day. Here's the information we're given. We expect a demand of 100 units per day for the iPhone XS and 80 units per day for the iPhone X. We have limitations on production capacity, so no more than 200 units of the iPhone X and 150 units of the iPhone XS can be produced on each day. The iPhone XS is more difficult to produce, so that's why we can't produce as many of them. Furthermore, to meet our production contract, we must produce at least 200 units in total of either phone per day. Finally, each iPhone X sold results in a $2 profit, but each iPhone XS sold results in a $5 profit. How many iPhone X's and iPhone XS's should we produce each day? Of course, our goal is to maximize profit. If we let X equal the number of iPhone X's produced and Y equal the number of iPhone XS's produced, then we can express the profit as 2X plus 5Y. Now, if we had unlimited resources, we could just produce an infinite number of phones, but we can't, so we have to account for the constraints. My first constraint is that X is greater than or equal to 80. This is so I can meet the demand for the iPhone X. I also have Y should be greater than or equal to 100 to meet the demand for the iPhone XS. I also have that X must be less than or equal to 200 since I can't produce more than 200 units of the iPhone X. Similarly, I have Y less than or equal to 150 since I can't produce more than 150 units of the iPhone XS. And finally, I have that X plus Y must be greater than or equal to 200 to fulfill my production contract. So overall, I have a problem of the form, maximize over X and Y, 2X plus 5Y, subject to the constraints, 80 is less than or equal to X, which is less than or equal to 200, 100 less than or equal to Y, which is less than or equal to 150, and X plus Y must be greater than or equal to 200. Of course, we can restate our problem in another form. If I use x1 and x2 to represent the number of iPhone X's and the number of iPhone XS's produced, respectively, then I can combine them into a single vector x. Then I can express my problem in a more general form. To maximize over the vector x, the vector C transpose x subject to the constraint AX is less than or equal to B. Note how the components of the problem make up a linear program. First, the objective is a linear function of the variable vector x. Second, note that the constraints are also a linear function of the variable x. So the general form of a linear program is a linear objective followed by linear constraints. In this more general form, you can imagine that if I had some generic software that could solve mathematical problems of this form, then my problem could be solved just by using an API or a library. In fact, this should remind you a lot of machine learning. Another great example of a linear program is this. In my linear regression course, a lot of students often ask me, why do we use the squared error? It seems just as reasonable to use the absolute error. Let's see what would happen if I did that. My loss would become the sum from I equals 1 to n of the absolute value of y of I minus w transpose x of I. But more in the spirit of SVM, we might simply want to minimize the maximum absolute error. In other words, I want to minimize over w the max from I equals 1 to n of the absolute value of y of I minus w transpose x of I. Now if I let the error for each training sample be epsilon I, then I can state my problem as follows. First, I can let epsilon, with no subscript, be the maximum absolute error. That should remind you of our margin in the SVM. Then I simply want to minimize epsilon, subject to the constraint that all the other errors have to be less than or equal to epsilon. Again, we have a linear objective followed by linear constraints. Let's now consider an example of a quadratic program. One of the most popular applications of quadratic programming is portfolio optimization. In this scenario, suppose I have a set of stocks I am considering investing in, and I would like to know what percentage of my money I should invest in each stock. Let's call this x, where each component of the vector x, called xi, is the proportion of money I will invest in asset I. Now suppose I have some historical data for each stock. Importantly, this gives me some information about how each stock is correlated with the others. For example, if one stock goes up, another tends to go down. That would be a negative correlation. In order to find such correlations, what I would do is find the covariance matrix. So for D stocks, I would get a D by D covariance matrix. My portfolio risk is equal to 1/2 times x transpose C times x, which is a quantity that I want to minimize. Furthermore, I am able to obtain an estimated return for each stock M of I. Thus, my total return is the weighted sum of M of I times X of I. As a constraint, I would also like my total return to be at least some number R. Finally, since X of I represents a proportion of my investment, I have another constraint that all the X of I's must sum to 1. To summarize, this gives me a problem of the form minimize over x 1/2 times x transpose cx, subject to the constraints m transpose x is greater than or equal to r, and the sum of all xi's must be equal to 1, as well as all the x of i's must be greater than or equal to 0. Now, what's interesting about this example is that we also have an equality constraint, which you haven't seen before. Luckily, it's easy to convert equality constraints into inequality constraints, although we won't discuss how to do that in this class, since it's not particularly relevant for SVMs. What we can see from this problem is that, while the objective is quadratic, the constraints are still linear. And thus, the general form of a quadratic programming problem is a quadratic objective with linear constraints. We can express the general form as minimize over x 1/2 x transpose qx plus c transpose x, subject to the constraint ax is less than or equal to b. One final note about this is, if the matrix Q is positive semi-definite, then the problem is convex, which means it has a global optimum. In the portfolio optimization case, this is true because Q is a covariance matrix. In the SVM case, this is also true, since the matrix is just identity. The final thing I want to talk about in this lecture are examples of standard software packages that solve linear and quadratic optimization problems. Previously, I claimed they exist, but didn't show you what they are. So on these slides, I'm going to share some examples in order to further increase your confidence in the fact that these are well-studied problems. The first package I want to mention is from Google called OR Tools. OR stands for Operations Research. This package implements many standard algorithms that you would learn in an algorithms course, such as shortest path algorithms, min-cost flows, max flows, integer programming, and of course, linear programming. At this point, it does not look like it solves quadratic programming problems. On the other hand, there is MATLAB, which does both linear and quadratic programming. The MATLAB ecosystem is such that on top of the base installation, you can install more library functions on top of that called toolboxes. So for example, you could install a machine learning toolbox or an econometrics toolbox. Of course, there's also the optimization toolbox, which contains linear and quadratic programming. MATLAB is a tool you're probably familiar with if you come from academia, along with Mathematica, which also contains optimization software. Finally, there's the Python library cvxopt, which is a package for convex optimization, and this library also contains solvers for both linear and quadratic programming. By the way, just as a point of interest, if you're in school and you want to study these sorts of problems, then there's probably a class in your computer science department called optimization or convex optimization that covers these exact topics. This was sort of the old school version of machine learning back before machine learning was popular. The burning question you might have at this point is, since we have these very robust and well-engineered libraries for solving quadratic programs, why don't we use them to implement the SVM right away? Well, the goal of showing you some of these libraries was simply so that you know that they exist, and using them to solve the SVM objective is something that is possible to do. Now, possible to do doesn't mean that it's something we should do. This is because someone has already invented a better algorithm for solving our SVM objective, which we will have an entire section for later on in the course. So in the old days, yes, people use standard optimization software to solve this problem, but these days we have better ways of doing this. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to further our description of the linear SVM problem so that it handles more real-world datasets. Previously, we've been looking at two nicely separated clouds of data, which are easy to discriminate with a line. Of course, real-world data never looks like this. We have two problems that we still need to overcome. Problem number one is that the data may not be linearly separable. That's not to say that the data doesn't follow a linear pattern. In this picture, it's clear that trying to get 100% training accuracy would probably lead to overfitting, so a line is still best. However, at the same time, it's not possible to perfectly separate this data with a line, so our quadratic programming solver will fail. And just to be explicit about that, it fails because it cannot meet the inequality constraints of the quadratic program. Problem number two is that the data may be linearly separable, but it may contain outliers. In this picture, I can clearly separate the two clouds, but there's this outlier that pushes the line into an awkward position. It's clear that in this situation also, achieving 100% training accuracy would be overfitting, and so perhaps it would be best to just misclassify this outlying training point. What happens if we achieve 100% training accuracy? Well, it makes the margin with respect to all the other training points much smaller, had this outlier not existed. So is it worth getting a very small margin, just to meet the constraints of the quadratic program? That is the question we'll try to answer in this lecture. Of course, based on our previous discussions, you might recognize that the solution to this problem is regularization. To solve this problem, it's as easy as introducing a new variable called the slack variable. This leads us to what is called the soft margin SVM, meaning that this SVM allows the margin to be violated. In other words, it's still possible to meet the constraints of the problem, even if we misclassify a few data points. To represent the slack variable, we use a new Greek letter called xi. So our quadratic program becomes the minimum over WMB of 1/2 the magnitude of W squared plus C times the sum over all xi i's. And this is subject to the constraints y of I times W transpose x of I plus B is greater than or equal to 1 minus xi I, and that xi I must be greater than or equal to 0. And this is for I from 1 to n. Oh, and by the way, you can see that this is still in the form of a standard quadratic program. As you can see, we have a quadratic objective with linear constraints. As you can see, this new letter xi appears in 3 places. First, let's look at the last one. All the xi's must be greater than or equal to 0. If it's 0, that means data point I is correctly classified, and that data point is either on the margin or further away from the margin. If xi of I is greater than 0, that means the data point I violates the margin. Why is that? Notice I was very careful here. I didn't say that the point is misclassified, because that's not necessarily the case. For example, if xi is 0.5, then the functional margin for data point I will be greater than or equal to 0.5. That means it's allowed to violate the margin, but it's still correctly classified because it's greater than 0. On the other hand, if xi is greater than 1, now the data point can be misclassified because the right-hand side of the constraint can be negative. Finally, let's look at the third place where xi appears, the objective we want to minimize. Remember, xi represents the data points which violate the margin or are misclassified. The more wrong we are, the bigger xi gets. So this is like a misclassification penalty. Of course, we would like to minimize this. On the other hand, we are still trying to minimize the magnitude of W, which was our original objective. This has the dual purpose of not just making the magnitude of W small, but also of making the margins large. You'll notice that I have this number C in front of my misclassification penalty. As you might suspect, this controls the relative strength of the misclassification penalty. In other words, if I care more about misclassification than I do about large margins, I can make C bigger. If I care more about large margins than I do about misclassification, then I can make C smaller. This might remind you a lot of the logistic regression regularized loss, which is great if it does. If you can recognize the similarities between these two, you are on the right track. The loss function for both of these models is the sum of two terms, the misclassification penalty and the large weights penalty. As you can see, the C variable and lambda play opposite roles. If we care more about the misclassification penalty, we increase C but decrease lambda. If we care more about making W smaller, we decrease C but we increase lambda. Another thing I want to mention is that if we go back to the beginner's corner, we actually played around with a parameter called C when we used the scikit-learn implementation of the SVM. Of course, this C and the C we just introduced are one and the same. So now you know exactly what this C hyperparameter represents and how to use it. The last thing I want to mention in this lecture is a funny little paradox. In logistic regression, our cross-entropy loss function ensures that our classification error is small, and the W squared term is our regularization penalty. Yet, in SVM, it appears that minimizing W squared is what gives us our large margins, and when we don't include regularization in our model, only this W squared term appears in our objective. Only when we do introduce regularization do we get this additional misclassification penalty. This seems paradoxical because in the logistic regression case, regularization is performed by minimizing W squared, whereas in the SVM case, regularization is performed by minimizing the misclassification penalty. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to further explore the relationship between SVM and logistic regression. For this lecture specifically, we'll be focusing on the loss function. Let's start with the logistic regression loss. In order to do this analysis, we only need to consider the loss for a single training sample. As you recall, the logistic regression loss is equal to the negative of y times the log of sigma of W transpose x plus 1 minus y times the log of 1 minus sigma of W transpose x. Now here I've explicitly used the term W transpose x, since this is the term that appears in both classifiers. Also, note that I've excluded the bias term here for simplicity's sake. The next thing you'll want to think about is, only one of these terms matters for any single training example. When y equals 1, only the first term matters, and when y equals 0, only the second term matters. For simplicity's sake, let's just look at the case for when the target is 1. If we plot the loss as a function of W transpose X, here is the plot we see. It's sort of like a hockey stick shape. Okay, so that's as far as we need to go for logistic regression. Just keep this picture in mind. Now let's turn our attention over to the SVM. For the SVM, our misclassification penalty appears as xi. Xi is either 0 or a number bigger than 0. Let's recall our equation for the constraint. Y times W transpose X is greater than or equal to 1 minus xi. Again, I've removed the superscript I and the bias term B to keep things simple. Now, if we think about this, the term Y times W transpose X is not actually going to be greater than 1. Because if it were, then the data point would be correctly classified and would satisfy the margin, and there would be no need for xi to be greater than 0. If you recall, our objective is simultaneously minimizing xi while also trying to meet this constraint. So if Y times W transpose X is already greater than 1, then the minimizer will automatically make xi equal to 0. So the only time when xi is actually positive is when this data point violates the margin, in which case we can assume that instead of this inequality, we have an equality. So let's say Y times W transpose X is equal to 1 minus xi. We can rearrange this to get xi equals 1 minus Y times W transpose X. Now remember, Y times W transpose X is not greater than 1 here, otherwise xi is just 0. So xi can never be negative. In fact, we can encapsulate these two conditions into one equation. We can say xi is equal to the max of 0 and 1 minus Y times W transpose X. Let's now plot this loss with respect to W transpose X. Interesting, it looks very similar to the logistic regression loss, except that it has a sharp corner at 0. Of course, you might wonder what would happen if we were to plot these losses superimposed on one another. And of course, it looks like we might expect, very similar. The SVM loss appears to be a coarse approximation of the logistic loss, and the logistic loss a smooth differentiable version of the SVM loss. In machine learning literature, we refer to the SVM loss as the hinge loss. At this point in our studies, it's nice to compare all of the different classification losses we've encountered so far. In fact, the study of these different loss functions is a typical part of theoretical machine learning. In this course, it's just interesting to name them and remind ourselves of which algorithms they correspond with. So of course, the two easy ones, which we just discussed, are the logistic loss for logistic regression and the hinge loss for the SVM. We've also seen the exponential loss before in our study of Eta Boost. We've seen the 0-1 loss before in our study of the perceptron. If we take the mean of the 0-1 loss, we of course just get the error rate of our classifier. Sometimes you might also see the squared loss included as a part of this plot, which makes it clear why it's not a good loss for classification. If you notice, the pattern for all the correct losses is that they decrease or go down to 0 on the right side. However, this is not the case for the squared loss, which actually increases the more you go to the right. So this provides even further justification for why the squared loss is no good for classification. And I think one last interesting point of discussion regarding the perceptron in relation to the SVM is this. If you've never studied the perceptron, then don't worry, since this is not crucial for this course, but if you have, then this is nice to know. If you recall, the perceptron algorithm is such that the weight is only modified so long as the misclassification error is not 0. Once we've moved the line enough so that all the points are classified correctly, we can quit. Of course, this can easily lead to a non-optimal line, which gets 100% training accuracy, but is really only just good enough. This also helps to explain why the SVM generally works better and is more robust. Instead of just finding any correct line, It tries to find the best correct line. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to use an alternative method for solving the linear SVM. It's a method we are all familiar with by now, gradient descent. Earlier, I told you that gradient descent was impossible because we have to solve a quadratic program with constraints. But when we introduced slack variables, we were given more freedom to violate the constraints, and so gradient descent becomes a viable option. This lecture is a quick tutorial to go over what you need to write this implementation for yourself. As you know, the functions we would like to implement are fit and predict. The predict function should be very simple, since it's essentially the same as what you would see in linear regression and logistic regression and neural networks, just the usual linear equation, x.w plus b. In the fit function, we'll have our gradient descent loop, and at the end of it, we should have the optimal values of w and b saved as attributes of the object for later use. In order to do gradient descent, we'll need a loss function. Luckily, we just derived that. So it's 1/2 of w transpose w plus c, the misclassification penalty, times the sum from I from 1 to n of the max of 0 and 1 minus yi times w transpose xi plus b. As you can see, if our misclassification error becomes non-zero, it doesn't violate any constraints since it simply means that xi would be greater than 0. Now, I'm not going to derive the gradient with too many steps, since this is just a linear equation, but you should be able to arrive at this result by yourself on paper. If not, you can always ask about it on the Q&A. One thing that's important to notice about these gradients is that the summation index does not go from 1 to n. This is because for any correctly classified samples, the loss is 0, and the slope at that point is also 0. So those do not contribute to the gradient. Only points which are misclassified, or more correctly, violate the margin, contribute to the gradient, so we only sum over the i's for which xi of I is greater than 0. As usual, you'll want to output useful information, such as the loss per iteration, but other than that, this is all you really need to begin your implementation. We'll be going over some other useful visualizations, such as plotting the decision boundary, margin lines, and so forth, but that's not necessary for your first try. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to look at the implementation for a linear SVM trained with gradient descent. The relevant file for this lecture is linear_svm_gradient.py. At the top, we have all our usual imports. We're going to use the breast cancer dataset since it's mostly linearly separable, as well as some Gaussian clouds, since we would like to visualize what the classifier is doing. The first thing we implement in this file is the linear SVM class. In the constructor, we just save the misclassification penalty c. Next, we have a function for calculating the objective. As you can see, it takes in a variable called margins, which is just y multiplied by the SVM output. Unfortunately, the term margins is overloaded when we're talking about the SVM, so it's always good to keep in mind which margin we mean when we say margin. Next, we have the fit function. It takes in the training data, x and y, and the learning rate, as well as the number of iterations of gradient descent to do. The first thing we do in this function is randomly initialize the weights and set the bias term to 0. Next, we enter the gradient descent loop. The first thing we do inside the loop is calculate the margins. As you recall, these are the functional margins. Next, we pass in the margins into our objective function and save the loss for plotting when we're done. Next, we grab the indices for any margins which are less than 1. Remember, these are data points which violate the SVM's margin lines. The next step is to actually perform the gradient descent step. So we calculate the gradient for W and then update W, and then we calculate the gradient for B and then update B. You should be able to verify that this code implements the equations we derived in the previous lecture. When we're finished the gradient descent loop, we'd like to save the indices for any data points which lie on the margin or violate the margin. The reason we want to save it as an attribute called support is because scikit-learn does the same thing. So we're just being consistent with that interface. Lastly, we plot the loss per iteration and then return from the fit function. Next, we have a function called decision function, which just implements the linear equation for the SVM. We have the predict function, which applies the sign function to the decision function. And finally, we have the score function, which returns the classifier's accuracy on the data that you pass in. Next, we have a function called plot decision boundary, which will plot our data points along with the separating line and margins. The details of this function are not critical for you to know, so you can ignore it. But if you have any questions about how it works, I would be happy to answer them on the Q&A. Next, we have two dataset functions, which are going to return the data, split into train and test, as well as reasonable hyperparameter settings. So in this example, we are interested in the cloud data and the medical data. For the medical data, it's more than 2 dimensions, so we won't be able to visualize it. For the cloud data, we will be able to visualize it, so perhaps that will be more useful to us in this lecture. Lastly, we have the main section. This is more or less just the same kind of code you saw in the beginner's corner. First, we load in the data, then we make sure the targets are -1 and +1 so that they work with our SVM. Then we create a model, call the fit function, and call the score function on both the train and test sets. Finally, we check the dimensionality of the data, and if it's 2, which means we can visualize it, then we call plot decision boundary. So let's run this and see what we get. Alright, so this is the value of W and B that we find. This is the loss per iteration. And this is a plot of the decision boundary along with the margin lines. And of course, our score is pretty good. Hey everyone, and welcome back to this class. Support vector machines in Python. In this lecture, we are going to summarize and conclude everything we learned in this section. This section was all about the linear SVM. I hope that at this point you understand how the logistic regression review tied into everything you learned here. When we talked about logistic regression, we focused on the specific parts that are interesting for us when we study the SVM. First, we reviewed the equation for a hyperplane. This is the typical linear equation you see everywhere, from linear regression to neural networks. We noted that the weight vector is perpendicular to the plane, a fact that became important for us in this next section. We looked at the idea that logistic regression wants its weights to have infinite magnitude, which minimizes the loss and increases the model's confidence in its training predictions. But we also know that infinite magnitude weights are no good, so we introduced regularization. Finally, we saw that another way to increase prediction confidence would be to position the hyperplane so that it is far away from the training points. These facts all became useful when it came time to study the linear SVM. In this section, we saw how the SVM handles these issues. We started with the picture where the data is perfectly separable using a hyperplane. This is the usual picture for linear classification, and it helps us to develop both the theory and intuition for the linear SVM. We introduced the idea that the SVM is a maximum margin classifier, and we looked at exactly how to define margins. We learned that there are two types of margins, the functional margin and the geometric margin. Functional margins are dependent on the magnitude of the weights, whereas geometric margins are independent of the magnitude of the weights because they represent actual geometric distance in space. Importantly, we learned that in order to build a maximum margin classifier, we had to build up an objective that had not only a term to minimize, but also some inequality constraints. This doesn't look like our usual objectives that we have for linear regression, logistic regression, or neural networks. And so we couldn't use conventional methods such as gradient descent. Instead, we had to employ the optimization method known as quadratic programming. Luckily, we don't need to know the algorithms for how to solve quadratic programs, since they don't really belong in a class about machine learning, any more than algorithms for how to invert a matrix would. Once we established the basic theory behind the linear SVM, we reintroduced the idea that some points might be misclassified. This is the most realistic scenario, so it's necessary in order to build anything that is of practical use. This led us to the idea of slack variables, which gave us the soft margin SVM. In a way, the allowance for misclassified examples acted as regularization. This was sort of the opposite picture compared to logistic regression, where minimizing the magnitude of the weights is the regularizer. At the same time, it gave us something very similar to logistic regression, where the objective became the sum of our two usual terms, the misclassification penalty and the large weights penalty. Finally, we discovered that the loss function for the SVM looks like a piecewise approximation to the logistic loss, and it is called the hinge loss. We also reviewed some other loss functions for other classifiers and looked at their commonalities and differences. In the next section of the course, we'll take our first step into the theory that allows us to convert the linear SVM into a nonlinear SVM. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this section of the course, we are going to take our first steps into the theory that helps us transform the linear SVM into a nonlinear SVM. Interestingly, this is actually a lot of heavy theory, and by the end of it, we still won't have a nonlinear SVM. So in some way, this section is also a test of your patience and grit. To give you a rough sketch of what we're trying to do, the problem we've been dealing with so far is called the primal problem. In optimization, what we can often do is convert our primal problem into what is called the dual problem. This is a related problem, but also a totally different problem, which results in a different set of variables to optimize. You can think of it in terms of these two curves. If the primal problem is a minimization problem, it has a solution P star. Then the dual problem will be a maximization problem, and it will have a solution D star. What we're interested in is under what conditions will the solution to both problems be the same. In other words, what we're trying to do is reframe our problem so that if we solve either of these problems, they both give us the same answer. Now, this might seem very strange, but you can imagine it in practical terms. Pretend that the primal problem is very hard to solve computationally. Let's say it takes 10 hours to solve. On the other hand, the dual problem only takes 10 minutes to solve. Of course, we would like to solve the problem in 10 minutes instead of 10 hours. By the way, this type of paradigm exists for all types of programs, including linear programs and quadratic programs. If you're uncomfortable with this type of thing, then linear programming is a much more popular topic than quadratic programming. And as such, you're more likely to find examples on the internet for linear programming duality as opposed to quadratic programming. So you can increase your comfort level by looking up more examples and increasing your familiarity with these types of problems. So if you think that will help your intuition, then you're encouraged to do a search and find some examples of linear programs and their duals. Now, by the end of this section, you'll probably be very tired of quadratic programs and trying to manipulate them mathematically, but we'll also have arrived somewhere very useful. In particular, we'll be able to express our quadratic program in an entirely different format. This allows us to make several important insights. First, we'll learn what we mean by support vectors, which is, of course, how this classifier, the support vector machine, gets its name. Second, we'll see how both the training phase and prediction phase of the SVM can be completely expressed in terms of dot products only. This might seem trivial now, but it's an important feature that allows us to transform the SVM into a nonlinear classification machine. As a side note, in this section we will again assume that we are working with linearly separable data. In the next section, we'll reintroduce slack variables and hence allow for regularization. But this is not necessary to develop the theory in this current section. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss the concept of duality, which is going to set us up for the next topic, which is how to apply SVMs to nonlinear problems. When we're talking about linear programming, quadratic programming, and other types of optimization problems, there's this concept of duality. What we've been working with so far is called the primal problem. In its canonical form, we have some objective that we want to minimize. Generally, we are able to convert this into another problem called the dual problem. In its canonical form, the new objective for the dual problem is something we want to maximize. Note that this is not the same as simply flipping the sign of the objective. In our transformation from the primal problem to the dual problem, we're going to create an entirely new objective with entirely new constraints and add a few more variables as well. In this lecture, I want to give you just a rough outline on how this works. Understanding this is somewhat optional in terms of the overall flow of this course, but the most important thing is to understand the result. Alright, so here's a rough sketch for how this works. You can imagine the primal problem as trying to find the minimum of this curve here. Let's say that the solution, the minimum value, is p star. Now let's say we're able to construct the dual problem, which we represent by the bottom curve. Let's say the solution, the maximum value, is d star. As you can see, there may be some space between p star and d star. We call this the duality gap. What we would like to know is, under what conditions is d star equal to p star? Let's now take a deeper look into what these conditions are. But first, as a warm-up, we're going to take a digression into Lagrange multipliers, which you may have studied in your undergraduate calculus class. You will see the similarity between a Lagrange optimization problem and the quadratic program we've been working with for SVM. In its simplest form, Lagrange multipliers are used to solve problems of the form max of fxy subject to the constraint g of xy equals 0. We want to maximize some function f with respect to x and y. But we also have some constraints, which are expressed as another function g, also of x and y, and that function is equal to 0. To solve this problem, let's first consider this picture. As you can see, the function f of x and y represents a surface. Of course, if we didn't have the constraint, we could just solve this problem using conventional calculus methods by setting the gradient of f of xy to 0 and solving for x and y. But now, we do have a constraint given by the function g of x and y. As you can see, it is represented by this red curve. In other words, the only solutions allowed by the constraint are the points x and y, which lie along the red curve. That explains why we can't use the maximum on the surface, which you see here. That is not on the red curve. So we want to find the point along the red curve for which f is maximum. By the way, the blue dotted lines here represent contours of the function f. Contours are where the value of f doesn't change. So what we can tell from this picture is that the solution seems to be the point where f and g are both parallel. Let's use this intuition, that f and g must be parallel, to make sense of the solution that Lagrange multipliers gives us. So the way that Lagrange multipliers works is that we're going to introduce a new variable lambda, appropriately called the Lagrange multiplier. Now we're going to set up a function L, which is called the Lagrangian. It's equal to f minus lambda times g. The solution to this problem consists of the values x, y, and lambda that satisfy the gradient of L being equal to 0. The question is, why does this make sense? Well, if we take the gradient in terms of f and g, we get that the gradient of f equals to lambda times the gradient of g. And of course, this matches our intuition that f and g are parallel at some optimal point. In other words, since f and g are both pointing in the same direction, that means their gradients are parallel. Note that while they point in the same direction, they don't necessarily have the same magnitude, which is why the gradient of g is scaled by lambda, the Lagrange multiplier. Finally, note that taking the gradient of L with respect to lambda simply yields g of xy equals 0, which was our original constraint. At this point, it might seem like all these symbols are really flashy and make the problem seem very abstract, but this is really just a simple type of problem that you'd find in your calculus homework. Basically, for the problem above, it boils down to having 3 equations and 3 unknowns, x, y, and lambda, which you can use just basic algebra to solve. The gradient with respect to x gives us one equation, the gradient with respect to y gives us another equation, and the gradient with respect to lambda gives us the third equation. Let's do a simple example to drive the point home. Suppose we want to maximize the function f of xy equals x plus y, subject to the constraint g of xy equals x squared plus y squared minus 1 equals 0. Of course, this means we want to maximize the height of a plane, subject to the constraint that the points on the plane, which we are interested in, must lie on the unit circle. So the first step to solving this problem is to set up our Lagrangian. L equals x plus y minus lambda times x squared plus y squared minus 1. The next step is to take the derivative of the Lagrangian with respect to our 3 parameters, x, y, and lambda. This gives us 3 equations and 3 unknowns. Finally, we can solve for x, y, and lambda to get x equals the square root of 2 over 2, y equals the square root of 2 over 2, and lambda equals the square root of 2 over 2. This gives us a maximum value of f of xy equals the square root of 2. So that was pretty simple. We solved this problem in just 3 steps. Alright, so I hope that satisfied your curiosity behind Lagrangians. What we're going to do next is discuss more sophisticated forms of the Lagrange multiplier method. To generalize what we just did, we can think of it in the following form. First, we had an objective, f of x, which we wanted to maximize or minimize. Now you can think of x as a vector containing an arbitrary number of components. We also have a function g of x equals 0, which specifies our constraints. We set up a Lagrangian, L, equals f of x minus lambda times g of x, where we introduce lambda as our Lagrange multiplier. Finally, we take the gradient of L, set it to 0, and solve for x and lambda. In this scenario, if the vector x has length d, then we end up with d plus 1 equations and d plus 1 unknowns. The next step to making this more sophisticated is to consider the scenario where we have multiple constraints. So suppose x is a vector of length d, and we have n constraints. So g1 of x equals 0, g2 of x equals 0, all the way up to gn of x equals 0. In this case, we need to introduce n new Lagrange multipliers, and our Lagrangian takes the form f of x minus the sum of I from 1 to n, lambda I times g of I. Luckily, the solution to the problem doesn't change. We still take the gradient of L and set it to 0 and solve for all the x's and all the lambdas. In this scenario, we have d plus n equations and d plus n unknowns. Our last step in making this problem more sophisticated is to consider the scenario where we not only have equality constraints, but inequality constraints as well. This problem is posed as follows. We would like to maximize f of x subject to the constraints gi of x is less than or equal to 0 for all I from 1 to n, and hj of x is equal to 0 for all j from 1 to m. In this scenario, we create two sets of Lagrange multipliers, a set of alphas for the inequality constraints and lambdas for the equality constraints. This gives us a new Lagrangian with two summation terms, one over the g's and one over the h's. We'll use the Lagrange multiplier alpha for the g's and lambda for the h's. The problem now is, because we have inequality constraints, it's not clear what conditions we have to meet in order to find the solution. Before, we just had to find the gradient of L and set it to 0. Now that we have inequality constraints, this is no longer the case. At the same time, taking the gradient of L and setting it to 0 is still one of the conditions. It's just that now we're going to have a few more conditions. Analogously to before, we want the gradient of f to be equal to the weighted sum of the gradients of all the g's and h's. As a side note, if we wanted to minimize f of x, we simply add a negative sign to the gradient of f to this condition. And one important note about this is that the gradients are only taken with respect to x and the lambdas, so the original variables and the Lagrange multipliers for the equality constraints. For the alphas, which correspond to the inequality constraints, we do something different. In particular, we have a new set of conditions that alpha I times g of I must equal to 0. We also have that g of I is less than or equal to 0, which was just our original inequality constraints. And finally, that all of the alpha i's must be greater than or equal to 0. In total, these are called the KKT conditions, and the values of x, alpha, and lambda, which satisfy these conditions, are the solution to the problem. These conditions are analogous to the basic gradient conditions when we only had equality constraints. So to put this in a more general format, what we have is a function f of x, which we want to maximize or minimize. Then we have a set of constraints, which can be equality or inequality constraints. Finally, we have a set of conditions, which tell us what equations we have to solve in order to arrive at the solution. For equality constraints only, we just have the basic condition that the gradient of the Lagrangian must be 0. For inequality constraints, we have to solve for the KKT conditions. As a final note, these KKT conditions are exactly the conditions we need to ensure that the solution to the primal problem and the dual problem are the same, which is what we were discussing at the beginning of this lecture. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to apply this concept of Lagrangian duality to our SVM objective, and we'll see how all the crazy math we discussed actually becomes useful to us. We'll see how to apply the KKT conditions in order to transform our SVM primal problem into its corresponding dual. As usual, we're going to start with our primal problem, but this time, we're going to make it look a little more like our SVM objective. We would like to minimize f of w and b subject to the constraints gi of w and b is less than or equal to 0 for all I from 1 to n. Remember, we don't have any equality constraints for the SVM, so luckily we can leave those out. The question is, what is f and what is g? Well, f, as we know, is our original objective, just the squared magnitude of w. By the way, remember that we're going to assume that, for now, our problem is again linearly separable, so that we don't have to deal with slack variables. And g of w and b is just the inequality constraints we had before, but rearranged so that we have 0 on the right-hand side, and that we have a less than sign. Putting this all together, our Lagrangian becomes 1/2 of the magnitude of w squared plus the sum from I from 1 to n of alpha I times 1 minus y of I times w transpose x of I plus b. The next step is to solve the KKT conditions. Again, I just want to remind you that all of this is optional. So if you find all this math to be a big headache, remember that all we need is the solution. So this derivation is only for those who are interested in how we arrived at the solution. This is all just going to be a bunch of mechanical work. So the first thing we're going to do is take the gradient of L with respect to w and set it to 0. That gives us w minus the sum from I from 1 to n of alpha I times y of I times x of I equals 0. In this simple form, it's easy to solve for w, which gives us that w is just equal to the sum of alpha I times y of I times x of I. Next, we're going to take the derivative of L with respect to b and set it to 0. This is going to give us a linear constraint on alpha. So it tells us that the sum of alpha I times y of I must equal 0. There's nothing we can really do with this right now, so let's just save it for later. Next, let's see what happens if we plug in our solution for w back into the Lagrangian. First, let's rearrange the original equation a little bit by separating out the term involving alpha. We can also move the w and the b outside the summations because they don't depend on I. Of course, we can see right away that the last term, where b appears, is equal to 0 due to one of the KKT conditions we derived earlier. So now this just becomes 1/2 w squared plus the sum of alpha I minus w transpose times the sum from I from 1 to n of alpha I times y of I times x of I. The next step is to realize that in the final term, according to the KKT conditions, we just have w dotted with itself. And so we can combine this with the first w squared term, since that is also equal to w dotted with itself. And we end up with just the sum over all the alpha i's minus 1/2 w transpose w. So pretty simple expression. Finally, the last thing we need to do is plug in the expression for w in terms of alpha. Keep in mind, since w is already a summation, what we end up with is a nested summation. And so in this situation, we need to make use of another index other than I for the inner summation so that we don't get the two indices confused. For this, we're going to use the letter j. Now I want you to notice two things here. First, we've completely gotten rid of all our original parameters, w and b. We're left only with this new variable alpha. Second, what have we found here? Well, in fact, we have found the dual problem. Let's state the dual problem explicitly. we would like to maximize over alpha the sum of all the individual alphas minus 1/2 times the sum over I and the sum over j, alpha I times alpha j times y of I times y of j times x of I transpose x of j. And this is subject to the constraints that alpha must be greater than 0 and the sum of all the alpha i's times the y of i's must equal to 0. As a final step, let's relate this back to our original picture of the primal and dual problem. We can think of this as having some Lagrangian, L of w and b and alpha. For the primal problem, we find the solution p star by taking the max over alpha and then the min over w and b. In other words, you can think of it as the problem is already solved for alpha, we just need to find w and b. For the dual problem, we reverse the order of the min and the max. In this problem, we first minimize with respect to w and b, and then we maximize over alpha. In other words, you can think of it as the problem is already solved for w and b, we just need to find alpha. This explains why p star is always greater than or equal to d star. It's because the min max is always greater than or equal to the max min. And we can ensure that they are exactly equal by making sure that the KKT conditions are satisfied. Hey everyone, and welcome back to this class, Support Vector Machines in Python. Sometimes I think it's nice to look at simpler but similar problems, so you get more comfortable with the things we're doing, even though they might initially seem complex. This idea of duality is probably new to you, and so I think it's very helpful to see the same process being done on a simpler problem, namely a linear program. In linear programming, finding the dual is much simpler. It's just a matter of plugging into these handy formulas, which you can see here. In particular, for a given primal problem, maximize C transpose X subject to the constraint AX is less than or equal to B. The corresponding dual problem with respect to the new vector y is to minimize B transpose Y subject to the constraint A transpose Y equals C and Y is greater than or equal to 0. So if we were dealing with linear programs, all we'd have to do is plug and chug into this formula. By the way, I got this from the Wikipedia page on linear programming, so you guys know I didn't just make this up. And if you want to see an example of a word problem of a linear program, as well as its dual interpretation, you can check that out on this same Wikipedia page. I don't find it particularly useful for understanding SVMs, but it's there if you want to read it. In this lecture, we're going to use our knowledge of Lagrangians and the KKT conditions to derive this rule ourselves. The first step is, as usual, to form the Lagrangian. We're going to call the Lagrangian multipliers y for obvious reasons. As with the SVM problem, we only have inequality constraints, so we'll only have one set of Lagrange multipliers. Since we know that the second term is just the summation over I, over all the individual constraints, we can use our knowledge of dot products to express that as a dot product from the start. So y transpose AX minus B. The next step is, of course, to apply the KKT conditions. The first condition is that the gradient of L with respect to x must be 0. So let's calculate that. We get C minus y transpose A all transposed is equal to 0. Using this, it's easy to arrive at a constraint for y. We get that A transpose y must equal C. Also, the other constraint, that y must be greater than or equal to 0, is just one of the KKT conditions. The last thing we need to do is find the dual objective. To do this, let's try to replace the y term in the Lagrangian with what we just found. It's simpler if we express the second dot product in reverse, which readily gives us A transpose. And if we multiply out the dot product, we get x transpose A transpose y. But we already know that A transpose y equals C because we just solved for that. So once we do that, we see C transpose X minus X transpose C, which is just 0 because the dot product is commutative. What we're left with is an expression that contains only the Lagrange multiplier y, which is weird because we just tried to replace the y. But in any case, this is just like with the SVM, where we have found our dual objective, something that only depends on the new variable y. Putting it all together, we have derived a plug-and-play formula for how to convert a linear program primal problem into its corresponding dual. This gives us back the same formula that we observed on the Wikipedia page on linear programming. The steps we had to perform were simply to satisfy the KKT conditions, which are exactly the same steps we performed to derive the SVM dual. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to wrap up our discussion about duality, talk about how our model will make predictions, and also what the name Support Vector Machine really means. First, let's start talking about how, once we've solved the dual problem, we can use the solution to make predictions with our model. You probably noticed that with the dual problem, our goal was to solve for alpha, yet our model is in the form of W transpose X plus B. This means we need to somehow find W and B. Luckily, we found W already, simply by trying to satisfy the KKT conditions. We got that W is the weighted sum of X times Y, where the weight is alpha. Now, this seems pretty simple, but in fact, we can simplify this equation a little bit, as you will see later. Let's now turn our attention to the bias term B. You may have noticed something weird. For W, the way we found it was simply by taking the gradient of the Lagrangian with respect to W and then solving for W. But when we take the gradient of the Lagrangian with respect to B, B disappears. So we can't use that equation to solve for B. What we can do, however, is use the equations for the margin, which we already have. Let's see what I mean by that. To do this, we need to turn our attention to the KKT conditions again. You'll notice that the final three conditions involve only alpha and G, the original constraints. Let's look at the first one. Alpha times the corresponding G must equal to 0. If that's the case, then at least one of these must be 0. Now let's look at the second equation. G must be less than or equal to 0. When is it less than 0 and when is it equal to 0? Well, let's recall what G actually is. It's 1 minus the functional margin. Remember, the functional margin is either bigger than 1 if it lies beyond the margin, or it's equal to 1 if it lies right on the margin line. So if data point I lies right on the margin line, then G is equal to 0. Otherwise, G is negative. What is the significance of G being 0? Well, when G is 0, that means we can make alpha bigger than 0 and still meet the KKT conditions, in particular constraint number 1. Alpha is allowed to be greater than 0 because in that case, all the constraints are still satisfied. But alpha being greater than 0 might improve the dual objective, which is how we can end up with alpha is greater than 0. Now, that might be a complicated series of steps to follow, but we can summarize the result. You're encouraged to think about it more on your own if it doesn't make sense to you right away. The result is that alpha is only greater than 0 for the data points which lie directly on the margin line. Any points outside the margin have an alpha equal to 0 in order to satisfy the KKT conditions. And so this is the big reveal for where the support vector machine gets its name. These vectors which lie on the margin are called support vectors. You can think of them as holding up or supporting the margin. They are the only vectors for which the corresponding alpha is greater than 0. And so using this, we can simplify our equation for w a little bit. Instead of summing over all values of I from 1 up to n, we instead only have to take the sum over the values of I, which correspond to the support vectors. Why is this relevant? Well, first of all, it's faster. Summing up less values is faster than summing up more values. But this insight is more important than that. It tells us that in order to find the separating hyperplane, most of the data points didn't even matter. The weight vector actually depends only on a very small subset of the data. These support vectors are also sometimes called exemplars or landmarks. In other words, they are very important because they completely determine the classification rule. Furthermore, we can use these facts to find B. We know that these support vectors lie on the margin. So if we have a positive training point on the margin, we would have W transpose X plus B is equal to 1. Alternatively, if we have a negative training point on the margin, we would have W transpose X minus plus B equals minus 1. Of course, we can just combine these together to get Y of I times W transpose X of I plus B equals 1, where I is an index that corresponds to the support vectors. Using this, it's simple to rearrange the equation in terms of B. We get B is equal to Y of I minus W transpose X of I for any I which belongs to a support vector. Now, theoretically, you could just choose any support vector and this should give you the same answer, but in practice, it doesn't work that way. So what we would normally do is calculate multiple versions of this B and then take the average. What is interesting is, at this point, we can express our entire problem without W at all and instead only use alpha. Our objective is expressed in terms of only alpha, and hence, our quadratic program needs only to find alpha. Furthermore, we can make predictions using only alpha as well, and of course B, the bias term, which as you've seen, is calculated using only the training data and the alphas, since that gives us knowledge about which data points are support vectors. So ultimately, in order to make a prediction, we really only need the training data and the alphas as well. At first, this might seem strange to you, since obviously it would be easier to just calculate W and B and then use them as constants. Why should you do this sum every time you want to make a prediction when you don't have to? In the next lecture, I'll give you some hints as to why we might want to do this. The last thing I want to talk about in this lecture is just to connect this back to the real world and step back from the math a little bit. Although we still have a lot of theory to develop before moving on to the implementation, it's still a good exercise to think about how one might implement a linear SVM. At this point, we can conceptualize both steps we need to implement a supervised machine learning classifier. As you know, the two functions we are interested in are fit and predict. First, we would import some function that solves quadratic programs from our favorite optimization library. In this pseudocode, I'm calling that qpsolve, which comes from the library awesome_qplib. In the fit function, our job is to find the alphas in the bias term. So we just call qpsolve and then plug in x and y to get our alphas, from which we can calculate W and then calculate B. For reasons that are not clear to you yet, we don't actually want to calculate the weight vector, but rather just store the alphas for later. Also remember that we want to save x and y as our training data. If you've studied other machine learning algorithms before, this should remind you of k-nearest neighbor, which is one of the few other algorithms that also do the same thing. In the predict function, all we need to do is x.w plus b, or the equivalent, x dot x train times y train times the alphas, summing over axis equals 1 plus b. And so that's why we wanted to save x train and y train so that we could use it again in the predict function. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, I'm going to give you some hints about why we might want to transform the primal problem into the dual problem, and we'll fully flesh this out in the next section. At first, you might consider this very strange. We know that the primal problem contains computations which are dependent on D, the feature dimensionality. On the other hand, the dual problem contains computations which are dependent on n, which is the number of samples. And typically, n is much bigger than d, because we would like to have a lot more samples than input features. So it seems this only makes our computations worse. W transpose x plus b clearly looks a lot simpler than summing over all the alphas from 1 to n. At the same time, we haven't considered one thing: feature transformations. Earlier in the course, we saw that feature transformations can potentially blow up the feature dimensionality. I told you earlier that SVM can handle this elegantly, and now we are close to finding out how. For now, it seems intuitive that if our computations depend only on n, then we might be free to increase d as much as we want. Another thing to keep in mind is that when we're making predictions, the computation is a lot faster than it appears. Even though we technically have a sum from 1 to n, we know that most of these alphas will just be 0. Typically, the number of support vectors is very small compared to the size of the training set. At the same time, I want you to be aware that this is the type of thing you'd read in a theory book. So yes, the number of support vectors will be small, and most of the alphas will be 0, making the summation in the prediction not so bad. But in practice, does prediction take a long time, relative to, say, using a neural network? And the answer is yes. We saw that earlier in this course. The final thing I want to talk about in this lecture, which will lead us into the next section, is how we can express the dot products that appear in our quadratic program and in our predictions. By the way, you can think of the quadratic program as our training phase and the predictions as our prediction phase. These are, of course, the two functions we care about implementing for any supervised machine learning model: fit and predict. What you'll notice is that, in both these cases, the input vector x never appears by itself. It only appears as a dot product. If you've ever studied higher level mathematics or maybe quantum physics, then you'll be familiar with the inner product notation, where we use angle brackets rather than the transpose in order to denote the dot product. This seems like a minor notation change, but it also clues us into the fact that perhaps this dot product need not be a dot product at all. Perhaps we could replace it with some other function. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to summarize everything we learned in this section. This section was all about applying the concept of duality in order to find an alternative quadratic program for our SVM classifier. First, we had to review Lagrange multipliers. We imagine a Lagrange multiplier problem in 3 steps. The first step is to state the objective along with the constraints. The second step is to add the Lagrange multipliers to form the Lagrangian. The third step is to use the Lagrangian to meet a specific set of conditions. This gives us a set of equations to solve, from which we can find the values of the variables that optimize the original objective. In our case, those conditions are the KKT conditions. The KKT conditions are the conditions that must be met so that the solution for the primal problem is equal to the solution for the dual problem. The next step was to apply the KKT conditions to our SVM objective. From this, we were able to discover something important. The dual problem, which is of course also a quadratic program, involves only the dot product between each input vector x. This corresponds to the training phase of the SVM. Furthermore, the prediction phase of the SVM also only depends on the dot product, this time between the input vector and each of the training vectors. This fact will become very important in the next section when we discuss kernel methods. This is what allows our SVM to become a nonlinear classifier. Finally, we learned the meaning of the term support vector machine. The support vectors are simply vectors that lie on the margin. We remarked that, even though theoretically we will only have a few support vectors in relation to the size of the training set, it still seems like a computationally expensive thing to do, to make both training and prediction depend on n. In fact, we saw the consequences of that earlier in this course, when we tried to use the SVM on the MNIST dataset. At the same time, this allows us to do something very powerful, which is explode the number of feature dimensions. This might be something we want to do when we want to build a nonlinear classifier. This is what we'll discuss in depth in the next section. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this next section of the course, we are going to build off of what we learned in the last section on duality to create a nonlinear SVM. In this lecture, we are going to introduce this section and outline how this is done. The key component we learned in the previous section was that both steps of the model, training and classification, can be expressed only in terms of dot products between the input features. Earlier in the course, we learned about feature expansions. By doing feature expansions, we're able to apply linear classifiers to nonlinear problems. For example, we can use logistic regression to solve the XOR donut. We can think of normal logistic regression as just fitting x and y while predicting on x. We can think of a polynomial expansion as, instead of passing in x directly, we first transform it using some feature transformer called phi. With SVM, since it would only use dot products of the feature vector with itself, what we can do is simply replace the dot product with some other function called a kernel. Typically, the kernel is more efficient to compute than actually transforming the input into a different feature vector and then taking the dot product. So of course this is only advantageous if you have a kernel function that is actually more efficient. In other words, in order for this process to be actually worth doing in the first place, the kernel has to be more efficient to compute. In some cases, actually calculating the feature transformation can be impossible to compute. Once we've chosen our kernel and hence chosen our feature expansion, we can express both the training phase and the prediction phase only in terms of this kernel. Notice again how x never appears in isolation. The basic facts of the problem haven't changed. Training still simply involves passing in our quadratic program into a standard software solver, and predictions are still just a few dot products and additions. It's just that now, the kernel provides us with an opportunity to be more efficient. After introducing the kernel trick, we are going to discuss a few common kernels. In particular, we'll discuss the polynomial kernel, which efficiently implements feature expansions like the ones you saw earlier in the course, as well as the Gaussian kernel. The Gaussian kernel is very important because it's almost synonymous with SVMs. It's most often the default choice, and so it's important to understand why it works and how to use it. We'll also prove that the Gaussian kernel corresponds to an infinite dimensional feature expansion. After that, we'll also discuss the sigmoid kernel, which makes our SVM very close to a neural network. and one example of a string kernel, which is common for NLP and bioinformatics. To close this section, we'll look at Mercer's condition, which is essentially a test which will tell you whether or not a function you chose for the kernel is actually a valid kernel or not. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to describe what is commonly known as the kernel trick. By applying the kernel trick, we can transform our linear SVM into a nonlinear SVM. The success of this trick depends on a result that we derived in the previous section of the course. In particular, that the entire model, both the training and prediction phases, can be expressed only in terms of inner products of the feature vector x. The actual feature vector x never appears by itself in isolation. Let's step back for a moment and go back to feature transformations, a topic we discussed in our logistic regression review. What we saw was that, in order to solve nonlinear problems, what we might like to do is derive new features from the original features. So for example, if we have the inputs x1 and x2, we could add x1 squared, x2 squared, and x1, x2. This would correspond to a degree 2 polynomial feature expansion. And just to make this point super crystal clear, doing a nonlinear feature expansion is what makes the model nonlinear overall. As a side note, we also saw how we could do this in code in the beginner's corner. The particular tool that we would use is called the pipeline, which allows us to daisy chain various feature transformers, ending with a final supervised model. So in scikit-learn, if we wanted polynomial features, we could simply create a pipeline consisting of two objects. One with the polynomial features class, and then another with some classifier such as logistic regression. Now going back to the math, we can express such a transformation as follows. Instead of inputting x directly into the SVM, we instead transform it into a new feature vector phi of x. In this scenario, what might end up happening is that we could explode the dimensionality of the feature vector. So if x has dimensionality d, then phi of x will have dimensionality d prime, and it's possible that d prime is much greater than d. Of course, this is not good because it means our computations will take a lot longer. But I told you earlier that SVM has an elegant way of handling this. Let's see how. The idea with SVM is, instead of actually calculating the dot products, we are instead going to calculate something called a kernel function. You can imagine a kernel function as a function that takes in two x vectors and outputs a single scalar. This is exactly what appears in our training objective and in our predictions, so that makes sense. The requirement that we have for this kernel function, usually denoted by the letter k, is that it actually reduces to a dot product of actual feature vectors. The basic idea behind the kernel trick is this. Since both the training phase and the prediction phase only have dot products between the x's, we can replace them with feature transformations. That is, instead of having a feature transformation happen before we apply the model, let's just make it part of the model instead. Additionally, after making it part of the model, we can find a more efficient method of calculating the dot product in the form of a kernel function. In this lecture and the next few lectures, you'll see a few examples of kernels that do implicit feature transformations and how calculating those kernels is much more efficient than explicitly doing the feature transformation. Let's do a simple example. Suppose that instead of simply calculating the dot product between the two x's, I calculate the dot product and square it. I claim that this represents a dot product of certain features derived from the x's. Let's see if we can prove that this is the case. The most basic example we can start with is two input feature vectors, where we have that the input dimensionality is 2. So in this case, x is just x1, x2, and x prime is just x1 prime, x2 prime. Now the first thing we can do is write down the dot product explicitly in terms of the components. So I have x1, x1 prime plus x2, x2 prime times the same thing, because that's what we mean by square. The next step is to multiply out the terms. We get x1, x1 prime all squared plus 2x1, x2, x1 prime, x2 prime plus x2, x2 prime all squared. The third step is to realize that we can factor this into another dot product, where of course the first dot product is only allowed to depend on x1 and x2, and the second dot product is only allowed to depend on x1 prime and x2 prime. So what does this mean? It means we have found the feature transformation phi. In particular, it transforms the inputs from a two-dimensional vector x1, x2 into a new three-dimensional vector x1 squared, root 2 x1, x2, and x2 squared. Later on, we can do the same exercise for an arbitrary input dimension, but for now, let's get back to the main point. In this simple example, we saw that a calculation which only depended on an input dimensionality of 2 implicitly performed a feature expansion, where the feature dimensionality was 3. You might think that's not really huge savings, but of course, our first example was necessarily very simple. In practice, we'll be able to create features of very high dimensionality, even infinite dimensionality. In the next lecture, you'll see how we can handle the exploding polynomial problem, which we encountered earlier in this course. So why is this good? Well, imagine if we did the feature transformation explicitly, say using the scikit-learn object polynomial features. Then we'd transform the input of size, say 10, into an output of size maybe 1000. Then our SVM solver has to contend with inputs that are size 1000. Instead, we're saying that the SVM can do this automatically simply by using the kernel function. In other words, we can have features with dimensionality 1000, even though we only ever deal with actual computations on the order of 10. In the case of infinite dimensional features, it would not even be possible to compute them explicitly. One last note is that sometimes we refer to what is called the linear kernel, which is equivalent to having no kernel at all, which is equivalent to the linear SVM, which we've already discussed. In the next few lectures, we'll go over some common kernels, discuss what makes a kernel, and how to choose the best kernel for your problem. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to explore polynomial kernels more in depth. Earlier in the course, you saw how polynomial feature expansions explode in size. This happens both when we increase the input dimensionality and when we increase the degree of the polynomial. Thus, if we can find a kernel that can represent arbitrary polynomial feature expansions, that could be very useful. Let's start by doing the same exercise we did before for a kernel where we just square the dot product, but for an arbitrary input dimensionality, d. First, we can start with the simple definition that a dot product is just the element-wise multiplication and sum of each input vector. By definition, to square it, this is just the dot product multiplied by the same dot product. Now, theoretically, I could use the same index I for both summations, but I would like to combine these, so to keep things clearer, I'm going to use two distinct summation indices, I and j. Remember that these are just dummy variables, so we're allowed to call them anything we want. Now this is an ugly summation, so we'll have to think about it a little bit. I think a simple example helps. If we just let xi prime equal to ai and xj prime equal to aj, and we let the dimensionality equal 3, this should be sufficient to help us see the pattern. So we have a1 plus a2 plus a3 times a1 plus a2 plus a3. And we arrive at, if you expand this out, a1 squared plus a2 squared plus a3 squared plus 2 times a1 a2 plus 2 times a1 a3 plus 2 times a2 a3. In other words, we can always factor out a summation into two distinct types of terms. We have the square terms and the interaction terms. Of course, we can now generalize this back to our case. So it's the sum of xi prime all squared plus 2 times xi prime xj prime, but only for certain indices. Specifically, we're following the pattern where I is some number and then j is some bigger number. And this, of course, corresponds to the following factorization. Now you might want to double check this on paper by yourself. So we have x1 squared, x2 squared, all the way up to xd squared, and then we have the interaction terms. Square root of 2 times x1 x2, square root of 2 times x1 x3, and so on. One thing you might have noticed right away is that while squaring the dot product to get a new kernel gives us all the square terms and interaction terms, it seems to erase the linear terms. As we discussed previously, we might want to keep the original features as well, since they could be useful. Let's consider another kernel where we add a constant c before taking the square. Again, our strategy is going to be to represent everything as a scalar and just multiply it out. So we have the sum over xi prime plus c times the sum over xj prime plus c. Luckily, we already know how to handle a summation multiplied by another summation because we just did that. The only new thing we need to consider is the c term, and since it's just a constant, that should be pretty easy. So expanding this out, we can start with the two terms we had before, the sum over xi prime squared, and then the interaction terms. The two new terms are just c times the single summation, and then c times itself. Using this, it is again pretty simple to factor out what phi is, just by separating the prime and non-prime terms. As you can see, this gives us back our linear terms, and it even gives us a constant term. At this point, we now know how to modify our polynomial kernel to get all the polynomial terms for when we want a polynomial of degree 2. What about polynomials of higher degree? Well, this is as easy as simply changing the power in the exponent from 2 to any other number. In this case, we're not going to perform the derivation explicitly, although you are welcome to try it yourself. You can imagine intuitively that this will contain polynomial terms up to and including d. And to reiterate, what makes this so powerful is that normally, computing a polynomial grows as d increases. Using kernels, the computation time for computing the feature expansion remains constant, since we don't have to compute the features explicitly. So we get a very expressive, nonlinear function, while still only doing the exact same amount of work as we had to do for the linear SVM. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss the most popular kernel, and probably the one that people most often think of as synonymous with SVMs, the Gaussian kernel. The Gaussian kernel takes on the same shape as a Gaussian distribution, although the Gaussian kernel is not a proper probability distribution. In other words, we care about the overall shape, but not really about any of the constants associated with the Gaussian distribution. As you recall, the Gaussian is in the shape of a bell curve. So after removing all the unnecessary constants, what we're left with is the Gaussian kernel, which you can see here. In some sources, you'll see the Gaussian kernel with the parameter on top, where we call it gamma. In other sources, you'll see the Gaussian kernel with the parameter on the bottom, where we call it sigma. We'll mostly use gamma since that's what it's called in scikit-learn, although sigma might be slightly more intuitive if you're used to working with the Gaussian probability distribution. That's because sigma squared in the Gaussian distribution would exactly correspond to that distribution's variance. So if sigma is large, then the bell curve is fat. When sigma is small, then the bell curve is skinny. So just remember that gamma is the reverse of this. When gamma is large, the distribution is skinny, and when gamma is small, the distribution is fat. Let's discuss the behavior of the Gaussian kernel. First, you'll notice that the maximum value is 1. This occurs when x is equal to x prime, so that the distance between the two vectors is 0. This gives us e to the power 0, which is 1. Now what happens if x is not equal to x prime? In that case, the distance will be greater than 0. If the distance is greater than 0, then we get e to the power of a negative number, which gives us a number less than 1. Notice also that the Gaussian kernel depends only on the relative distance between the 2 points. If you imagine x as fixed and x prime as variable, we can do some simple examples. Suppose x is fixed at 0, 0 and x prime is at 0, 2. Assume that gamma is 1. Then the squared distance between x and x prime is 4, so we get e to the power minus 4, which is 0.018. Now imagine that x prime is on the other side, 0 minus 2. Now what do we get? Well, the squared distance between x and x prime is still 4, so we get e to the power minus 4, which is still equal to 0.018. Now imagine x prime is not above nor below x, but to the right of x at 2, 0. Now what do we get? Again, the squared distance between x and x prime is 4, so we get e to the minus 4 equals 0.018. As a final example, suppose that x prime is at a 45-degree angle relative to x at root 2, root 2. Now what do we get? Still the distance between x and x prime is 4, so we get e to the minus 4 equals 0.018. So what is the lesson here? Well, the lesson is that the value of the Gaussian kernel is dependent only on the distance between x and x prime. You can imagine concentric circles around x, which would draw a contour plot of the Gaussian kernel. Another way I can state this is, the value of the Gaussian kernel only changes as I move radially outward. For this reason, the Gaussian kernel is also sometimes referred to as the radial basis function. So sometimes you'll see this referred to as the RBF kernel. We'll provide more insight into this name later on in the course when we discuss RBF networks. As a final note, this also explains why we have to normalize our data before passing it into the SVM. In other words, this is why the SVM is scale sensitive. You can imagine that if we left the data unscaled, some dimensions might be much more spread out than other dimensions. When this happens, it causes the large variance inputs to have much more influence than the small variance inputs, which is of course not desirable. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to further discuss the Gaussian kernel. In particular, we are going to talk about some important topics, such as how to choose the hyperparameters involved with the Gaussian kernel, as well as potential problems overfitting. First, let's be direct about the hyperparameters involved with the SVM. Normally, there are really only two hyperparameters you have to worry about. The reason for this is, the Gaussian kernel is by far the most common choice. It works well for most problems you'll apply the SVM to. As you know, the Gaussian kernel has only one hyperparameter, gamma. The other hyperparameter you should care about is c, but we already discussed that earlier in this course. Let's review C again, since it's somewhat related to this discussion. C is the strength of the misclassification penalty. Thus, it allows us to either care more about the classification error, or to care more about having small weights and large margins. It's your usual run-of-the-mill bias variance dilemma. If we were to put this in a table, you could list out the differences between high C and low C. As usual, we can express this in terms of training accuracy, in terms of overfitting, in terms of the expressiveness of the decision boundary, and, now that you know about them, in terms of the number of support vectors. So if we have high C, that means we want higher training accuracy. We could be more amenable to overfitting, we'll have a more complex decision boundary, and we'll have more support vectors. If we choose a lower C, that means we're okay with a lower training accuracy, but less overfitting. We'll have a simpler decision boundary, and we'll have less support vectors, which could be more computationally efficient. Next, let's talk about gamma. As discussed, the Gaussian kernel always gives us back a number between 0 and 1. If we recall our prediction function, this is just the sum over all the kernel values for the support vectors, which of course are important vectors from the training set. The basic idea is, if our test input is close to the support vector, we should get a value close to 1. If our test input is far from the support vector, we should get a value close to 0. Using this intuition, let's think about the effect of gamma. Remember, gamma is like a precision, which is the opposite of variance. So let's imagine a Gaussian curve with low precision but high variance. This is a fat Gaussian curve. In this scenario, we can see that, for a wide spread of input values, we can still get a pretty large number. Therefore, when the precision is low, the data points that the Gaussian kernel considers close is pretty liberal. On the other hand, let's consider what happens when the precision is high, but the variance is small. In this case, we have a very skinny Gaussian curve. For most input values, unless they are very close, we will get a number close to 0. In other words, this Gaussian kernel is very conservative in regards to which data points it considers close. One way to picture this is as follows. When gamma is very large, we have very high precision, and hence we have very sharp decision boundaries. In other words, this should tend to overfit. When gamma is small, we have very low precision, and hence we have very smooth, broad strokes for our decision boundary. In other words, this should tend to underfit. To summarize this, we can make another table. When gamma is high, we can expect to have higher training accuracy, but with overfitting, and a complex decision boundary. When gamma is low, we can expect to have lower training accuracy, which means we're underfitting, and a simple decision boundary, approaching a straight line. Interestingly, this doesn't give us a simple high-low relationship with the number of support vectors. The reason is, if we overfit, the number of support vectors will be large, due to having to support the complex decision boundary at all its points. On the other hand, if we underfit, the training accuracy will be low, which means many points may violate the margin, and they will also be support vectors. So the minimum point, where the number of support vectors is small, is somewhere in between. What is also interesting about this is the Gaussian kernel doesn't overfit in all cases. Let me explain why you might think it should. If you're an extra astute observer, you might have noticed one thing. I told you earlier that for a kernel to be valid, we should be able to express it as a dot product of some feature transformation. Yet the Gaussian kernel looks nothing like a dot product, nor does it appear to be obvious how we can factor it out to express it as a dot product. In fact, the Gaussian kernel is very special. It corresponds to an infinite dimensional feature space. How exactly that is, you'll have to wait until the next lecture. But an infinite dimensional feature space seems bad from our intuition about polynomials. As you know, if we use a polynomial of infinite degree, then we can approximate a function with perfect accuracy. Of course, this leads to severe overfitting. Polynomials have the same type of bias variance trade-off that we've been discussing. Low-degree polynomials have less complexity but higher training error. They are simpler but tend to overfit less. High-degree polynomials express more complex curves and have lower training error, but they overfit more. And so you can imagine that a polynomial of infinite degree would surely overfit. So why then does the Gaussian kernel, if it implies an infinite dimensional feature space, not overfit? The answer is that which we've already discovered. The degree of overfitting is more due to gamma than it is to the feature dimensionality, which is actually infinite in all cases. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to prove that the Gaussian kernel corresponds to infinite dimensional features. This is important not really because of the infinite dimensional nature of the features, but because we still have to make sure that the kernel really corresponds to a dot product of features. Recall that earlier, we showed that the high dimensionality actually is of no consequence. What really matters is that it's a proper kernel and corresponds to a real dot product in the first place. In a later lecture, we'll go more in depth into what makes a kernel a kernel. The first thing we need to show is that the sum of two kernels is still a kernel. Let's see how. First, we'll define K3 to be the sum of two kernels which we know are valid, K1 and K2. If K1 and K2 are valid kernels, then they can be expressed as dot products, so we can expand this into phi1 transpose x times phi1 x prime plus phi2 transpose x times phi2 x prime. Of course, we can now see that this is in the exact form of a dot product. The feature vector for kernel 3 is simply the concatenation of the feature vectors for kernels 1 and 2. With this fact in mind, let's begin to factor out the Gaussian kernel. We can assume gamma equals 1 without loss of generality. As you recall, the squared magnitude is just the dot product between a vector and itself. So we can replace the square magnitude expression with x minus x prime dotted with itself. Next, we can expand the expression. This is just your basic quadratic equation. Now, we can see that there is one term that depends only on x and one term that depends only on x prime, so we can factor those out. The next thing we have to remember is the Taylor expansion rule for exponentials. In particular, it says that e to the power z is equal to the sum from k equals 0 to infinity of z to the power k divided by k factorial. Using this identity, we can replace the final exponential. The next step is to realize that the two exponentials outside the summation can really be thought of as just arbitrary functions of x and x prime. We can just name this function c and not really worry about what it represents. Next, we can move these c's back into the summation. The next step is tricky, but if you think about it in terms of basic algebra, you can understand why it works. We're going to move the c's inside the dot product, which requires us to take the kth root of c. Note also that for convenience, I'm going to start using the brackets for inner product notation rather than dot product notation, although either is fine if you have space. The last step is to realize that k factorial can also be moved inside the inner product, simply by taking the square root and giving the square root of k factorial to both sides. At this point, we can use several facts to convince us that this is in fact a valid kernel. First, the innermost term is an inner product, which is of course a valid kernel. Next, we know that raising an inner product to a power k is also a valid kernel because that gives us the polynomial kernel. Finally, we know that summations of kernels are also kernels, which means this is an infinite summation of polynomial kernels. Thus, we can conclude that the Gaussian kernel is in fact a valid kernel. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to have a short discussion about other, less popular kernels that can be used in your nonlinear SVM. The first one we're going to discuss is the sigmoid kernel. The sigmoid kernel was very interesting to researchers because of its similarity to neural networks. Specifically, the sigmoid kernel uses the tanh function as follows. Now, it might seem at this point only to be related to neural networks for the fact that it uses a tanh, but the connection is in fact deeper than that. Let's see how. First, let's consider the full equation for a one hidden layer neural network. Let's use W and R for the input to hidden weight and bias, and let's use alpha and B for the hidden to output weight and bias. Then our neural network equation becomes what you see here. For the hidden values, we get Z of I equals to tanh of Wi transpose X plus R of I. For the output value, which we're assuming is just a single output node for binary classification, we get Y hat is equal to the sigmoid of the sum over all I, alpha I times Z of I plus B. Putting these together, we can get the final equation. Now let's look at the output for an SVM with a sigmoid kernel. For the kernel, we have k of xi and x equals to tanh of gamma times x of I transpose times x plus r. For the output prediction, we have our usual prediction rule. And finally, we can plug in the expression for k to get the final expression you see here. Now, comparing these side by side, it's easy to see these similarities and differences. First, it's almost like gamma times x of I is the input to hidden weight. R is the input to hidden bias. In the SVM case, it's the same for all hidden units, but for the neural network case, each hidden unit has its own bias. For the hidden to output weight in the neural network, this is just alpha I, but for the SVM, it's alpha I times Y of I. And of course, the output bias is exactly analogous in both cases. Also note that the output function is very similar. For the neural network, we use a sigmoid, and for the SVM, we use the sine function. If we rescale the sine function to go from 0 to 1, we can see how it's almost like a coarse approximation of the sigmoid. Or alternatively, the sigmoid is a soft or fuzzy version of the sine function. One major difference between the SVM and neural network is that with the neural network, all the weights are updated globally and simultaneously. Every parameter in the neural network is updated using gradient descent. In the SVM, this is not really the case. Instead, for the input to hidden layer, the relevant xi's, the support vectors, are chosen via the quadratic program. They are not simply arbitrary vectors, they are feature vectors which appeared in the training set. The alphas are also chosen via the quadratic program rather than using gradient methods. What's interesting about the sigmoid kernel is that it in fact is not always a valid kernel. In the next lecture, you'll learn about Mercer's condition. It can be shown, although we won't do so, that for certain values of gamma and r, the sigmoid kernel does not meet Mercer's condition. The next interesting kernel I want to talk about is the string kernel. The string kernel is very interesting because it operates on objects that are not numerical, but rather strings, as its name implies. For example, my input can be 2 emails if I'm building a spam detector, or 2 movie reviews if I'm building a sentiment analysis classifier. Additionally, string kernels are popular in bioinformatics because DNA sequences are also strings. Although we won't use any string kernels in this course, it's certainly a topic you're encouraged to look into if it's applicable to your work. The best way to learn is by example, so let's look at an example of a string kernel. In this example, we compute the feature expansion explicitly. The basic idea is we're going to have a vector of all the possible pairs of letters in our corpus, where those letters appear in order. So for example, we want to have an entry for CA because the sequence CA appears both in the word cat and in the word car. We want to have an entry for CT because T appears after C in the word cat, even though they are not beside each other. The value of the feature is then how far apart those two letters are. For example, CA gets the value lambda squared because the sequence CA takes up 2 spaces in the word cat. The sequence CT gets the value lambda to the power 3 because going from C to T in the word cat takes up 3 spaces. And the key is we choose a lambda between 0 and 1. So the closer together 2 letters are, the higher the feature value they have. The further apart 2 letters are, the closer to 0 the feature value is. And the feature value has a geometric decay towards 0 with respect to the distance between the 2 letters. In this example, we can compute that when you dot phi of cat and phi of car together, you get lambda to the power 4. Now, interestingly, while the feature expansion is easy to understand, the kernel itself is not, so we're not going to discuss it in this course. The advantage of using it is that, like the other kernels we discussed, calculating the kernel directly is more efficient than calculating the feature expansions and then doing the dot product. So if you'd like to read more about the algorithms developed for efficient calculation of the string kernel, you are welcome to read the paper I've attached in extrareading.txt. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss more in depth this question of, how do I know if my kernel function is a valid kernel? Previously, we discussed it from the perspective of dot products. We said that if you can express your kernel as a dot product of a feature expansion of the inputs, then it's a valid kernel. In this lecture, we are going to generalize this concept. To start, we'll have to discuss this concept of a matrix being positive semi-definite. What does this mean? Well, first, let's talk about what a positive number is. A positive number is just a number that is bigger than 0. Of course, we also have the concept of non-negative numbers. These are numbers that can be greater than 0 or equal to 0. Now we can discuss the matrix analog of this idea. For matrices, we can say a matrix is positive definite if it meets this criteria. Basically, for any non-zero vector x, this relationship has to hold. For the positive definite case, x transpose ax must be greater than 0. For the positive semi-definite case, x transpose ax must be greater than or equal to 0. As an example, let's consider the identity matrix. Let's suppose the dimensionality is 2 to make things simpler. Given that x contains the elements a, b, the result of x transpose ix is equal to a squared plus b squared. And since x must be non-zero, this number must be positive, and hence the identity matrix is positive definite. Let's see how this applies to SVMs. Remember that our training objective includes the kernel, and it sums over the training set twice in a nested loop. That means we have a kernel value for every training point matched with every other training point, including itself. Hence, you can think of this as giving us an n by n matrix. The ijth entry of this matrix is just the value of the kernel function for the inputs xi and xj. As you might suspect, our goal is to show that this matrix is positive semi-definite. In fact, this is exactly Mercer's condition, which is the topic of this lecture. It says that if K is a positive semi-definite matrix, then K is a valid kernel. Notice we use the same letter K for both purposes, so you have to pay attention to the context. K refers to both the matrix and the function. Let's now apply our original criteria, that the kernel can be expressed as a dot product of some feature expansion. Note how here I'm using the letter K to mean the matrix of kernel values for the training inputs, and not K the function. Also in this case, let's use the letter Z on the outside, so we don't confuse it with our input vector x. Let's start with Z transpose times K times Z. Our goal is to show that this will be greater than or equal to 0. Since we're assuming that K can be split up into the dot product of a feature expansion, we can replace K with an actual dot product and also write things down in scalar form. Using the definition of matrix multiplication, this is the sum over I and j of Z of I times the dot product of phi of xi and phi of xj times Z of j. Remember that since the dot product in the center is the output of a kernel function, the result is just a number. But we can split this into its own dot product over the index k. Since summations can be done in any order, we can move the summation over k to the outside. To see how we can simplify this, let's do a simple problem. Consider the summation over I and j from 1 to 3 of just ai multiplied by aj. After multiplying this out, you can see that we can express it in a different way. In fact, it's just the sum over the a's all squared. You might want to pause this video and try it on paper if you don't see it right away. Thus, we can simplify our summation that we had previously by getting rid of the I and j summations and instead express it as a square. And of course, since this is the sum of all squared terms, it must be greater than or equal to 0. Hence, Mercer's condition is another way of stating that the kernel function must be a dot product of some feature expansion. So how does this apply to us and why is it useful? Well, surely you must have noticed that trying to derive each kernel as a dot product is very labor intensive and not very easy at all. So this gives us a much simpler way to test whether or not our kernel is valid. Since it is easy to use NumPy to check whether or not a matrix is positive semi-definite, then all we need to do is calculate the kernel matrix over our training data and call our NumPy function. This is a computational and automated approach as opposed to trying to manipulate the kernel function on paper. As a side note, while Mercer's condition is a nice theoretical tool, In practice, sometimes we just don't care whether or not Mercer's condition is met. One example of this is the sigmoid kernel, which turns out to work well in practice. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to summarize everything we learned in this section. This section was all about taking the result we derived in the duality section and applying that to create the kernel SVM. The kernel SVM allows us to create nonlinear decision boundaries since a kernel can represent different kinds of feature expansions. Earlier in this course, we looked at explicit feature expansions. That means we would manually calculate the feature vector phi and then feed that into our model. With SVMs, we saw how we could have implicit feature expansions by representing the dot product of features as a kernel. We also saw how when we represent feature dot products as kernels, the calculation becomes more efficient than if we had actually calculated the features explicitly and performed the dot product. In fact, for cases where we have an infinite dimensional feature expansion, such a calculation would be impossible. After learning about the kernel trick, we discussed a few common kernels. First, we looked at the polynomial kernel, which is the most natural extension to the dot product. It seems almost magical that we can use a polynomial of arbitrary degree without any more work than just a simple dot product raised to a power, which is to say, no more work than a linear SVM. Next, we looked at the Gaussian kernel, the most important kernel when it comes to SVM. It's often chosen as the default, so we looked at how to use it effectively. In particular, that C and gamma are the two most important hyperparameters for the SVM, and how they help tune the bias variance trade-off. We also proved that the Gaussian kernel corresponds to an infinite dimensional feature expansion. Finally, we discussed the sigmoid kernel, which is very relevant due to its similarity with neural networks, and the string kernel, which is commonly used in NLP and bioinformatics. To close this section, we looked at Mercer's condition, which is essentially a test which will tell you whether or not a function you chose for the kernel is actually a valid kernel or not. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, in preparation for the implementation, we are going to go over the final dual form of our quadratic program. To recap, here are the steps we've taken so far. First, we looked at the linear SVM in its primal formulation, where the data was perfectly linearly separable. Because a quadratic program cannot be solved if the constraints are violated, we can't build a linear classifier unless it has zero training error. The solution to this was to add slack variables. This acts as regularization and allows for both misclassified samples as well as samples which simply violate the margin but are still classified correctly. Next, we developed the dual formulation of the linear SVM. This allowed us to represent the SVM program in terms of dot products only, which led us to the kernel trick. We did so again, assuming the data was perfectly linearly separable. This, of course, is necessary to develop basic intuitions about the problem without making it overly complicated. The final step, which we're going to discuss in this lecture, is to reintroduce slack variables into the dual formulation. This is going to give us a nonlinear SVM, which also has regularization and allows for misclassified samples, which of course is necessary for any real-world problem. This is the last step we need to do before we can start discussing implementations of the SVM. Since we're actually one step removed from the duality lectures, let's recap again how that works. The basic steps are this. First, we state our problem, both the objective and constraints, for the primal formulation. The next step is to introduce the Lagrange multipliers and form the Lagrangian. The third step is to manipulate the Lagrangian by plugging in the solutions to the KKT conditions. And by eliminating all of the original variables, we arrive at the dual objective. So the first step is to state our primal form. This, of course, we've already done. If you want to review that, then the relevant section is the section on the linear SVM. We would like to minimize, with respect to w and b, 1/2 w squared plus c times the sum over all xi's. This is subject to the constraints that y times w transpose x plus b must be greater than or equal to 1 minus xi, and that all the xi's must be greater than or equal to 0. As before, we're going to form the Lagrangian. Now, since the xi's also have inequality constraints, we'll need to create a separate set of Lagrange multipliers for them. We can give those the letter beta. Now, looking at this, it's important to remember which are the original variables and which are the new variables. You might get this confused because xi is a Greek letter, so you might group it with alpha and beta. But in fact, it's one of the original variables from the primal problem, so it goes with w and b. For those of you who care more about the high-level picture and want to just know the answer so that you can jump to the implementation, I'm going to state it here. The derivation is quite long and boring, and quite frankly, it doesn't add much to the discussion, which has been pretty involved already up to this point. So really, anything past this is optional. Understanding the result is most important. First, surprisingly, the objective remains exactly the same. Only the constraint on alpha has changed slightly. Before, we only had the constraint that alpha had to be greater than or equal to 0. Now, it also has to be less than or equal to c, the misclassification penalty. So in terms of how the dual formulation looks, it's almost exactly the same as what we had before. Here's the crucial difference. The value of alpha actually has very important implications for the meaning of the support vectors. There are 3 distinct cases we have to consider. If you recall, alpha being 0 means a data point does not violate the margin, and in our equations, they are generally ignored. So because you're always multiplying by alpha, anytime alpha is 0, you don't have to sum over that value. So that part is the same. Remember, this is due to the constraint that alpha multiplied by the margin constraint must equal 0. If the data point lies beyond the margin, then the g is less than 0, so alpha must be equal to 0. The second case is where alpha is strictly between 0 and c. This will take some thinking. In this case, xi is 0, and the data point lies directly on the margin, meaning that y times w transpose x plus b is equal to 1. These points will be useful for us, as you'll see later. The third case is where alpha is exactly equal to c. In this case, the data point violates the margin. That means the data point is either correctly classified and inside the margin, or is incorrectly classified. Xi is greater than 0, and y times w transpose x plus b is equal to 1 minus xi. Now, if you're interested, we can look at how these constraints are derived. Although be warned, this is again just pure mechanical calculation. All we're doing is solving the KKT conditions. First, you'll notice that if you take the gradient of the Lagrangian with respect to w and b, you get the same answers as we had before. It's important to remember that xi is also one of the original variables, so we should take the gradient of the Lagrangian with respect to xi as well. This just gives us that alpha plus beta must equal to c. The final step is to replace w, b, and xi in the Lagrangian to get the dual objective. After doing that, you should arrive at the expected answer, which is the same dual objective we had before. The next step is to determine the constraints on alpha and understand how different values of alpha have different meanings in terms of whether or not a data point is past the margin, on the margin, or violates the margin. First, we already know that alpha must be greater than or equal to 0, since that is just one of the raw KKT constraints. Next, since alpha plus beta must equal to c, and the smallest value of beta is 0, that means the maximum value of alpha is c. Therefore, alpha must be between 0 and c. Next, let's focus on the following KKT conditions. Let's consider beta. Since beta times xi must equal 0, then if beta is greater than 0, xi must equal to 0 for the product to be 0. In this case, since beta is greater than 0, alpha must be less than c. In other words, when xi is 0, alpha is less than c. From here, we can plug in the fact that xi is equal to 0 to get this equation. Alpha times 1 minus y times w transpose x plus b is equal to 0. Again, we have this pattern, the product of two things must equal 0. So now we can reason that if alpha is greater than 0, that means the other term must be equal to 0. Finally, putting all this together, we can conclude that if alpha is strictly between 0 and c, then y times w transpose x plus b is equal to 1, which means the data point I lies directly on the margin line. Next, we can consider the other branch of this logic. What if alpha is equal to 0? Then the other term is free to be less than 0. Recall that one of the KKT conditions is that the second term must be less than or equal to 0. So if alpha is equal to 0, then the other term is less than 0, which means that y times w transpose x plus b is greater than 1. As before, this corresponds to data points which lie on the good side of the margin. The final scenario to consider is when alpha is equal to c. In this case, beta must equal 0, which means xi is greater than 0, which means the error is not 0. For this, you can just think of the hinge loss not being 0. What this means is the data point violates the margin. To summarize this lecture, what we've done is reintroduced slack variables into our dual formulation so that we have all the pieces we need to implement the SVM for real-world datasets, which may have a non-zero error rate and may require regularization. We discovered that the dual objective looks exactly the same as it did before, while the constraint on alpha looks only a little bit different. We looked at the three scenarios for alpha. If alpha is equal to 0, the data point lies beyond the margin and is correctly classified. If alpha is greater than 0 but less than c, the data point lies directly on the margin line. If alpha is equal to c, the data point violates the margin and may be incorrectly classified. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss a couple of simple ways to solve a quadratic program and implement your SVM. The first method I want to discuss is the method which we already described very early in this course, to simply use a library function that solves general quadratic programs. Unfortunately, this method doesn't work particularly well as it doesn't scale to even moderately large datasets. The reason for this is that solving the quadratic program requires us to pass in the objective function, which involves calculating the entire kernel matrix. If you recall, this is an n by n matrix, thus its size grows faster than n itself. If n equals 100, then the kernel matrix will be size 10,000. But if n equals 1,000, the kernel matrix will be of size 1,000,000. At the same time, if you want to try using a Python library such as cvxopt to implement an SVM yourself for practice, that would be strongly encouraged. The next method I want to discuss is a form of gradient descent which will be the topic for the rest of this lecture. I personally like this method because it is not much different from regular gradient descent, which we use for other popular machine learning methods such as linear regression and neural networks. It is much simpler than the next algorithm we're going to discuss, which is called SMO. For reasons you don't understand yet, SMO requires us to manually loop through the training set, which, as you know, is very slow in Python. So it's a method which is better suited for languages such as C or C++. This is why, most commonly, people will use a library called libsvm, which incidentally is written in C++. Even scikit-learn uses this library for its SVM class. It does not try to implement the SVM by itself. Of course, the purpose of implementation for us is exercise, not to actually engineer useful software. So while SMO is currently the standard solution for solving the SVM quadratic problem, in Python, it's actually faster and easier to do gradient descent. Earlier, I told you that gradient descent is not possible to use because we just don't have an objective. We also have constraints. This was true, but there are still workarounds. First, let's rewrite our objective in vector form so that we can more easily derive the gradient. The goal is to maximize over alpha transpose 1 minus 1/2 times alpha transpose times g times alpha. And this is subject to the constraint that alpha must be between 0 and c. In this case, 1 means a vector of 1s of length n, and g is a matrix such that gij is equal to yi times yj times the kernel for xi and xj. Now if we let j be our objective, then the gradient of j with respect to alpha is just 1 minus g times alpha, which is a very simple expression. By the way, since this is an objective we want to maximize, we're going to be doing gradient ascent rather than actual gradient descent. So we're going up instead of down the gradient. And so normally, if this were just regular gradient descent, we would just repeatedly perform the gradient ascent step in a loop. But since we now have constraints, we are going to do the simplest thing possible to fix them. If we find that any of the alphas violate the constraints, we'll simply clamp them to their boundary values. For example, if alpha becomes negative after a step of gradient descent, we'll just set it to 0. If it becomes larger than c, we'll just set it equal to c. We call this method projected gradient descent. Now you might realize there is still a problem with this. Let's recall how we make predictions with the kernelized SVM. As you can see, we sum over all the training samples and calculate the kernel, but we also have to add the bias b at the end. Unfortunately, the bias b does not appear anywhere in our objective. So how can we do gradient descent on b if it doesn't even appear? The answer is we don't. What we have to do is use the facts we derived in the previous lecture for the different possible outcomes for alpha. Recall that if alpha is equal to 0, then the data point lies beyond the margin and is correctly classified. If alpha is between a 0 and c, then the data point lies directly on the margin line. And if alpha is equal to c, the data point violates the margin. What we're interested in is data points for the second case, the ones that lie directly on the margin line. These are very useful to us because they give us an exact equation for b. We know that the margin lines are given by the equation y times w transpose x plus b equals 1, where y can only be plus 1 or minus 1. So we can rearrange for b to get y minus w transpose x. And theoretically, we should be able to choose any of these data points and they should all give us the same answer. In reality, they don't. So what we're going to do instead is find b for all of them and then take the average. Now surprisingly, that's all you need to know to implement an SVM in code with projected gradient descent. Although keep in mind that while this seems simple, there had to be a lot of theoretical development in order to get us to this point. In the next lecture, we'll implement this SVM solution in code. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to look at how to implement an SVM with projected gradient descent. As usual, you are always encouraged to try this as an exercise by yourself first before looking at this code. So if you want to give that a try, please stop this lecture now and return when you are done. The relevant file for this lecture is svmgradient.py. At the top, we've defined some kernel functions. The first is a linear kernel, which is just the standard dot product between x1 and x2. Optionally, you can add a bias term c. Next is the RBF kernel. This one is a bit longer since we have to handle different cases for when x has different dimensionality. In the first case, both x1 and x2 represent one sample, which means they are both one-dimensional arrays. In the second case, one of the inputs is a batch of samples and the other input is a single sample. In the third case, both inputs are batches of samples as we would have when we have to calculate the kernel matrix. Lastly, we have the sigmoid kernel, which implements the equation which you saw from the lectures. Since it only involves a dot product of x1 and x2, we don't need to consider different cases. Next, we have the SVM class. The constructor takes in two arguments, c, the misclassification penalty, and a kernel function. The next function is for calculating the objective. We assume we're only going to calculate the objective over the training set, so we don't need to pass in any data, and we can just use a pre-calculated kernel matrix. Also note that we've taken the convention that the objective is something we want to maximize rather than minimize. So if you want something more like a loss to minimize, you could reverse the signs. Next, we have the fit function, which takes in the training inputs, the training targets, the learning rate, and the number of iterations. To start, we're going to assign x and y to be attributes of the object, since they are both used when making future predictions. We also set n the number of training samples. Next, we initialize alpha randomly and set the bias term to 0. Next, we pre-calculate the kernel matrix, which we use when we calculate the objective. Since the y's also appear in the objective multiplied by the kernel matrix, we can combine them all together in one attribute called yyk. As a side note, if you really wanted this to be scalable, you wouldn't be able to store this in memory. Instead, you'd have to calculate it by looping over all the data. However, that would be slow, and also you probably wouldn't be using Python if you were going to attempt something like that. So just keep that in mind. It could be more scalable, but for this exercise, it's impractical. Next, we have the gradient descent loop. On each iteration of the loop, we first calculate our training objective and append it to a list so we can plot it later. Next, we calculate the gradient, which we derived in the lectures. Then we do one step of gradient ascent. Note that you could also apply modern deep learning techniques here, such as momentum, atom, and so forth, if you wanted. The next step is to clip the alphas so that they are in the valid range. Remember that alpha must always be between 0 and c. Once we've completed the gradient descent loop, we can calculate the bias term. To do this, we're going to use the equation we derived in the lectures, y minus w transpose times x. And we're going to calculate the bias for every data point which corresponds to a support vector that lies on the margin. These are the data points for which alpha is strictly greater than 0 and strictly less than c. Once we've retrieved those indices, we can find all the b's as a batch and then take the average. Lastly, we plot the objective per iteration. The next step is to implement our decision function. This is just alpha times ytrain times the kernel function with xtrain and the input arguments, then add the bias term. Our prediction function then takes the sign of the output of the decision function. Finally, the score function returns the accuracy of a given set of x's and y's. Next, we have some data loading code. This is going to allow you to test the SVM on several datasets, along with preset hyperparameters. Note that I didn't do an extensive hyperparameter search, but the hyperparameters chosen are reasonable. We have the medical dataset with an RBF kernel, the medical dataset with a sigmoid kernel, the XOR, the donut, and spiral problems, and then a basic Gaussian cloud problem. For the Gaussian cloud, we would like to use the linear kernel because the data is linearly separable, although you are encouraged to test other kernels as well. Finally, we have the main section. This is exactly the same as you've seen before. We load in the data and reassign any targets where the negative class is 0 to -1. Then we scale the data using a standard scalar object. Next, we instantiate our SVM, fit it, and print out the train score and the test score. Also, one thing that's nice is that for 2D datasets, we can plot the decision boundary and look at the margins, so we can see what the SVM has learned. Now let's run this and see what we get. Alright, so let's try the medical dataset. So here's the objective. This is our train score and our test score. Now notice it doesn't print anything because the medical dataset is not two-dimensional. Let's now try the sigmoid version of this. Use the loss per iteration, and we get pretty comparable results. Next, we can try the XOR problem. So here's the loss per iteration, and also we get a plot. Now let's try the donut. Here's the loss, and here's the decision boundary. And finally the spiral. And so here's the spiral data set. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to do something which I think is very interesting. We're going to implement the kernelized SVM using gradient descent, but instead of working with the dual, we are going to work with the primal. What I find is that this actually works better than the dual version. So how is this going to work? Well, it requires us to do a little trick, which is to pretend we're training a linear SVM and define the weights in terms of the feature vectors. You might think of this as a reparameterization trick. Of course, these things are hard to understand in words, so let's just look at the math. The idea is we're going to introduce a new parameter called u, which is a vector of length n. In this equation, I'm using phi of x to mean the feature transformation over the entire training set x. So whenever you see the big X, that means the whole training set, and if you see a little x, that means one sample. So you can imagine this as a big n by d matrix, where d is the number of features. The transpose of this would be of shape d by n, so when you multiply it by a vector of length n, you get a vector of length d, which is what w is. so the dimensions check out. The next step is to restate our primal problem in terms of our new parameter vector u. Now, this might look a little odd to you at first, and this is because the way we store feature vectors in machine learning is a little weird. When we think about a single feature vector, meaning the lowercase letter x, usually by convention it is a column vector. But when we think of a full data matrix, usually each sample goes along the rows. So each feature vector becomes a row vector when it's batched with other feature vectors. That's why it's n by d and not d by n. So keeping that in mind, you can confirm that anywhere you see a phi here, the dimensions actually do work. What is interesting about this is, like our dual from before, it only contains dot products. I think this is a very nice result actually. It means that we have the power of the kernel trick without having to even derive the dual, which is, as you experience firsthand, a lot of work. Now you might recognize that whenever we do the outer product of phi of big X and phi of big X, that actually gives us our kernel matrix. So I can rewrite the loss function as follows. In this expression, k sub I refers to the ith column of k, which is actually equal to the ith row of k, but it helps to think of it as a column so that the matrix dimensions match. Now this is pretty cool because it allows us to perform a gradient descent on U, and the gradient is no more difficult than when we did gradient descent for the linear SVM. As before, you'll want to check these yourself by hand, and if that doesn't work, then ask me about it on the Q&A. Notice how the gradient for B remains the same. Also, as before, you want to remember that these summations are only over the misclassified samples. So if a sample does not violate the margin, both the loss and the slope at this loss are 0. The last step, of course, if you haven't already done so, is to think about how predictions are made. Now you might think, because we defined a weight W earlier, that we might need to do a manual feature transformation. Luckily, the math works out just right, so that we can again apply the kernel trick. You can see that because we end up with phi multiplied by itself, we can just substitute the kernel. For this equation, you'll want to remember that x superscript I refers to the x's from our training set, while the x with no subscript refers to an arbitrary test input. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to implement the kernel SVM in code. We will do this using gradient descent on the primal problem using a reparameterization trick so that we can take advantage of kernels. The relevant file for this lecture is kernel svm gradient primal.py. The part of the code we're interested in for this lecture is the kernel svm class. Everything else is largely the same, all stuff you've seen previously. So let's scroll down to there. So in the constructor, you see that we pass in the kernel and C, the misclassification penalty. We save these to attributes of the object. Next, we have the objective function. Now this is the same as with our other gradient script, which takes in the margins, but instead of w.w, we now have u.k.u. Next, we have the fit function. To start, we initialize our U array to a random vector of length n and a bias initialized at 0. Next, we pre-calculate our kernel matrix, where we just call the kernel function on the training data twice. Next, we enter the gradient descent loop. By the way, you'll find that the structure of this script is very similar to the linear SVM with gradient descent. So we calculate the margins. This is now y times u.k plus b. Next, we grab the loss and save it so we can plot it later. Next, we grab all the indices where the data points violate our margin lines. Then we can use these indices to grab the relevant y's and x's so that we can calculate the gradient of u. Then we update u. Next, we calculate the gradient of b, which is the same as before, and then we update b. When we're outside the loop, we assign the support attribute so that this matches the interface of scikit-learn, and plus we'll be making use of this later. Finally, we plot the loss per iteration so that you know that training has progressed as expected. Next, we have our decision function, which calculates the output of the SVM. Notice how one of the x's passed in here is the train x, and one is the test x. Next, we have the predict function, which takes the sign of the decision function. And then we have the score function, which you have seen before. So that's everything new in this script. Let's run this and see what we get. We'll start with the spiral data set. Okay, so these are the margins. This is the loss per iteration. And this is the decision boundary. Let's try the clouds just for fun. Okay, these are the margins. This is the loss per iteration. And this is the decision boundary. Okay, so it still works for linear data sets. Let's try another one. Let's do the donut. Okay, again, the margins, the loss per iteration, and the boundary. There we get a perfect score on both the train and test set. Alright, so it seems that everything looks good, and this is on par with our other code. In fact, it does better because we don't have to worry about constraints. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, my goal is to give you a rough sketch of the SMO algorithm, which stands for Sequential Minimal Optimization. Currently, SMO is the most popular algorithm for training SVMs. libsvm, which is the most popular library for training SVMs in code, is written in C++ and is heavily based on the SMO algorithm. Even scikit-learn uses libsvm without trying to implement anything by itself. Just to give you a little bit of history, the SMO algorithm was invented by a researcher named John C. Platt while he was working at Microsoft Research. His paper was published in 1998, which is actually not that long ago, and actually came out after the theory behind SVMs had been developed. So before this paper, researchers were using other methods, such as general quadratic programming solvers, which were not that efficient. You can imagine that the SMO algorithm was a very important development for this reason. Today, John Platt works as a principal scientist at Google. As I mentioned earlier, the goal of this lecture is only to give you a rough sketch of the SMO algorithm. You are most certainly welcome to read John Platt's paper, which is linked in extrareading.txt, if you want more details. Personally, I don't find the details particularly illuminating when it comes to understanding the SVM, so it's really more for those of you who are extra curious about how this specialized algorithm works. It's one of those algorithms where the details are quite different from the main theory behind the model, because it requires new theorems and new heuristics to work. In other words, to fully understand the SMO algorithm, it's almost as if you're developing an entirely new set of theory on top of what we've already studied. Here's a great visual for why the SMO algorithm is more scalable than previous algorithms. And by the way, notice I said more scalable, not absolutely scalable. It's important to know that while SMO is better than the previous algorithms it replaced, it still has trouble with larger datasets. In any case, this is a picture of previous generations of algorithms. You can imagine that each of these blocks is how much memory the algorithm is taking up. So the first algorithm, called chunking, requires loading in a big chunk of data all at once. It then grows into more and more chunks on each iteration. This, of course, will cause your memory to run out quite fast. The second algorithm, called Osuna's algorithm, starts with one moderately sized chunk and then strips away a single sample from the chunk and grabs another sample from somewhere else on each step. According to Platt's paper, this is also inefficient. Finally, we have Platt's algorithm, which only requires us to look at 2 samples at every step. You'll see exactly why that is very soon. It's also important to remember that while Platt's algorithm is memory efficient, it is still not time efficient. Each step requires O of n cubed time, as you'll soon see, so if you have a large dataset, this is not ideal. Let's now look at the details of the algorithm. First, we'll need to discuss the concept of coordinate ascent, which will help us understand the steps in SMO. Coordinate ascent is a little different from gradient ascent, which is probably what you're used to if you have a background in machine learning. When you take the gradient, you're taking a small step in every direction at once. So if your parameter vector is of size 1000, you are taking a small step in all 1000 dimensions on each iteration of gradient ascent. With coordinate ascent, we only choose one variable at a time. So you're always moving at right angles. Usually, there is a guarantee that every step will yield a value for the objective that is at least the same or better than the previous value. Other than the SVM, another example of where coordinate ascent is applied is non-negative matrix factorization. With this in mind, we can start to think about how SMO works. First, we would like to choose one alpha and optimize it by itself, while holding all the other alphas constant. Unfortunately, we realized right away why this won't work. If you recall, one of our KKT conditions was that the sum of alphas times y's should equal 0. What this means is, if we pick one of the alphas to update, there's nothing we can possibly change it to, because changing it means that we will violate the KKT condition. Of course, there's a reason we mentioned coordinate ascent in the first place, and that's because we're still going to apply this idea, just modify it a little bit. Instead of picking only one of the alphas, we'll pick 2 of the alphas. This forms the basis of the SMO algorithm. The basic outline of the algorithm goes like this. While we are not converged, the first step is to choose the best alpha I and alpha j to update, which will yield the largest boost in our objective. The second step is to optimize the objective with respect to alpha I and alpha j, keeping the other alphas fixed. Our test of convergence, unlike regular gradient descent algorithms, is not that the objective stops improving, but rather that the KKT conditions are met within some specified tolerance level. So in that sense, it differs from regular gradient descent, which normally you would just stop after the objective flattens out. Without loss of generality, we can assume that the alphas we choose are alpha 1 and alpha 2. In this case, we can separate out these alphas from the rest of the alphas using the KKT constraint we looked at earlier. Since we're not changing any of the other alphas currently, the sum on the right-hand side is a constant. Usually we just rename this to zeta. The next step is to realize that if you take the perspective that alpha 1 and alpha 2 are variables, this equation actually forms a line. After taking this course, you are probably very comfortable with this idea. Of course, depending on the sign of y1 and y2, this can be an upward sloping line or a downward sloping line, but for the purpose of this illustration, it doesn't matter. Also keep in mind our other KKT constraints. The alphas must also be between 0 and c, which constrains the optimal value of alpha 1 and alpha 2 not only to be on this line, but also within this c by c box. The next step is to use this equation for alpha 1 and alpha 2 and just isolate one of the alphas. So let's isolate alpha 1. Now we can plug this back into our original objective, in which alpha 2 is the only variable. This is because we've substituted alpha 1 for the expression involving only alpha 2, and alpha 3 up to alpha n are constant. And now, using your knowledge about what the objective function actually is, you should be able to verify that this is just a scalar quadratic equation over alpha 2. Of course, once you have this, you can just use basic algebra to solve for the optimal value of alpha 2. Once you've optimized the quadratic with respect to alpha 2, you have to remember that you are still constrained by the c by c box. So you can see from the box that you'll have some maximum value h and some minimum value L for alpha 2. With this, you can set the value of alpha 2. If the alpha 2 you optimize with the quadratic falls between L and h, then you can just keep whatever you found. If it's bigger than h, you set it to h, and if it's smaller than L, you set it to L. So that's a very basic rough sketch for how the SMO algorithm works. Luckily, the paper provides very detailed pseudocode, and there is Python code in the repository that implements this pseudocode almost verbatim. The relevant file in the course repo is svm.smo.py. One minor difference is that the paper defines the prediction function to subtract the bias term rather than add it, so you'll just have to keep that in mind. This makes it different from the way we treated the bias term in the rest of this course. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss how SVM theory can be applied to regression. Initially, the SVM was developed specifically with binary classification in mind. However, lots of research has been done in order to modify the SVM for the regression case. Luckily, this course already developed all the heavy theory behind the SVM, so translating the problem to regression is a natural next step. To start, it would be helpful if you saw the example we did earlier in this course for how to apply linear programming to linear regression. If you recall, I introduced this problem just to give you some practical examples of linear programming in order to increase your comfort level in dealing with optimization problems that have constraints in addition to an objective. The idea was we wanted to minimize the maximum absolute error. In other words, we let the individual error for each data point be epsilon I. Epsilon with no subscript is just the maximum of the individual epsilons. So then our optimization problem is to minimize epsilon with the constraint that all the y minus y hats have to be within epsilon. We can picture this regression as requiring all the data points to fall within a height of epsilon above or below the line. With support vector regression, we're going to do a very similar thing. Instead of minimizing epsilon, we'll instead start with the same SVM objective that we had before, to minimize w squared. In this case, although it looks very similar, epsilon is now a predefined constant. This allows us to pre-specify the desired error level of the regression model. Such behavior might be necessary, for example, if you want your stock return to be within a certain limit so you don't lose too much money. As before, we're going to follow the same pattern in adding regularization and developing the dual solution. Fitting all the data points exactly within a pre-specified error may not be ideal because it could lead to overfitting. Thus, we introduce slack variables. For regression, we actually need to introduce 2 new slack variables per data point because there will be slack both above and below the regression line. We'll use the prime and non-prime symbols to denote corresponding slack variables for the same sample. As before, C is the strength of our error penalty. This error penalty is called the epsilon insensitive loss because, as you can see, as long as the true data point is within epsilon, above or below the regression line, we don't care. Its loss is 0. The only time we count an error is if the data point goes outside the epsilon bounds. This, of course, looks similar to the hinge loss we studied earlier in this course. One thing that's possible to do is make epsilon equal to 0, in which case you would penalize all errors, and your loss would look like a regular absolute loss or L1 loss. The downside to this is that you would have many more support vectors up to the size of the full training set, which will slow down your calculations. As usual, the next step is to use the Lagrange multiplier method to derive the dual formulation of the problem. Remember that now we have double the slack variables and an error measure both above and below the regression line, so we'll also have to double the Lagrange multipliers as we had before. In other words, for every error constraint, we'll have an alpha and alpha prime, and for every xi and xi prime, we'll have a beta and beta prime. Solving for the dual, we get what you see here. Although this is probably just a big mess of equations, it's good to be able to recognize the core facts. In particular, again we have this idea that both the training phase and prediction phase only depend on dot products between the x's. No x ever shows up in isolation. Thus, we can apply the kernel trick, as we did before, and end up with kernel support vector regression. Also, again, notice the neat dual form, which only contains alphas as variables to optimize, even though we also had betas as our Lagrange multipliers. If you want to learn more about how the KKT conditions are met for this problem, you're encouraged to read the paper attached in extrareading.txt. I found it interesting because it also mentions a bunch of other theorems for finding valid kernels, such as integrals of kernels, products of kernels, and so forth. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss how you might apply the SVM to multi-class classification problems. First, you'll notice that libsvm, and hence scikit-learn, already allow for multi-class classification. This is because they use the techniques discussed in this lecture. It's important to remember that the SVM was developed with binary classification in mind. However, there exist some common methods in machine learning to convert binary classifiers into multi-class classifiers. The first method is called the one versus all strategy. Using this method, if we have k different classes, we will train k separate classifiers. For each classifier, the kth class is treated as the positive class, and all the other classes are treated as the negative class. You can imagine that for each classifier, training will produce a weight wk and a bias bk. You can also think of this in terms of the dual, so that you end up with alphas and then you sum over the training set, but this distinction isn't necessary. The ultimate prediction of the classifier is the class which yields the largest value of w transpose x plus b. The second method is called the one versus one method. This method pits all classes against all other classes. So each class faces off against each other class once. This results in having to create k times k minus 1 divided by 2 different classifiers. In order to make predictions, we will take a vote. Note that a vote still counts even if the true label was not used to train that classifier. So for example, if you have a classifier which compares 0 and 1, but the true digit is actually 9, and say 0 wins, that still counts as a vote for 0, even though it was only against 1. This is because during test time, we won't actually know the true label, so of course, the true label should never be used for making predictions. So the 1 versus 1 method results in having k times k minus 1 over 2 classifiers. While this might seem like a lot more work to do than the previous method, also remember that the dataset used to train each classifier is much smaller. For example, if we're working with MNIST and we have 100 samples for each of the 10 classes, then we'll have 1,000 samples in total. For the 1 versus the rest method, that means we'd have to train 10 classifiers on 1,000 samples each. That gives us a total of 10,000 parameters, not including the bias terms. Compare that to the 1 versus 1 case, training 45 classifiers on 200 samples each. In total, that gives us only 9,000 parameters, not including the bias terms. So 45 classifiers might seem like a lot, but the total number of parameters to be learned is actually less. Furthermore, remember that the time complexity for training is O of n cubed. If we just plug in for n naively and we're doing 1 versus 1, we would get 45 times 200 to the power 3, which is 3.6 times 10 to the power 8. If we plug in for n and we're doing 1 versus all, we would get 10 times 1000 to the power 3, which is 10 to the power 10. Now if we take the ratio of these two numbers, we get 0.036. So in fact, using a naive estimate, training 10 classifiers using 1 versus all is 2 orders of magnitude slower. According to this paper I've attached in extrareading.txt, these two methods perform comparably, but 1 versus 1 is faster, and so this is the method implemented in libsvm. If you want to do a nice exercise, I would recommend trying to build out the 1 versus 1 method yourself using Python, and perhaps making use of scikit-learn's SVM, but only in a binary capacity. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to introduce the next section of this course. This section of the course is nice because it is friendly to both beginners and experts. So if you made it through the tough theory parts of this course, then you'll find that this section will help you build your intuition further and make more sense of the concepts you've already learned. If you're a beginner, then this section will give you more intuition about how the SVM works to become a powerful nonlinear classifier. The outline of this section is as follows. First, we are going to introduce the RBF network. RBF stands for Radial Basis Function. The idea behind the RBF network is that you're going to take the training set and set up several important landmarks or exemplars. Then you can use this to build an automatic feature vector, which is simply made up of the distances from your test point to each of these landmarks. Once you have this, you can pass it into a regular linear classifier and train it using gradient descent like you normally would. Next, we are going to look at a funny approximation of the radial basis function, which helps it work a lot faster. What's very interesting about this method, called random kitchen sinks, is that to find the parameters of this model, you don't actually make use of the training data. The author of Random Kitchen Sinks wrote a popular blog post about how machine learning is the new alchemy, and made a reference to this method in that blog post, which caused a little bit of controversy in the machine learning community. Earlier in this course, we demonstrated how an SVM with a sigmoid kernel has almost the exact same equation as a neural network. In this section, we are going to take that idea further. Specifically, we are going to build a neural network, but instead of training the input to hidden weights, we'll instead just randomly set the weights to the input data. This will mimic precisely what the SVM is doing, although in that case the input data is not selected randomly. So that should be very interesting. Instead of backpropagating the error and updating all the weights, perhaps the weights simply making a copy of the training data is already quite good. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss a new model called the RBF network. We'll see how they are very closely related to SVMs and can in fact, under the right circumstances, be considered equivalent. Let's first look at the SVM model. For those of you who are coming here from the first beginner's corner, this will be your first look at the SVM. For those of you who went through the theoretical sections of this course, this should be a good review. So what do I mean by model? Well, I mean, what equation do I use to get from the input features to the output prediction? For example, with linear regression, my model is y hat equals w transpose x plus b. My modeling assumption is that y hat is linearly dependent on the input features x. So that's what I mean by model. I mean, what's the equation to go from the input to the output? So for the SVM, the equation I use to get from the input to the output is this. In order to do classification, we just take the sign of the output. So if h of x is greater than 0, we predict the positive class. If h of x is less than 0, we predict the negative class. As you can see, this is almost linear, except for this weird k function. Now whether you've taken the rest of this course, or you are coming from the beginner's corner, this notation is probably new to you. So I'm going to explain everything from scratch. If you did the rest of the theory parts of this course, you should be able to relate it back to what you've already learned. First, the function k is what we call a kernel function, and our choice for this kernel function, for the time being, will be the Gaussian kernel, also known as the radial basis function. As you can see, the acronym for radial basis function is RBF, which explains the title of this lecture, RBF networks. We'll explain this function in more detail later on, but for now, just know that this is the equation. It basically looks like a Gaussian with no constant term. Next, the parameters of the model are alpha and b. We can think of the alphas as weights and b as the bias term. So this is similar to linear regression, where you have w transpose x plus b, where w represents your weights and b is your bias term. Now what is this x tilde and why are we summing from 1 to L? Well, this is where the magic of the SVM happens. All the x tildes are data points, which we call landmarks or exemplars or prototypes. In SVM theory, we call them support vectors, although this has a very specific meaning. These are just important points for determining our classification rule. So when we count from 1 to L, that just means that there are L of these important points. You can imagine that for this machine learning problem, these are the important points that help to determine the decision boundary. You can see that the curves are sort of built around these points. At this point, we have to take a little digression to explain the RBF kernel further. First, if you recall, the Gaussian always takes the shape of a bell curve. Since the most outer operation is an exponential, the output of the RBF kernel is always going to be between 0 and 1. Let's consider when the output is close to 0 and when the output is close to 1. Well, let's say x is very close to one of our landmarks, x tilde. Then the distance between x and x tilde is very small, close to 0. Let's assume gamma is equal to 1 without loss of generality. We'll remind ourselves about the effect of gamma later. Well, e to the power 0 is equal to 1, so we can conclude that if x is very close to x tilde, then the RBF kernel will return a number very close to 1. Now let's consider what happens if x and x tilde are very far apart. In this case, the distance between x and x tilde is large. Let's say, for argument's sake, that they are at a distance of 5 units away from each other. In this case, we get e to the minus 5, which is equal to 0.007, which is approximately equal to 0. In other words, when x and x tilde are far apart, the RBF kernel returns a value very close to 0. Putting this together, we can see that the RBF kernel is doing a kind of feature expansion. It's almost giving us binary features. 1 meaning x is close to the landmark, and 0 meaning x is far away from the landmark. So if we pretend our feature value f sub I is equal to k of x tilde I and x, then f sub I is like a binary feature saying, how close is x to x tilde I? On top of that, our classifier is a linear function of these features f sub I. So this is just like doing a feature expansion and then applying a linear classifier on top. Let's solidify this by looking at a picture. Consider this quadratic-looking decision boundary. We can think of the red side as +1 and the blue side as -1. I've highlighted the landmark so that you can see that there are 2 red landmarks and 1 blue landmark. Let's assume our classification rule is as follows. h of x is equal to -1 times k of blue in x plus 1 times k of red 1 in x plus 1 times k of red 2 in x. Now it's important to keep in mind that this is just a rough example. Don't expect these numbers to be precise or for it to exactly fit the geometrical picture. This is only for intuition. So let's imagine that we have a test point here, which you and I can see clearly belongs to the blue side. Well, we can see that it's pretty close to the blue exemplar, so let's say that kernel gives us a value of 0.5. We can also see that it's pretty far away from both of the red exemplars, so let's say those both give us 0. In this case, h of x is equal to -1 times 0.5, which is -0.5. This is less than 0, so we predict -1, which is correct. Now let's say we have a point over here, close to the exemplar red 1. Since it's far away from the blue exemplar and red 2, those both give us 0. Let's say the kernel for red 1 gives us 0.7. Then h of x is equal to 0.7, which is greater than 0, so we predict +1, which is correct. Now let's say we have a point which is far along the red side of the boundary, but not really near the exemplars. Still, it's closer to red 1 than it is to the blue exemplar. Let's say that the kernel value for red 2 is 0.01, and the kernel for the blue exemplar is 0.001. Let's also say that the kernel for red 1 is 0. In this case, h of x is equal to -1 times 0.001 plus 1 times 0.01, which is equal to 0.009. This is still greater than 0, so we predict class 1, which is correct. In other words, these exemplars give us the decision boundary we expect. You'll notice that there's one parameter we haven't discussed yet, which is gamma. In this lecture, I'll give you the short version, but you're encouraged to check out the previous lecture titled Gaussian Kernel if you want a more in-depth explanation. You can think of gamma as the precision of the Gaussian kernel. If we have a high gamma, then we have high precision, and the Gaussian kernel is very skinny. If we have a low gamma, then we have low precision, and the Gaussian kernel is very fat. You can see that if the Gaussian kernel is very skinny, it is very conservative as to what data points should be considered close. The value of the Gaussian kernel drops to 0 very fast as you move away from the center. If the Gaussian kernel is very fat, it is very liberal as to what data points should be considered close. Even if a data point is far away from the center, you can still get a value which is significantly larger than 0. The result of this is that we can change the expressiveness of the decision boundary. When we have low precision, we can imagine that the landmarks are not very precise, so the decision boundary is smooth. When we have high precision, we can imagine that the landmarks are extremely precise. They allow for sharp corners and turns, giving you a very expressive decision boundary. You can think of this in terms of the bias-variance trade-off, or overfitting and underfitting. When we have low precision, we'll have a higher bias, lower variance, and will tend to underfit. When we have high precision, we'll have a lower bias, higher variance, and will tend to overfit. The next question I want to consider is, why is this called an RBF network? Why is this a neural network? You might see this picture a lot and assume it refers to a picture of a neural network in the deep learning sense. But this actually may not be true. In fact, the picture for an RBF network is exactly the same. Sometimes we draw these little Gaussians in the hidden layer to make it more explicit that a Gaussian kernel is being used. And with a deep learning artificial neural network, you might see little sigmoids drawn in the hidden layer to make it more explicit that a sigmoid is being used. Of course, these are arbitrary activation functions, and both networks actually have the same architecture. In addition, the operation which is occurring in the input to hidden edge is a little different as well. With regular neural networks, we're calculating a dot product between the input and some weight wi. With RBF networks, we're calculating a squared Euclidean distance between the input and some landmark xi. In some sense, the dot product and Euclidean distance are different ways of doing a similar thing. Of course, we know what Euclidean distance is. It's just the length of the line that connects 2 points in space. In other words, it tells us how close those 2 points are. What about the dot product? Sometimes you'll see the dot product referred to as cosine similarity. This is because another way of writing the dot product between w and x is just the magnitude of x times the magnitude of w times the cosine of the angle between w and x. Considering a w and x of constant length, what happens when we change the angle? Well, if w and x are pointing in the same direction, we get cos of 0, which is equal to 1. This gives us the maximum possible similarity. If w and x are perpendicular, we get cos of pi over 2, which is equal to 0. This gives us 0 similarity. If w and x are pointing in opposite directions, we get cos of pi, which is minus 1. This gives us the minimum possible similarity. So in fact, the dot product is also a measure of the closeness between two vectors. They are just different kinds of closeness. And thus, RBF networks are actually more similar to deep learning neural networks than you might have thought. One interesting fact is that the Euclidean distance actually breaks down into a dot product. If you recall, the square length of a vector is equal to the vector dotted with itself. Therefore, we can actually expand the square length term, and all we get is a series of dot products. Then we can imagine, in the deep learning neural network sense, that the activation function is the exponential of this series of dot products as its input argument. The last question I want to consider is, how are these landmarks chosen in the first place? And that's also the most important question. If we don't choose these landmarks wisely, then we'll have poor features and our classifier won't be good. So how do we choose the best landmarks possible? And more importantly, where do these landmarks come from? In fact, these landmarks are actually just data points from the training set. So if you wanted to be lazy, one thing you could do is just include all the points from your training set and sum from 1 to n. Now you might wonder, that seems very inefficient. What if my training set is large? Of course, there are other ways around this. If you took the previous theory part of this course, then you know that the landmarks x of I are actually called support vectors, and they are chosen by optimizing a quadratic program. This makes it so that the number of landmarks is much less than the number of training points we have. One problem with both of the above two methods is that they actually aren't very efficient. The first method is inefficient for the reason we already discussed. If it depends on the training set size, then it won't work for large datasets. But the SVM method is also susceptible to the same problem. It promises to only find a few support vectors, but the number of support vectors still tends to grow. This makes both training and prediction slower, as you saw when we used the SVM on MNIST, which has about 40,000 samples in our version of the dataset. In the next lecture, we'll discuss some other ways of obtaining an approximate answer for which data points should we consider our landmarks. In short, these will make our calculations more efficient while still providing the benefits of this nonlinear model. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to discuss some scalable approximations of RBF networks that are very useful for implementing RBF networks in code. You'll find that we don't actually have to implement anything ourselves unless we really want to. Instead, we can use different pieces of scikit-learn as building blocks to form what is, in total, an RBF network. As discussed in the previous lecture, one challenge with the RBF network is finding the landmarks. If we just use all the training points, that's bad, because we could have a lot of training points. If we use the SVM method, that's also bad, because the SVM can be slow for large datasets. The SVM algorithm is O of n cubed, where n is the number of training points. Luckily, machine learning offers some good approximations to this process. It's helpful to think of the RBF network as a two-stage process. I discuss this a lot in deep learning as well, so if you've taken my deep learning courses, then this should be very familiar. The idea is, our two stages are as follows. Stage number 1 is feature extraction. This converts our input data x into a new representation. In the previous lectures, I referred to this as f, or phi of x. It doesn't really matter what letter you want to give it, since this is all abstract. Stage number 2 is to input the features you found into a linear model. So for example, you could use logistic regression for classification, or linear regression for regression. It might help to think of it in terms of scikit-learn code, since we saw how to write such code earlier in this course. If you recall, the class we need when we want to chain multiple scikit-learn models together is the pipeline class. The only requirement is that everything before the last model must be a feature transformer and not a supervised model. So for example, if my input is some text, I might create a pipeline that performs a TF-IDF transformation and then does naive Bayes. If I wanted to model some polynomial function, I might create a pipeline that does a polynomial feature expansion and then does linear regression. Of course, the reason I'm mentioning this is that there are feature transformers for the RBF kernel as well. The first one I want to discuss is called the RBF sampler. However, its name is a little misleading. Just by looking at its name, what does it sound like it does? Well, I'll tell you what I think when I see it. It sounds like, since choosing all the training points will be slow, then what might be a little faster is to randomly sample a subset of those training points. That should pretty trivially make things go faster. Perhaps we could even intelligently select a random sample, perhaps by trying to find data points which are close to data points from another class. In reality, the RBF sampler does none of this. In fact, it doesn't even use the input data you pass in at all. So when you call rbfsampler.fit, it actually ignores the x that you pass in. The way that the RBF sampler really works is actually quite hilarious. Let's start by reviewing kernels. As you recall, a kernel machine involves some linear function applied to the output of the kernels, evaluated at each training point against the test input. The kernel function is meant to be a faster way of calculating the dot product between xi and x after they have been transformed using some feature expansion phi. This is nice for us because we can make it so that phi has very large dimensionality, up to infinite dimensionality in the case of the Gaussian kernel. We can do this because we never have to explicitly calculate phi. If we did want to calculate phi, then our model would simply be W transpose phi of x plus b. As we discovered earlier in this course, this becomes very hard for features such as polynomial expansions, because the number of features explodes as our input dimensionality and degree of the polynomial increase. In the case of the Gaussian kernel, this would be impossible to compute. So that's nice. The kernel trick allows us to never have to explicitly train this linear model at all. Except it's not really that nice, because if the number of training points is large, say n, then the kernel matrix for the training set will be of size n by n. So what machine learning researchers decided to do was go backwards. Instead of applying this nice new trick called the kernel trick, how about if we invent an even newer trick in which we never have to calculate the kernel? Suppose we could come up with an approximate feature transformation z so that it very closely gives us an approximation of our kernel, but not exactly the same. Then we can approximate our kernel with the dot product of z. Except remember that the whole point of doing the kernel trick was to apply a linear model on top of the infinite feature expansion phi. So we're looking for some model like W transpose phi of x plus b, which is hard to impossible to calculate. And now we can approximate this with z, W transpose z of x plus b, which is easy to calculate. Using this low dimensionality feature expansion z, we can avoid ever having to calculate the n by n kernel. So this is pretty amusing. Our solution to the problem that calculating the kernel is too slow is to just go back to what we were doing originally. Going back to the RBF sampler, what is interesting is that it doesn't use the input you pass into the fit function. The reason why this works is far beyond the scope of this course, but I've attached the author's blog post, as well as a couple papers in extrareading.txt for your reading pleasure. You are also encouraged to look at the source code for the RBF sampler, since of course the entirety of scikit-learn is available on GitHub. What is interesting is that even though this method is a few years old, it recently resurfaced as the author of the blog post, who also happens to be the person who invented random kitchen sinks, was actually trying to make a much more controversial claim in his blog post. His main point was that machine learning is the new alchemy, and this got him into a debate with deep learning pioneer Yann LeCun. There is another approximation to the RBF kernel included in scikit-learn, which is worth mentioning since it is just as easy to plug and play as random kitchen sinks. This one is known as the Nystrom method, and it also specializes in doing feature approximations for kernel machines. The math for this is again outside the scope of this course, but some relevant papers are attached in extrareading.txt if you want to have a look. The short story is, it does an eigendecomposition and low-rank approximation of the kernel matrix, also known as the Gram matrix. And of course, since it's just a regular feature transformer implemented in scikit-learn, it is completely interchangeable with the RBF sampler. In other words, it's as easy to use as commenting out one line and uncommenting another. So we'll be playing around with both in our code, and you're encouraged to do so as well. Hey everyone, and welcome back to this class, Support Effective Machines in Python. In this lecture, I want to consider a funny little paradox for those of you who took the theory part of this SVM course. Earlier, I claimed that the Gaussian kernel gives you an infinite dimensional feature expansion. But now that we look at the RBF network, you might think that this is not the case. If you recall, we can only have up to n landmarks, and if we have n landmarks, that gives us n features. So how can we simultaneously have n features and yet have an infinite number of features? The answer is, it's all a matter of perspective and what you consider to be a feature. The difference is this. In the RBF network section, we considered the features to be the output of the kernel functions. So f sub I is equal to k of xi and x. But in the SVM sections, we considered the features to be implicit in the kernel. If you recall, a valid kernel can be expressed as a dot product of feature expansions. So is f the feature or is phi the feature? That is the difference. Here's another way to see that both ways of thinking of the model are valid. If we consider the classifier to be a two-stage model, where stage 1 is the feature expansion and stage 2 is the linear transformation, then for the RBF kernel, this is what we have. The features, all the f sub i's, are equal to k of xi and x. Then we perform a linear transformation on these f of i's. So another way to write this is just alpha transpose f plus b, where alpha is a vector containing all the alpha i's, and f is a vector containing all the f of i's. But in the SVM case, we can rearrange the equation a little bit by separating out the phi's. Just let the sum over I of alpha I times phi of x of I to be another vector, call it alpha prime. Then we simply get another linear equation, alpha prime transpose phi of x plus b. To summarize, we have solved this paradox of how our RBF network could have an n-dimensional feature vector and an infinite dimensional feature vector at the same time. We discovered that it really depends on what you consider to be the feature. Is it the output of the kernel function, or is it the implicit feature expansion being calculated by the kernel function? Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to look at some code which can be used to build your very own RBF network. The relevant file in the course repo is rbfnetwork.py. To start, we're going to import a whole bunch of stuff. Mainly, we need our dataset, which is mnist. We need the pipeline class. We need the RBF approximations, which are the RBF sampler and the Nystrom approximation. We need the standard scalar. And finally, we need a linear classifier. I've included one from scikit-learn called SGD classifier, although you might also want to test out linear SVC. Linear SVC will be slower than SGD classifier because it still has to solve the SVM problem, but it is faster than the regular SVC class because it assumes your support vector machine is linear, and so it calculates the weights directly. We also have a class called feature union. You'll see how that will be used very shortly. So the first thing we do is load in our data. This gives us xtrain, ytrain, xtest, and ytest. Next, we are going to build our pipeline. As you can see, I have a whole bunch of stuff commented out. These are just some examples of some of the ways you can mix and match these objects we've imported. So one way is just to use the SGD classifier by itself. That's this one. You can use that as a sort of baseline. You can also use the linear SVC by itself. Check whether or not this performs better than the SGD classifier. Also compare its speed. Next, we use an RBF sampler in conjunction with the SGD classifier. So that's this one. So the RBF sampler does the feature extraction, then the SGD classifier does a linear classification on the features. Next, I show you how you can actually use multiple RBF samplers at the same time. So that's this one. Now, why would you want to do this, you might ask? Well, consider the fact that you have to choose the hyperparameter gamma. You might use cross-validation to choose the best gamma. But what if different gammas are best based on different areas of space where the training points live? So the feature union object allows you to use multiple RBF samplers in parallel. In other words, you're sort of gluing them together to create a new, giant feature extractor that does multiple things at once. The last two things we have are a pipeline with the Nystrom approximation, and then the very last one is a feature union of multiple Nystroms, ending with a linear SGD classifier. This is the one we're going to use in the lecture. Of course, you are very strongly encouraged to mix and match different feature extractors and models on your own, and test your own hyperparameters. The last thing we do is what we usually do. Fit on X-train and Y-train, then calculate the train accuracy and the test accuracy. So let's run this and see what we get. So as you can see, we do quite well, about 95%. As an exercise, you might want to check how this compares to a pure linear classifier. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to further explore the relationship between SVMs and neural networks. Earlier, we assumed that we would use the Gaussian kernel with the SVM, but this need not be the case. As you recall, we discussed earlier in this course that it is also possible to use what is called the sigmoid kernel, which actually refers to the tanh function. Of course, this has a direct relationship with neural networks. Let's look again at the equations for the SVM and neural network side by side. In this table, you can see I've renamed some of the letters, which are conventional in neural network literature, to something more like SVMs, so that the two columns appear more similar. So how do we get from the input layer to the hidden layer? For the SVM, we take an input x, multiply it by some landmark x of I, and multiply it by a constant gamma. Then we add some bias term r, and then take the tanh. For the ANN, we have something very similar. We take an input x, multiply it by some weight vector w sub I, add a bias term r sub I, and take the tanh. The difference between the two is that for the SVM, gamma is a hyperparameter chosen by yourself, and x of I is a landmark chosen from the training set using some method such as quadratic programming. For the ANN, the weight vector w sub I is updated using gradient descent. For the bias term, it's similar, but for the SVM, we only have a single bias term, which is the same for every landmark. It's yet another hyperparameter that you can choose. For the ANN, it's again learned by gradient descent. For the hidden to output layer, we have something very similar on both sides. For the SVM, we sum over all I, and we multiply the feature by y of I times alpha sub I. Then we add the bias b and apply the sine function. For the ANN, we sum over all I, multiply each feature by the weight alpha sub I, then we add the bias b and apply the sigmoid function. As you recall, the sine function and the sigmoid function are also very similar. The sine function is like a piecewise approximation of the sigmoid, whereas the sigmoid is like a smooth, differentiable version of the sine. Of course, they are at different scales, since in SVM we usually use the targets +1 and -1, whereas with neural networks we use the targets +1 and 0. Other than these minor differences, you can see that the two models are actually very close. One interesting experiment that is worth considering is, for the input to hidden layer, what if we didn't learn the weights using gradient descent? What if, instead, we just use the training data? That seems to make sense, since that's what the SVM does. One thing that's difficult is choosing which data points we should use as our quote-unquote weights. So our experiment is going to be to create a regular feed-forward neural network, but do not train the weights using gradient descent. We're instead just going to take some x-i's from the training set. In the following code example, I've experimented with 3 methods. If you're only here for the beginner's material, you can skip the reasoning as to why these choices make sense. But if you worked through the theory behind the SVM, then you'll find it easy to follow along. The first method is just to choose randomly. This doesn't sound like it'll work well, but it actually works just as well as the other methods, which only makes sense theoretically. The second method is to apply k-means clustering. The reason we want to do this is because it'll give us some separation of the data. Once we've established some unsupervised labels on the data, we can then look at those points which are the most ambiguous. The ambiguous points would be the points which are about an equal distance away from all the cluster centers. In order to get some intuition for this, imagine you have 2 clusters. If your data point is right in the middle, you don't really know which cluster it should belong to. Whereas if your data point is very close to one cluster center and far away from the other cluster center, then you are very certain which cluster it belongs to. We can quantify this with variance. Low variance means that the distance between a data point and each cluster is about the same. Large variance means that the distance between this data point and each cluster are very different. So we can sort each data point by variance and grab the ones with the lowest variance. Those will be the ones we call the most ambiguous points. And just a reminder, to really understand why we'd want to choose the most ambiguous points, you would have had to go through the theory part of this course. The third method is to apply a similar algorithm to k-means clustering, called the Gaussian mixture model. This is like a superpowered version of k-means clustering, which allows you to have different sized and different shaped clusters. In k-means clustering, all your clusters have to be spherical, and all the spheres have to be the same size. In addition, the Gaussian mixture lets you have probabilistic cluster memberships. So you can be 50% part of cluster 1, 20% part of cluster 2, and 30% part of cluster 3. These add up to 1 because they are probabilities. Whereas k-means gives you the distance between each data point and each cluster center, the Gaussian mixture gives you something that might seem to be even better. It gives you the probability of belonging to each cluster. With k-means, we use variance to measure ambiguity, but with these probabilities, we can use a similar measurement called entropy. Entropy tells you how much uncertainty you have in a probability distribution, so that works in our case. Now, in reality, I'm just using what scikit-learn gives me. The k-means clustering class happens to give me the distance between every data point and the cluster centers, so that's what I used. And the Gaussian mixture class happens to give me the cluster probabilities for each data point, so that's what I use there. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to implement our neural network SVM mashup. Basically, we're going to run the experiment we just discussed in the previous lecture. What happens if, instead of learning the input to hidden weights using backpropagation, we just choose them randomly, or use some unsupervised method, such as clustering? The relevant file for this lecture is fakeneuralnet.py. At the top, we have all our usual imports. Really, the only new things here are the k-means class and the Gaussian mixture class. We also have scipy.stats, which includes a function for calculating the entropy. Next, we have the most relevant portion of this file for this lecture, the sigmoid featurizer. As discussed, the job of this class is to choose random points in the training set to save as static weights. Then, during prediction, we'll dot the input with these static weights and apply the tanh. In the constructor, we take in 3 things: gamma, the kernel multiplier, and components, which is the number of samples to choose, and method, which will determine how we choose the samples to keep. Method must be one of these four values: normal, random, k-means, or GMM, which will be explained very shortly. Next, we have a function called subsample data. This is necessary because k-means and Gaussian mixture actually take quite a long time to train on the full MNIST dataset, so it's easier and faster to just do it on a subset of the data. Next, we have the fit function. Now, it might look odd that this takes in a y argument, but this is actually part of scikit-learn's interface. You can't actually use this in a pipeline if this argument is not present. The first two methods are pretty trivial. If we choose random, we just select m random training points and save them to the attribute samples. If we choose normal, we do something even more simple. Just draw samples from the normal distribution without even considering the data at all. This would be equivalent to having a regular feed-forward neural network, but not bothering to train the input to hidden weights. Next, we have the non-trivial methods. First is k-means. The first step is to subsample the data, since, as we discussed, this part will go quite slow if we don't. Next, we create a k-means object with the number of clusters equal to the number of classes in Y. So it turns out that the y argument into this function is useful after all. Then we call fit and we print out the training duration. Next, we would like to calculate the most ambiguous points. These will be the points with the least variance. So the first thing we have to do is calculate the distance between each data point and each cluster center using the transform function. This gives us back an n by k matrix. Next, we calculate the variance for each training point by calling the var function. Then we get the sort indices by calling the argsort function. Next, we take only the first m indices corresponding to the smallest m variances. Finally, we index x using our indices and assign that to our samples attribute. Next, we have the GMM method, which is largely the same. First, we subsample the data, since GMM can be even slower than k-means, depending on which options you choose. Next, we create a Gaussian mixture object and fit it. By the way, the GMM algorithm is outside the scope of this course, but if you would like to know about these parameters I chose, you are welcome to ask about it on the Q&A. The next step is to select the most ambiguous points from the perspective of the GMM. First, we calculate the probability that each data point belongs to each cluster using the predict_proba function. This gives us an n by k matrix of probabilities. Then we call the scipy entropy function. Note that this function calculates entropy down the columns by default, so we actually want to transpose the inputs first. Next, we get the sort indices of the entropies. In this case, we want the entropies to be sorted largest to smallest, so we negate the entropies. This is because high entropy corresponds to high uncertainty. As before, we select the top m indices and then use those to get our samples. So that's the end of the fit function. For the transform function, we're doing the sigmoid kernel. So we take the input x, dot it with our samples, multiply by gamma, and apply the tanh. Lastly, we have the fit transform function, which just does both fit and transform. Next, we have the main section of this script. As usual, we load in our data, create our pipeline, and evaluate our model. In this pipeline, I tried both the SGD classifier and logistic regression, which are both linear classifiers. I found that SGD classifier works faster, but logistic regression, at least with the default settings, works better in terms of classification rate. So you are free to try different linear classifiers in different hyperparameters here if you want. Next, I decided to do something a little different. Instead of calculating the test accuracy once, I decided to do cross-validation, which of course we saw earlier in this course. So let's run this and look at the results. So as you can see, each method appears to perform comparably, and they all perform better than a vanilla linear classifier. What's interesting is that they also all perform better than choosing the weights randomly. So it would seem that choosing weights as your data points actually does something useful. Hey everyone, and welcome back to this class, Support Vector Machines in Python. In this lecture, we are going to conclude and summarize everything we learned in this section. This section was all about how to view the SVM as a neural network. We saw that architecturally, the SVM can be drawn exactly the same as a usual feed-forward artificial neural network. The only difference is how we map the inputs to the hidden layer. That is, instead of simply dotting the input with a weight, we apply a kernel function, which is like a different kind of feature extractor. When we use the Gaussian kernel, we get the RBF network. We learned that the idea of RBF networks makes SVM scalable because we don't have to rely on the kernel trick, which makes our algorithm at least n-squared complexity. This idea is powerful because the SVM is a complex optimization problem, but the RBF network is not. All we have to do is approximate the kernel function, and we get a standard two-stage procedure. Stage 1, feature extraction. Stage 2, linear classification. We learned about two approximations to the RBF kernel, the random kitchen sinks method and the Nystrom method. Finally, we looked at what would happen if we used a sigmoid kernel instead. We saw that this looks even more like a traditional ANN. The main difference being that the input weights are not parameters learned by backpropagation, but rather are just data points from our dataset. Normally, we would consider these data points to be landmarks or exemplars or support vectors, which are chosen using the methods discussed previously in this course. In this section, we did an interesting experiment which asked, what if we just chose those points randomly? We found that doing so, we can achieve a classification accuracy significantly better than a linear classifier by itself. That's pretty neat because one might assume that features should be intelligently chosen, that there should be some reason behind them, and yet choosing randomly seemed to work. To be clear, it didn't provide the best results for that architecture, but the results are decent considering that it's like a neural network where you didn't update any of the input weights. Hey everyone, and welcome back to this class. In this section, I'm going to go over some common questions that students have, and some general tips that have helped students in the past. Please keep in mind that this is not a core part of the course. These are just common general questions that students have had about machine learning or about my courses in general. I realize that it's not useful for everyone, but please keep in mind that it's useful for someone. There are a few people out there that tell me they think all the lecturers should only answer their questions, but not anyone else's questions. So just keep in mind that many of your fellow students have asked me these questions in the past. And in order to answer those questions in a scalable way, I've created this section. Please try not to hold it against me, as this may not directly help you, but it may help your fellow students. Please also keep in mind that the appendix section in no way takes away from the core content. All the material provided for the topic matter is exactly what I wanted to provide. These appendix lectures are simply extra stuff. So these appendix lectures do not displace any technical content. If the appendix section did not exist, the technical part of this course would be exactly the same as it is now. So just remember this, the appendix is in addition to the technical content. It does not displace any technical content. You get all the technical content that I intended. Also keep in mind that you are always able to select the lecture you want using the user interface. That's this thing. If you don't know how to use the video player to select a lecture, please ask me how on the Q&A or contact Udemy support. So you're encouraged to select the lectures you want to watch manually and skip lectures you don't want to watch. Also keep in mind, however, that a common mistake is in thinking that this material is not going to help you, when in reality it will. For example, I come across students all the time who have no idea how to get started implementing machine learning algorithms in code or why we are doing so in the first place. Then I come to find that they have never watched How to Code by Yourself. So I think it goes without saying that if you don't know how to code by yourself, you should probably watch the lecture How to Code by Yourself. Same thing goes for the other lectures in this section. Alright, let's get to the lectures. Hey everyone, and welcome back to this class. In this lecture, I'm going to go over a better way to install data science and machine learning libraries for Python for Windows users. Historically, Windows users have had a lot of problems installing this stuff. Luckily, these days there is an option that makes things very painless and just as easy as they are on Linux or Mac. That is Anaconda. In fact, even if you're not on Windows, you can still use Anaconda. It's nice because it isolates your environment from the defaults provided on your system. So for example, you can have Python 3 in Anaconda, but Python 2 as your system default. When I first started these courses, I wasn't keen on Windows since there were a few essential libraries that couldn't be installed on Windows without a significant amount of effort, if at all. In my view, anything beyond a couple of lines in the console or clicking an install file is too much. And believe me, some students even have trouble with that, so it's good not to make things too complicated before you can even begin the course. Nowadays, that has changed. It's a lot easier to install things on Windows, in large part thanks to Anaconda. And so this lecture is all about how to install all the data science and machine learning libraries you'll need on Windows using Anaconda. So in this lecture, I'm going to walk you through how to install Anaconda as well as some of the libraries you might need that don't already come with Anaconda. You'll find that most of the common libraries such as NumPy and SciPy are already included, so if that's all you want to use, then for you it's just a one-click install. On this slide, I'm going to give you a super short summarized version of this lecture, so you don't have to walk through the installation with me if you don't want to. For some people, that really helps since you can see it, but if you can do it on your own, feel free. So, number 1, download and install Anaconda. This is just a one-click install. It already includes NumPy, SciPy, Matplotlib, and Pandas. That's all we need for the NumPy stack in Python, linear regression, and logistic regression, and a few more courses. It also comes with NLTK, which is what we use for NLP, and scikit-learn, which has some pre-built machine learning models. Now, even though this stuff comes by default, you can still update them if you want. So you can do conda update NumPy, for example, and that will update NumPy. Number 2, install deep learning libraries. We've got pip install TensorFlow, that's going to install TensorFlow. And if you want to install Keras, you have to first do conda install pip, which is going to update pip, and then you can install Keras using pip install Keras. If you don't update pip first, you might get an error. Next we have CNTK, which is Microsoft's deep learning library. So you do pip install and then the CNTK URL, which you can get from Microsoft's website. So I'm not posting any URL here because the version could likely change in the future, and so you just Google search how to install CNTK and you can get a URL just like this. Next we have PyTorch. That's pip install -c peterjc123 PyTorch. After that we have Theano, so that's conda install Theano, or conda install Theano PyGPU if you have an NVIDIA GPU and you've installed the CUDA toolkit already. Number 3, install OpenAI Gym. That's just pip install Gym. If you want to be able to play Atari games also, then that's more involved, so just skip to the end of this lecture where I walk you through that. If you want to play and save videos using OpenAI Gym, then you also have to install FFmpeg. So the first thing we're going to do is go over to the Anaconda website. That's anaconda.com/download. Scroll down to the Windows section and click on either Python 3.6 or Python 2.7. Or if you're watching this lecture in the future and there's a new version, get that. The code in my courses is compatible with both Python 2 and Python 3, so in that regard, it doesn't really matter which one you get. In the lectures, you might see Python 2 code, but the best way to make sure you're seeing the latest version is to git pull inside the course repo. So make sure you're always doing that because I'm constantly making new updates. Now, although Python 3 is newer, there are still reasons to use Python 2. For example, in your work, you might use Python 2, or certain platforms like Google App Engine only support Python 2. So if you're running a web app there, that means you're stuck with Python 2. It does have great scalability features, so there are many good reasons to use Google App Engine. If you want to get more insight on whether to choose Python 2 or Python 3, just check out the appendix lecture, Python 2 versus Python 3. So now that we've downloaded the install file, all we need to do is click on it. That's what I mean by one-click install. You click on this, hit OK a few times, and everything is done. Unfortunately, I gave my username a space, which kind of sucks, but that's what happened. So I'm sure some of you have a space in your username too, so if I come across any issues, at least you'll know what to do. Alright, so everything's installed. So essentially everything except the deep learning libraries have already been automatically installed. So you don't need to manually install NumPy, SciPy, Matplotlib, Pandas, IPython, or scikit-learn. So if you're taking my NumPy course or any course that doesn't use modern deep learning libraries, you already have everything you need. So let's go into IPython and make sure that's the case. To start IPython, I go to the Start menu, type in Anaconda, and then this Anaconda prompt application should pop up. Actually, it should pop up before you even finish typing Anaconda. So we go into there, and this brings up a command line terminal. Next, just type in IPython. After that, we can import all the libraries I mentioned earlier. If we don't get an error, that means they've been installed successfully. So let's try something simple like generating some random numbers and making a plot. Okay, so that's a plot of random noise. Let's make a histogram too. Okay, so we see a normal curve just like we expect. Now you can see that TensorFlow is not installed, which is why we get this error. But we can install it very easily by exiting IPython and then typing in pip install TensorFlow. Next, let's try to install Keras. So we get this error. So I looked this up and determined that we need to update pip. So let's do that by typing in conda install pip. Conda kind of works like pip in that way. They are all just tools for installing stuff. Okay, now let's try pip install keras again. Alright, so everything works. Next, let's try to install NLTK. This is used in my NLP courses. So it looks like it's already installed, so there's nothing more to do. Just keep in mind, if we come across a library you don't care about, feel free to ignore it. I find it's useful just to install everything at the same time so that when you're deep in the code later, you don't have to think about stuff like this. So the next thing we'll install is CNTK. This is Microsoft's deep learning library. Notice how it's not part of pip, so you need to grab the URL manually from Microsoft's website. Unfortunately, it's a little hard to find because there are many pages that deal with how to install CNTK on Microsoft's website, but what you're looking for is a page that has a link to a WHL file. So copy and paste that after pip install. This is a good example because it shows you another way you can use pip by doing pip install and then a URL. Next, let's install PyTorch. This requires us to use a custom source, so we have to specify the option -c peterjc123. So that's conda install -c peterjc123 PyTorch. This is because a very nice guy called peterjc123 has provided us with a version of PyTorch that works on Windows. And once that's all done, we can verify that they've been installed correctly by going back to IPython. Alright, so TensorFlow works. Keras works. NLTK works. CNTK works. And Torch works. Next, let's install Theano. Theano has historically been pretty difficult to install on Windows, but nowadays, that's not the case. So if you go to their website, you'll see a bunch of instructions. If you don't want to use the GPU or you don't have a GPU, then the instructions will be very easy. I don't have a GPU on this machine, so I'm going to do the easy version. Keep in mind that Theano is really great for learning purposes, so it's totally fine, even if you have a GPU, to just install the CPU version for now and then use the GPU version of TensorFlow. Now I ended up upgrading MKL service and libpython since that's what they told me to do on Theano's website, but it looked like these were already installed. In fact, updating MKL service gave me an issue later, so we'll have to fix that. So if you want to install Theano for CPU only, that's conda install Theano. If you want to install Theano for the GPU, then do conda install Theano PyGPU. Now let me go into IPython and check if Theano works. So we get an error because of this MKL service thing that I mentioned earlier. So let's set this environment variable it's telling me to set. By the way, this is great to know if you don't yet know how to set environment variables on Windows. We can also check that it worked by using the echo command. So let's try that again. Let's do a simple example of adding two numbers in Theano, just to make sure everything's working. If you want to do something even more complicated, you can run this script from Deep Learning Part 2, which doesn't require any external dataset. So just go over to the folder ANN class 2 and type in python gridsearch.py. So that's going to look for hyperparameters using cross-validation. Now in this last section of this lecture, we're going to talk about reinforcement learning. When we start studying reinforcement learning, there is yet another library we'll need to install called OpenAI Gym. If you don't plan on learning reinforcement learning, you can skip this part of the lecture. This has also historically been very difficult, but luckily the open source community has put in the work so you don't have to. You're welcome to read through the GitHub issue on this if you want, but I'm going to just do the simplest thing that works. So let's first do pip install gym. Great, so that worked. Now the second command is a bit longer, so let's go to the actual GitHub issue and copy and paste the command. The easiest way to get there is just to go to Google and type in install OpenAI Gym Windows Anaconda or something along those lines. So let's paste that in. And notice how it fails since I haven't yet installed Git. So we can install Git by doing conda install Git. Now let's try it again. Unfortunately, this fails again because we need GCC, which is a C compiler. Now, one way to get GCC is to do conda install m2w64 toolchain. But unfortunately, I tried this and it also doesn't work. In fact, I think this toolchain was installed already. So I tried quite a few things that didn't work. So in order to save you some time, I'm going to recommend you only try the stuff on this page if everything else doesn't work for you. So what worked for me was to just grab the precompiled binary directly. Now in order to do that, you'll want to go to Cojoli's GitHub repo directly. So that's this URL here, github.com/kojoli/atari-pi/releases. Next, you'll want to download the WH file that matches your environment. So I have Python 3.6 on a 64-bit installation of Windows, so this is the file I want. Luckily, we already discussed earlier in this lecture how to install a WH file. That's just pip install and then the path to the file. So let's do that. Now we can test our installation by running a script that requires an Atari game. So let's cd over to rl2 and then Atari, and now let's run dqn_tf.py. Cool, so everything's good. Now the final thing we want to do for OpenAI Gym is if you want to play a video or save a video, you want to install FFmpeg. So to do that, you want to type in conda install -c menpo ffmpeg. Once you've done that, you can go to the cartpool folder and type in python saveavideo.py, and this will run a script that will play the cartpool game, show a plot, and then save a video. And of course, you can also play this video by just navigating to the file and clicking on it. So for now, that's everything. If I need to add new libraries or updates to this lecture, they will be appended at the end. Hey guys, in this lecture I'm going to show you how to set up your development environment so that you can follow along in these courses. First, let's talk about operating systems. The three big ones are Windows, Linux, and Mac. Most, but not all of my courses are part of the deep learning series. Eventually, the deep learning models we're going to build will become so complex that we will need specialized libraries like Theano and TensorFlow to implement them. Now, as of today, Theano and TensorFlow are not officially supported on Windows. So if you are interested in deep learning, you will discover pretty soon that there is not much you can do without a ton of work. Even working with non-GPU enabled libraries like NumPy and Matplotlib can be a challenge, but these are at least possible on Windows. If you really must use Windows and have your Python environment inside Windows, and you don't want to try the virtual machine method, which I'm going to discuss next, then one good library I know of is called Anaconda. You can get Anaconda at continuum.io/downloads. I can't vouch for this 100% because I haven't used it myself, but I've known others who have found it at least usable. Now I'm telling you this from experience. I've worked with a ton of clients one-on-one, and Python development, especially when it involves the NumPy SciPy stack, is not easy when it's on Windows. The method I'm going to describe using virtual machines will work on most modern computers, and as of right now, if you want to do any deep learning stuff, whether that be with Theano or TensorFlow, you cannot do this on Windows. With that out of the way, I'm going to quickly go over which courses I've released so far or plan to release in the near future that do not require Theano and TensorFlow, so it's possible to do on Windows. With these in mind, you can decide if you want to install a virtual machine or not, but I would highly recommend it because it's free and everyone can follow the same instructions. So we've got linear regression in Python, logistic regression in Python, which are the prerequisites to deep learning part 1. Then we have deep learning in Python part 1, which is mostly in NumPy and a little bit of TensorFlow. We've got easy natural language processing in Python, data analytics, SQL for noobs, beginners, and marketers, cluster analysis and unsupervised machine learning in Python, and unsupervised machine learning, hidden Markov models in Python. This course is going to have a little bit of Theano in it. Next, here are some courses that depend heavily upon Theano or TensorFlow or both. We've got practical deep learning in Theano and TensorFlow, convolutional neural networks in Python, unsupervised deep learning in Python, and recurrent neural networks in Python. As you can see, a lot of interesting and complex stuff can be done in Theano and TensorFlow. Alright, so hopefully I've convinced you that using a virtual machine is a good idea. Windows is a great operating system, but it tends to not be as developer friendly since it tries to be more consumer friendly. Note that if you're on a Mac, this probably isn't necessary. you can just install NumPy, SciPy, Pandas, Matplotlib, Theano, and TensorFlow using easy installer pip. Sometimes this stuff can fail depending on the many combinations of versions of each thing that are possible, but usually just Googling your error message will lead you to the right solution on Stack Overflow. If you're on a Mac, you can just do sudo pip install NumPy, SciPy, IPython, Pandas, Matplotlib, and Theano. Alternatively, you can use easy install, which might have a more recent version. You may need to use easy install to install pip itself, which is just sudo easy install pip. If you want to install TensorFlow, just copy the command at tensorflow.org. It's just a pip install command that points to their custom installation location. I won't put it here since it corresponds to a specific version, and that version may become out of date by the time you watch this. That is good news because the people working on TensorFlow are updating it all the time. Alright, so if you've made it this far, that means you want to install a virtual machine with Linux on Windows, or that you're already using Linux and you want to know what commands to use to install these libraries. We are going to need two things to start for this tutorial: VirtualBox and a lightweight version of Ubuntu. I would recommend Xubuntu or Lubuntu. I'm going to use the 64-bit version of Lubuntu for this tutorial. So download these first and then return to the tutorial. Alright, so now that you've got VirtualBox installed, we're going to create a new machine with 64-bit Lubuntu. So you want to hit New, type in a name for your machine. And this stuff is already correct. I'm going to choose 2 gigs of memory. You can choose more memory if your computer has more memory. I'm going to create a virtual hard disk now. I'm going to choose dynamically allocated, and 8 gigs is good enough for this example. Alright, so I'm going to go to settings. If we go to storage, you can choose the ISO file that you downloaded. So I'm going to load up the Lubuntu ISO that you downloaded from lubuntu.net. Alright, so hit OK and hit start. Okay, so it's going to take you through the installation of Lubuntu. So you want to hit install. Alright, so Lubuntu is going to take you through some prompts. Alright, so you want to erase disk and install Ubuntu, and I'm not going to check any of these. Just hit continue. Alright, so once that's done, it's going to ask you to restart. So just hit restart now. Alright, now that you're in the machine, what I always like to do, if you notice how this window is too big for my Mac window, you can make the inner window resizable by installing guest editions. And this also lets you do useful things like cut and paste between machines. So you want to open a terminal, you go to System Tools, select LX terminal. Now I'm going to cd into that folder. Cool, so the correct command was sudo /vbox linux editions.run. Notice how there was something that failed in there, so we need to install GCC. So you want to run sudo apt-get update, and then run sudo apt-get upgrade. So the next thing is you want to sudo apt-get install build essential. Alright, once you've done that, we can try to run VBox Editions again. So that's sudo /vbox linux. Alright, so everything worked this time, so we're going to restart this machine. Alright, so now the window is only as big as I want to drag it. Okay, so now we can install the actual data science stuff. So you want to open again LX terminal, do a sudo apt-get update again. Now you want to install, it's a long list, so Python NumPy, Python SciPy, Python matplotlib, IPython, Python pip, Python dev, and Python setup tools. Just hit yes. Alright, so now that that's installed, you can test it out. You can type in IPython. So IPython is open. Import NumPy. NumPy is working. Import SciPy. Import pandas. Right, we don't have pandas yet. We will install that next. Import matplotlib. Cool, so we have everything we've installed so far. So now we're going to install pandas and Theano. So that's pip install ---- upgrade pandas Theano. Alright, so now we've got Theano. The last thing we need is TensorFlow. To get this, you guys want to go to the TensorFlow website and just grab the latest command, since they're updating the package all the time. So let's open a browser. Let's search for install TensorFlow. Alright, so you take this code, copy it, you paste it into here. Alright, now you've got Theano and TensorFlow. You can test them out. Go to github.com/lazyprogrammer/machine learning examples. All right, so you need Git if you want to check out this code with Git. So let's install Git. All right, so let's run our clone command again. Let's try the HTTPS version. Okay, so this one works. All right, so use cd into machine learning examples. Go into ANN class 2. So this has some introductory TensorFlow and Theano code. So just run Python theano1.py since this does not require any data. Cool, so it seems everything is working. Now let's try the TensorFlow example. So it's TensorFlow 1. Alright, so you want to make sure you install the correct TensorFlow. You want the CPU only version. Hopefully it just overwrites the other version without any trouble. Cool, so let's try the example again. Super, so now everything is working. Now if you want, there is a text editor that I highly recommend. It's called Sublime Text. So you hit download. You go to Ubuntu 64-bit. You save this. And it will automatically be installed. All right, so now you have the exact same text editor that I use in my lectures. So you open machine learning examples, and this is all of our code. Hey everyone, and welcome back to this class. This lecture is designed to answer some common questions I get about how difficult this course is and where it fits in terms of academia, the professional world, and its practical applicability. So rather than answering this question individually over and over again, it seems like a better idea to make a lecture about it and answer everybody at the same time. A lot of people become confused because this is their first machine learning course and they just don't know where it fits in the grand scheme of things. So is this course academic or practical? And is it for beginners or experts? Is it fast-paced or slow-paced? I'm going to answer the second question first. Is this course for beginners or experts? Interestingly, the problem with this question is a problem for machine learning too. Let me explain why this question is itself problematic. One of the challenges in natural language processing is that of ambiguity. When someone says some words, the problem is those words can mean multiple things. And it just so happens that I have some courses on NLP, so this is a problem I think about often. So how does that apply here? Well, when we use the words beginner and expert, we have to ask, a beginner from whose perspective? An expert from whose perspective? For some of you, you might think that a beginner is a random person you take off the street who knows nothing. But even that is ambiguous. There are people out there who do not even really know how to use a computer beyond turning it on and checking their email and browsing the web. There are people out there who are pros at Microsoft Office, so they know how to use a computer and make a Microsoft Word document or a spreadsheet, but they've never done any programming before. There are people out there who are very good developers and have lots of programming experience, but they have no idea what machine learning is. So all of these people are beginners in some way, but each of them would require a vastly different amount of work to prepare for this course. It's the same situation with experts. Most people consider anyone who knows more than them to be an expert. But of course, how much you know and how much some other person knows is relative. If you know how to plug and play into scikit-learn and nothing else, you might seem like an expert to someone who only knows Excel, but you'll seem like a beginner to someone who's read Bishop's Pattern Recognition and Machine Learning book. So just to finalize our answer to this question, is this course for beginners or experts? This question is misinformed to begin with because beginners and experts are not well-defined terms. Instead, we have to go back to what is the specific skill set you need before starting this course. And of course, that's defined by the prerequisites which are listed in the course description. So precision is the key here. We want to know what is the precise list of skills that I need before taking this course. This is much better than ambiguous terms like beginner and expert. Another matter is that people are going to measure their own skills differently. That's a much tougher issue to deal with. Sure, I can say you need to know Python coding before starting this course, but you can be sure that there's a big difference between someone who just learned Hello World and for loops versus someone working at a big financial institution. Now, even in those big financial institutions, there could be big gaps in performance. Even within your own team, there can be big gaps in performance. I've seen guys who've been working for 15 years do worse than guys who've been working less than 1 year. So even if I say you need to know Python coding, there can be a lot of variation in skill among those who consider themselves good at it. A similar situation happens with deep learning. I can say you need to know how neural networks work. But there's a big difference between someone who can code them from scratch and has experience using them versus someone who just watched some online animations for a few hours. If you had to bet on who knows neural networks better, who would you pick? So to really answer this question, we have to turn to the course itself. If I say you need to know Python coding and you claim that you do, but you don't understand some Python code in this course, then simply put, your Python coding skills are not yet up to par. So you have to improve your Python coding skills by asking questions on the Q&A and taking the appropriate steps to cover your gaps. Quite often, I get people who are just too confident in their own abilities, when unfortunately the reality is there is a huge discrepancy between what they think they know and what they actually know. What's funny is these people sometimes say, this course requires PhD math. I assure you, there is absolutely no math in any of my courses that requires a PhD or that only a PhD can understand. My courses contain only undergraduate math at most. Sometimes people even claim to have a PhD and then claim that it's still too hard, which is funny because that essentially invalidates your entire PhD. The entire point of a PhD is to turn you into an independent researcher. And so if you're supposed to be at the level of doing independent research, but you can't understand some undergraduate math, well, that's not very good. Essentially, what it boils down to is people are really trying to say, everything I don't understand is not important. Everything I do understand is important, and therefore, everything you say that I don't understand, I don't need to know. You can see why this thinking is dangerous. If you truly believe that everything you do not know is not important, then you'll never learn anything new. Now this brings us to our third question. Is this course fast-paced or slow-paced? And I think you can see where I'm going with this. This is yet another example of ambiguity. Fast-paced to whom? Whether it's fast-paced or not depends on which person is taking the course. So if someone is well prepared, then things will be just right. If someone already knows most of these topics, then it will probably be too slow. If someone chose not to prepare for the course, or they have an inadequate understanding of the prerequisites, then it's going to be too fast. So if I expected you to know something and you didn't, then you have to look it up, which is going to make the course feel like it's going too fast. So here is the real test. If I say something depends on calculus and probability, and you claim to know calculus and probability, but you don't understand the thing that depends on calculus and probability, you have to ask yourself honestly, do I really understand calculus and probability? Or did the instructor invent his own kind of calculus and probability that I don't yet understand? Well, of course, that's not very likely. It's most likely that you thought you understood calculus and probability, but you really don't. Now on to our initial question. What kind of course is this? Is it academic? Is it for professionals? Is it practical? So to understand this, you have to understand where machine learning is usually taught and how it is usually taught. Firstly, machine learning is usually taught in upper year computer science and engineering programs in university and college. So these are students who already took calculus 1 to 3, linear algebra, differential equations, probability and statistics, discrete math, programming, and possibly more, all in their first 2 or 3 years of college. So by the time they get to 3rd and 4th year, they know all this stuff and they're ready to apply it. So a typical academic course might cover a whole library of machine learning algorithms. So you might learn k-nearest neighbor, logistic regression, k-means clustering, PCA, and so on, all in the same course. Typically, you'd cover one algorithm per lecture, which is about 2 hours. Overall, you might have something like 12 or maybe 20 of those lectures in a term. And by cover, I mean mostly via math, geometry, and derivations. These courses don't typically have you at your computer doing programming work. If you do end up doing programming, it's usually part of a lab assignment, which is actually just a very small part of the course, compared to the rest. So it's mostly theoretical, dealing with equations, solving equations, reasoning about equations. Those equations typically involve probabilities and information theory. So you have 2 hours to go through the theory for one algorithm, and then if there's coding involved, which there usually isn't, you do it on your own time. The lectures themselves do not involve any coding. But there's an even bigger problem with these academic courses, and what is that? What happens is that the grades turn out to be very low. Out of 100%, the average might be around 25% or up to 40%. Now you might think, wow, so everyone fails. And of course that's not the case since everyone gets shifted based on the average. So what is the real problem here? A lot of people ask me, well, why don't you cover every machine learning algorithm in one big massive course and just call it machine learning? Well, the answer is that if you try to do too much, you only end up understanding 25% of the material, which I think is clearly demonstrated here. And as they say, the proof is in the pudding. If you look at these courses where students are trying to digest 10 different algorithms at the same time, what is the result? The result is they don't understand any of them. If you try to understand too many things, you end up understanding nothing. I take the perspective that if you're going to take a course, you should aim to understand 100% of the material. Each course is broken up into appropriate levels, based on how difficult they are and by topic. So for example, you can typically take Calculus 1, which focuses on differential calculus, Calculus 2, which focuses on integral calculus, and Calculus 3, which focuses on multivariable calculus. You would never learn all of these in just one huge course called math, because that's just too much stuff to understand all at once. I want you to understand 100% of the material. Even 50% or 75% is not good enough in my opinion. If you only understand 75% of the material, and the next course depends on the 25% that you didn't understand, well then you're not going to make it to the next level. Now let's look at the opposite end of the spectrum, what most people might consider to be a practical course. I don't consider these to be practical courses, and I'll explain why later. But I'll use the word practical here in quotes, since that's what some of the more beginner students will refer to them as. So how does a practical course typically proceed? Well, first, you are never really taught how the algorithms work, other than at a very high level. You might learn how they work by way of analogies and metaphors. So for example, suppose you're learning about gradient descent. Well, the instructor might relate this to a ball rolling down a hill. Now some beginner students, they might conclude that, I understand a ball rolling down a hill, therefore I understand gradient descent. But they neglect to understand how to take derivatives, they neglect to understand how to choose a good learning rate, and most importantly, they neglect how to implement gradient descent in code. So it's totally wrong to assume that just because you can visualize a ball rolling down a hill, that you understand gradient descent. Why? Well, the problem is, everybody can imagine a ball rolling down a hill. Your grandparents who can't even turn on a computer can understand a ball rolling down a hill. So don't equate understanding an analogy to understanding the real topic. So what's the next thing these practical courses do? The next thing they usually teach you is how to plug into an API, or in other words, make use of a library someone else wrote. This is also not ideal. Typically, this involves just 2 or 3 lines of code. You have to wonder, if machine learning just boils down to 2 or 3 lines of code, why is it such a big deal these days? Why did it take decades for people to realize its usefulness? And of course the answer is that there's much more to machine learning than just these 2 or 3 lines of code. When you use a deep learning library like Keras, you're not doing deep learning. You are using a deep learning interface. You're simply programming. It's more accurate to say, I can program with deep learning libraries, rather than saying I actually know deep learning. But some of you might say, well, that's all I really want to do. All I need is an API, and for the API to give me an answer. I don't care about how it works. But then here is where you run into trouble. Recall that in addition to all data is the same, we know that all machine learning interfaces are the same. So the question becomes, which API do you choose if they're all the same? How can you make an informed choice about which one to use? Well, the reality is, if you don't know how these things work, then you can't answer this question. This is why some of these so-called practical courses can cover 20 algorithms in the same course. It's because they never actually talk about how the algorithms work. Since the API is the same every time, it's very easy to just do the same thing 20 times and then not bother with the details. So this gives people a lot of confidence that they were able to do the same thing 20 times. But it's dangerous thinking because you don't realize you really only learned one thing, you just repeated it 20 times. So how about when it comes to the professional world? Sometimes people tend to believe that in your profession, you'll be leaning more toward the practical end of the spectrum, where you don't really need to know how a machine learning model works, you just have to know its API. But what it really comes down to is what your job actually is. If you're a regular everyday programmer and you just want to see how a machine learning model might perform on your data, then you're going to use a pre-built library most likely. That's just the 2 or 3 lines of code I referenced earlier. However, that does not mean you don't still have to conform to best practices, make sure you're not mixing your test set with your train set, make sure you're doing proper validation, and so on. And when it comes to tuning your model, then you'll have to be able to dig down into the details and see which hyperparameters are possible to change and which are likely to have the most impact. So only knowing how to use an API is only going to get you past the first stage. You can plug in your data and at least your code has the right syntax and doesn't crash. But of course, your code not crashing doesn't necessarily mean it's right. Back on the other end of the spectrum, you have programmers and scientists whose sole job it is to do machine learning. These guys are machine learning experts. They know the math inside and out and have a full computer science education. And so, to even be able to communicate your ideas effectively, You have to be comfortable with the theory and not just how to plug into an API with 2 lines of code. These scientists are building custom models, really digging down into the math to not only use, but invent new things. And to be able to invent new things, you really need to know the math very well. And so if you're on a team like this, you can't just know how to write 2 lines of code. Your skill set has to be far beyond that. So your theoretical background has to be very solid if you want to be able to communicate effectively with other scientists. Now, a lot of people say, well, I don't ever want to be a scientist, so I don't really care how these algorithms work. Unfortunately, that's a very bad attitude to have in the workplace. Suppose, for example, I am running a business. Now, an employee of mine, he wants to show off and say he's learning about machine learning. He says, oh, I'm taking this machine learning course online, therefore I will become a machine learning master. But his approach to machine learning is to learn as little as possible. He says he doesn't care about the math, he only wants the practical stuff. He only wants to know the bare minimum. He tells me he doesn't care how it works, he's just going to plug into some API, because that's what his buddy told him he could do. As a business owner, I really don't want this guy working for me. I run a business that sells something, and the life of the company itself, and the livelihoods of the employees, all depend on our products being the best they can possibly be. So if someone comes to me and says, I don't care about being the best, I just care about doing the bare minimum, my response is, I don't want that guy on my team. In fact, he should be fired. So be careful if this is your approach to machine learning. No business owner wants to hear that your approach to the business is to do the bare minimum and to put off some math because you think it's too hard. That's a scary prospect for a business owner. Now, if we go back to our original question, maybe you've realized we haven't answered it yet. What kind of course is this? Well, you can think of it as a marriage between these approaches. We want to cover all the math and derivations because that's very important if you want to be able to communicate effectively with other scientists, to be able to debug your code effectively, and to be able to invent new approaches. This is also what we mean by machine learning. We mean really knowing machine learning and not just programming with an API. So the theoretical background is very important. At the same time, we're not going to introduce 20 different algorithms in the same course, because unlike a typical academic course where you can pass just by understanding 25% of the material, in this course it's structured in a way that if you have any missing gaps, it's going to be impossible for you to move on to the next stage. But academic courses don't contain much coding, if at all. So in this course, every algorithm we learn about will be implemented in code. My motto is, if you can't implement it, then you don't understand it. You can pretend to understand it, and when you talk about it, you might sound like you understand it, but implementation is the true test. It's like a math exam rather than writing an essay. When you write an essay, you might be able to fool the teacher into thinking you understand something, but in a math exam, either your answers are right or your answers are wrong. In this context, either your code works or it doesn't. It's very clear cut. When it comes to practicality, we cover that too. We demonstrate our algorithms both on real-world data like text and images, and we demonstrate our algorithms on two-dimensional data sets so that you can visualize what an algorithm is doing. Both of these are important. Text and images are quite possibly the most practical data there is. Some billion-dollar companies exist and thrive because of those capabilities. 2D data sets are critical as well because as humans, that's the only thing we can see. But at the same time, we don't try to pull the wool over your eyes and pretend like you need 20 different data sets to practice on. Instead, we learn something much more valuable, how to use an algorithm on an infinite number of data sets, because we are able to abstract the idea that all data is the same. Remember that all the computer sees is a list of numbers. It doesn't know that those numbers represent height measurements or an image pixel. And of course, by experiencing both ends of the spectrum, both the theory and the implementation, and then finally plugging data into your model, that's going to make you very well-rounded professionally. To conclude this lecture, I want to pose a final question. How does all this knowledge help you? Why does understanding the approach of this course make you better at machine learning in general? Well, my hope is that this gives you a very high-level, bird's-eye view of the landscape. You can see the different approaches of people from different backgrounds. Academic people typically don't see what other non-academic people are doing, and those people who hate math typically don't see what people who love math are doing. So with this bird's eye view, you can see everybody. If you're learning machine learning, it helps you understand who am I competing with when I apply for a job, and what kinds of jobs are out there, and what would be adequate preparation. If you're hiring for a machine learning team, it helps you understand the different backgrounds of individuals you have to compare to one another to understand their strengths and weaknesses and what they bring to the table. Hey everyone, and welcome back to this class. This is a short lecture I like to give in each of my courses on how to succeed in this course. This is very important to talk about because you're learning a difficult technical subject. It's easy to get stuck, or even worse, give up because you're just not getting things. Maybe there are too many gaps in your knowledge, so you can't connect the dots. Maybe some assumption you've made is incorrect. And keep in mind, there's a lot of material in this course. It can be overwhelming if you're new to this field of study and you're not familiar with the conventions and the typical patterns we use. Now, if you've already seen this lecture in the past, you are more than welcome to skip it if you remember what's in it and you're already using these guidelines. The first guideline is this. Remember that I want you to succeed. In fact, that's why I'm giving you these guidelines in the first place. So if at any point when you're watching these lectures and you become confused, just ask on the Q&A, also known as the discussion forum. Typically, I respond within hours, sometimes even within minutes if I happen to be on the site and I see a notification. I answer any and all questions, so even if you think it's stupid, just ask anyway. One example I get from time to time is, where do I get the code for this course? And of course my answer is typically, well, it's in the lecture called Where to Get the Code for This Course. At the end of the day, no one cares if your question was trivial or silly. If it's something keeping you from progressing in the course, I want to answer it. Now, very rarely I get people saying, well, I was so confused that I couldn't even think of the right question to ask. And this is where you have to take some responsibility for your own learning. You have to ask yourself, what did the instructor assume I know that I didn't actually know? Maybe I can look into those things, and that will help me formulate a question. Maybe there's some background knowledge I'm missing. A lot of people like to have exercises to practice when they're taking a course. The act of thinking of the right question to ask is itself an exercise. It might not be the type of exercise you thought you'd be doing, but in many ways, this is more profound. This is an exercise that requires you to think and to change how you think. And ultimately, that is the best value you can get out of a course. Speaking of background knowledge, this is one of the most important guidelines in this lecture. You may have noticed that in the course description, I've listed some prerequisites, or in other words, things you should know before starting this course. Now you might wonder, why do I ask you to know these things? Why don't I just teach them in the course? And while we do review some topics in this course, it's not the focus. There's such a wide variety of students in this course. Students from almost every country in the world. Students of all ages. Students of all backgrounds. What does this mean? That means what's review for one person is going to be totally new for another. Some people are going to tell me they don't know calculus. Some people are going to be very far behind with their Python programming skills. But if we start teaching Python programming skills, other people are going to say, hey, why are we doing Python? Isn't the topic of this course deep learning? And I tend to agree that we should stay on topic. So how can we reconcile this? Well, it doesn't make sense for me to give you an entire computer science education in this one course, because a lot of that would be irrelevant for a lot of people. The only logical thing to do is for all of us to meet at a common meeting point. How is that point defined? Well, it's defined by the course prerequisites. In fact, they are so important that in certain instances, I've listed the course prerequisites twice, just in case you missed it the first time, and I'm also reminding you now for good measure. Now, one pitfall is that people sometimes assume they know things that they don't really know. So if you took calculus 20 years ago and you got a C, and you skipped class, and the times that you did show up for class you were sleeping, well, probably you don't know that much calculus. But remember, I want you to succeed. I want you to be able to learn this material. I can point you to resources where you can pick up this missing background knowledge, but the key is you have to ask. In some cases, there are certain places where I'm not allowed to post certain links, so we have to be mindful of the rules of the platform we're using. Now, occasionally people ask me, well, why don't you just teach a course for pure beginners? Why don't you teach these courses in such a way that they don't require lots of math and lots of prerequisites? Well, I don't want to turn this into an easy beginners type of course, because for one, that's not what I'm interested in personally. And number two, don't forget that this is state-of-the-art stuff. State-of-the-art generally isn't easy, and if it were easy, that would mean everyone is doing it. And if 1,000 other people can do the same thing as you, well, what's a potential employer going to think? What are your chances of getting that job when all 1,000 of you have the exact same skills? So we don't want skills that are easy to get. We want skills that are hard to get. Skills that put you at the top of your game. Skills that not many people have. If I'm hiring someone, I want the guy who stands out, not the guy who says the same thing as everyone else. Finally, the final guideline for how to succeed in this course. I mentioned earlier that there's a lot of material, so much that it can be hard to keep track of. In addition to taking your own notes and doing all the derivations yourself, how can you be absolutely sure you're understanding this material? I would in fact consider this even more important than the derivations. Not everyone is going to be a pro at math, so it's understandable if you want to skip a few steps. Sometimes it's possible to compartmentalize some concepts or delegate learning them for some other time, but still understanding the high-level picture and how it fits in with everything else. What you cannot skip is the implementation. Implementing these algorithms in code is the real test for whether or not you understand the material. And this is not about reinventing the wheel or that you shouldn't roll your own whatever because someone else out there can do it better than you. That is a software engineering principle, not a principle of learning. In production, you don't want to write your own hash map or your own string class. And yet, what do we usually do as an exercise in a typical intro to computer science class? Well, we do precisely that. We implement hash maps and we implement strings. And why do we do this? Because we want to have a better understanding of how these things work. If you make an assumption that's incorrect, well, your code is probably just not going to work. Merely using a hash map and using a string only gives you a very superficial understanding. That's beginner stuff. That's stuff everyone knows. That's not stuff that's going to help you stand out from the competition. And it's true that you'll never use your own homemade hash map or your own homemade string in any code you write, unless of course you are a professional that focuses on that sort of thing. They'll probably be inefficient and they'll probably have bugs, but that's okay because you're not doing it to make it perfect. You're doing it to learn. You'll notice that the general pattern that this course follows is that we always discuss theory, and then we implement that theory in code. So we're always going from theory to code, implementing everything that we learned. If you can, try to implement something before watching the coding lecture. In the appendix, I have a lecture called How to Code by Yourself that goes much more in depth into this topic, along with multiple strategies for how to approach implementation exercises. So to summarize, these are the guidelines I think are going to help you succeed in this course. Number 1, make generous use of the Q&A, even when you can't think of the right question to ask. Number 2, make sure you meet the prerequisites to this course. If you're not sure what they are, or you're not sure how, see guideline number 1. Number 3, try your best to implement everything we learn. This is the true test for whether or not you understand something. Remember that it's perfectly normal to get stuck once in a while. I get stuck all the time when I'm learning. That doesn't mean I'm not smart, nor does it mean the book or video I'm learning from is bad. It means that there's a disconnect between what the author believed I knew and what I actually know. And as a learner, I do my best to close that gap. A good skill to have is learning how to compartmentalize concepts. So here are the things I understand, here are the things I don't understand, but here are the things I understand about the things I don't understand, and these are the holes. So you know what you're missing and you know where they fit, and you can work to fill in those gaps over time. One thing I've been doing quite a bit recently is adding review lectures to my courses. These aren't meant to teach you everything from scratch, since that's going to take you a long time, but they are meant to help you recall certain things you may have forgotten. So if you have an idea for a review lecture that you'd like to see added to this course, please feel free to make a suggestion using the Q&A. Hey everyone, and welcome back to this class. This lecture is about how to write code independently when you're doing machine learning. You always hear me say that the first thing you should try to do when you learn an algorithm is to go and write it up in code by yourself before looking at someone else's code. For some students who are new to machine learning, it's not quite clear how to do that. So this lecture is going to explain the thought process you should go through in hopes that it encourages more people to try to code by themselves. I like to encapsulate this in the phrase, when it's time to code, you must code. So remember this whenever you see some code that demonstrates the concepts we learned in this course. Even if you don't fully understand what's going on, coding and copying examples from others helps you build muscle memory. Sometimes people act like they are going to learn tennis by reading a book about tennis. This is of course obviously not possible. You need to learn some things about tennis which are pure fact and reside in your brain as conscious facts. But then you have to go out and practice those concepts on the tennis court. Once you've exhausted and mastered everything you know so far, then you can learn new techniques. So you have this continuous cycle of learning new techniques and then practicing them. Why is this? Because learning the technique as pure fact doesn't mean you truly understand it. Practicing the technique helps you think about the technique from a different perspective. Practicing again and again leads to new understanding, to learning in the subconscious, which is muscle memory. You must go through this cycle. But some students naively think they are going to read an entire book about tennis and then be a tennis master the first time they try playing. This is very common, especially when all you really need to do is sit there and watch a video and no one can force you to type. A lot of people don't even think to try. So just remember this whenever you see code. When it's time to code, you must code. First, we are going to talk a little bit about why you want to code by yourself. A lot of the time, what an algorithm does or how it works isn't quite clear the first time you learn about it. Every individual will have their own unique background, so they might be familiar with the patterns and know exactly what to do, while some individuals might have questions that no one else has. Sometimes you gloss over details because you assume you know what's going on, when really there are important things you're not considering. So this is how trying to code by yourself can help you. Coding by yourself forces you to think about each and every detail. It forces you to think line by line. You have to be familiar with the data types and the shapes of all your variables, and they all have to fit together properly, kind of like Lego blocks. As an example, you know that in order to do element-wise matrix addition, both matrices have to have the exact same shape. So if you find that they are not the same shape, then one of your previous assumptions was incorrect. So you should go back and correct it. Lego blocks have to follow a specific set of rules in order to fit together properly. If you make incorrect assumptions about how Lego blocks fit together and you try to join them, it's not going to work. Without trying to build things by yourself, you will never discover these details. Let's now talk about how to code by yourself. Consider the supervised machine learning scenario. We know that we're going to have some inputs and some targets, and we want to try to make predictions from the inputs that are very close to the targets. We typically call the inputs X and the targets Y. Sometimes we call the targets T, but for the purpose of this lecture, we'll call the targets Y. Now this next point is a key point. It doesn't actually matter what X is and what Y is. It doesn't matter if you're looking at an e-commerce data set and the columns of X might be time on site, time of day, how many pages the user looked at, and so on. You could just as well be looking at a data set of X-ray images where each column is the pixel intensity of an image. This is the key point. We say all data is the same. When we do linear regression, we don't have different kinds of linear regression for e-commerce and X-ray images. Linear regression is the same algorithm no matter what your data set is. So we say all data is the same. Theoretically, I could give you a data set of X's and Y's, and you could train a classification algorithm on it without me even telling you what the X's and Y's mean. You should get very comfortable with this idea. Sometimes people say, well, this isn't practical because I want to do concrete examples. But that's because they're not thinking intelligently. In fact, this is the most practical thing we can do because it means everything we learn, we can apply it to any data set that exists. It means that I can train a model on an e-commerce data set, but I can also train a model on an online advertising data set without learning anything new at all. It's truly the greatest form of lazy programming. Learn something once and apply it to every industry. One great consequence of all data is the same is that there is an unlimited amount of practice opportunity for you. You can download data sets from Kaggle, from Google, from Wikipedia, from Amazon, or from anywhere else and try the algorithms you learned. What this means is, let's say you have a data set you care about more than something we do in class. See, in class we have to use data sets that everybody can understand. For example, text and images. Everybody should know what text and images are. Text and images are just fundamental data types on the web. You probably don't even think about the fact that text and images are data because it's so trivial. In any case, we work with text and images a lot because everybody understands them. But let's say you're a biologist and you know about DNA. You find DNA and genomics really interesting. So you want to use the algorithms we learn on that. Well, that's great and you should totally do it. Remember, all data is the same, so all you need to do is convert your data into the appropriate X's and Y's to plug into our machine learning algorithms. The downside is we most likely won't talk about DNA in class unless it's a very simple example, because most computer scientists are not biologists too. So they don't know what DNA is. They don't understand the specifics. So an example wouldn't make much sense to them. This is opposed to text and images, which makes sense to everybody. Same goes with any other specialized field like finance, computer networking, cosmology, and so on. So now we can start off from the right place to talk about supervised learning. We have our X's and we have our Y's. What do we do with them? In supervised learning, we know that there are two main things we want to do. We want to do training and we want to do prediction. In scikit-learn, all the models have the same API. It doesn't matter if you're doing logistic regression or decision trees or random forest. All supervised models in scikit-learn have the same two functions, fit and predict. Fitting a model is just a synonym for training a model. If you don't believe me, you can go look at the scikit documentation yourself. When you're learning about supervised machine learning, what you're really learning is what goes inside these two functions. What are the parameters and how are those parameters learned? That's really what all supervised machine learning is, filling in these two functions. Taking this perspective is going to give your code structure and it's going to make things much easier to visualize in your head. Let's now do a simple example to solidify this idea. In this example, I'm going to give you an algorithm and you will implement it in code. There are two key points I want to make before I give you the algorithm. First, I'm not going to give you much intuition about how it works. Second, I'm not going to derive the theory behind why it works. The reason I want to mention these two key points is that you should realize you don't need these two pieces of information in order to translate pseudocode into code. A lot of time, these three concepts, intuition, theory, and implementation, work to reinforce each other. The reason I'm focusing on implementation right now is because it's the one people most often miss or think they don't need at all, when really it's an extremely important part of the learning process. Okay, so the pseudocode is as follows. In my predict function, as you already know, I'm going to take in some input data x. My predictions will be y hat equals x times w. You might already recognize this as linear regression. However, forget what you know about linear regression and pretend that this is just some formula I gave you. What I can tell you is that we are creating some kind of regression model. It should be clear from this equation that the parameters of the model are contained in this vector of weights w. I would probably also tell you that w is a vector that's the same size as the number of feature vectors in X. Of course, this must be true in order for the matrix multiply to be valid. This acts as kind of a sanity check so you can make sure everything is making sense. In my fit function, I want to perform this loop some number of times. Since we know from the previous slide that the parameters of the model are contained in w, then it should be clear that inside the fit function, what we want to do is update w. Not surprisingly, that's what's happening here, another good sanity check. Now, because you're already familiar with linear regression, you probably already recognize this as gradient descent. Again, I want you to pretend that you don't know that. But what do you know? You know that iterative algorithms are common in machine learning, and that gradient descent is among the most common. You could probably infer that this is some form of gradient descent, but you don't need to know what it is in order to write it in code. What else do we know? You know what a for loop is, and you know how to write one in Python. You know that X is an n by d matrix containing the input data, and that Y is an n-size vector containing the targets. You know that Y hat is an n-size vector containing the predictions. You know that W is a d-size vector containing the model parameters. And you know how to add, subtract, and multiply these objects. So we can write this algorithm without even knowing how it works. Of course, a lot about how it works can just be inferred from this formula. Here is what you don't know. You don't know t, the number of times the loop is supposed to run. You don't know eta, the learning rate. This is completely fine. You can't let this lack of knowledge stop you in your tracks. The truth of the matter is, there are going to be situations where you're not told the exact numbers to plug in. In many cases, the answer is going to be, it depends on the problem. The important thing is, you have to get used to the idea of trial and error, and you have to make educated guesses based on what you already know. So what can you do? Well, you know that the learning rate is supposed to be a small number. How small? It depends on the problem. Typically, it's a number less than 1, like 0.1. If that doesn't work, you might try lowering it. Typically, we lower it by factors of 10. So for example, the next learning rate we would try is 10 to the minus 2, 10 to the minus 3, and so on. Typically, in machine learning, whether you're looking at a supervised or unsupervised algorithm, there is an associated cost or objective function that you're trying to minimize. Let's suppose I tell you it's squared error, which is typically what we would use for regression. Well, now you have a way to choose the number of iterations of the loop and the learning rate. How do we do this? So inside your fit function, you would plot the cost as a function of iteration. I always recommend doing this, no matter what algorithm you're looking at. In general, you always want the cost to converge. The pattern you typically see is that there is a steep drop at the beginning, and it slowly flattens out as the number of iterations increases. To choose the number of iterations, you want to stop when the curve is sufficiently flat. You might recognize this as a diminishing return scenario. The returns diminish because at the beginning, we reduce the cost by a lot in just a few iterations. At the end, we can do a lot of iterations, but we reduce the cost by almost nothing. An alternative is, you could use a separate validation set and stop when the validation cost increases, but that is not the focus of this lecture. Unlike the training cost, the validation cost is not guaranteed to decrease at every round, because that is not what we are minimizing with respect to. You can also use this same plot to help improve your learning rate. If the cost explodes or becomes not a number, your learning rate is probably too high. If your cost converges too slowly, you can try increasing your learning rate. So what does your final code look like? Well, we know we want to create a class with at least the predict and fit functions. You don't have to use a class, but I find that it encapsulates the code nicely and provides useful structure. Notice that once you have the algorithm in math, there isn't much work to convert it into NumPy code. You know how to do matrix multiplication, you know how to add, you know how to subtract. These are basic arithmetic operations that I'm sure you know already. If you don't know how to do these in NumPy, then I have a completely free NumPy course on the NumPy stack that you can take. Here is the second part of the code where we actually create an instance of the class and then use it. I've also included the squared error cost function just for completion's sake. What's cool about this template is that it doesn't really change from one algorithm to the next. The structure is basically always going to be this way, at least for supervised learning and unsupervised learning. So as we discussed before, it doesn't matter what algorithm you're implementing, whether it be linear regression, logistic regression, a neural network, and so on. They always have the predict function and the fit function. And learning what goes inside these functions is equivalent to learning the algorithm. So in fact, one way to begin coding is to start with just this boilerplate code and then fill in the blanks. This is what is known in software engineering as test-driven development, or TDD. In test-driven development, we start by writing tests, because number one, your code should always have tests, and number two, writing the tests first forces you to think about how you expect your API to work, and it allows you to make sensible design decisions without being distracted by implementation details. So you see how this applies to every machine learning algorithm, not just linear regression. In a lot of my older coding videos, I unfortunately decided to just write the code straight through. This helps some people, but is not ideal for others. In addition, the coding videos will appear without warning. Generally, the lectures appear in the same pattern. First we do theory, and then we do the corresponding code. It pretty much always works this way. So after the theory lecture, you can be pretty sure we are going to implement that theory in code soon, unless it's so simple that it can be an exercise. Now, to avoid treating everyone like they're in kindergarten, I don't have videos telling you that it's time to code. You're all proactive and independent adults, so when you learn some theory, you already know that it's time to try to put that into code by yourself. Sometimes you might get stuck and have no idea what to write in code or what the data set is. In that case, it's fine to watch the next coding lecture, but don't watch it all the way through. Watch just enough so that you know what the general idea is and what we're trying to accomplish, and then try to finish the rest yourself. Now let's say you've watched just enough so that you know what we're trying to do. You know the theory, but you still can't complete the code. At this point, you may want to revisit the lecture theory to make sure you really understood each part. Failing that, you may want to try and get clarification on the discussion board. Failing that, you may want to look at external resources as well. Sometimes you might be missing some important computer science background that I've assumed everyone already knows. That's perfectly fine because everyone has a different background. It's highly encouraged to do your own research, and this is also perfectly normal. It's not a bad thing, it's a good thing. Ask any university student if this is what they do, and they'll tell you that they do it all the time. This builds a level of mental toughness and initiative taking that's important if you want to learn this stuff. There's a lot to learn, and I myself am still learning new things every day. So let's say you've rewatched the theory lecture. You've looked at some external resources on the theory, and you still don't understand how you would put it into code. Well, at this point, there are some great exercises you can do. Watch the coding lecture or look at the full code on GitHub. Go through it and make sure you understand each line. The next step is, without looking at the code again, try to implement it yourself. This by itself is a great learning tool. Many of the algorithms I've learned, I didn't understand them the first time. I learned them by looking at someone else's implementation and dissecting it. I looked at each part and I asked myself, which parts did I get right and which parts did I get wrong? This helps you understand the mistakes you were making previously. The cool thing about implementation is it works backwards too. We go from theory to code, but thinking in the reverse direction, the code actually helps us understand the theory better also. I always say that if you can't implement the code, then you don't understand the theory. So if you can learn the theory 50% of the way, try to implement the code, look at an existing implementation, and then finally get it working, then you can be guaranteed that you now know more than just 50% of the theory. The act of coding helped you understand more of the theory than if you had just learned the theory by itself. So implementation helps you understand the theory, but it also helps you understand the intuition as well. Intuition is a tricky thing. In fact, I would go so far as to say it's a trap. In many or maybe even most cases, intuition is built on experience. That means deriving the theory from first principles, or in other words, deriving the theory from facts you already know to be true, and from implementation. Students often want to hear intuition from people with lots of experience, but the problem is that this intuition is built on hindsight. Intuition is often both the first thing and the last thing you want to focus on. You want to have a little bit of intuition at the beginning, so you have some general idea of what you want to accomplish. Then after you learn the theory and implementation, you can reflect on the details and summarize them at a high level. This is real intuition built on hindsight and experience. The big mistake beginners make is that they read some intuition written by someone else who actually has experience when they themselves do not. From an outsider's perspective, it's hard to tell the difference. Why is that? Well, if the beginner can regurgitate the same high-level ideas as the expert, then it would sound like they are also an expert when in fact they are not. There are unfortunately too many courses out there that do this. They want you to feel good that you learned something, and they want to avoid you having to do anything too difficult. And because you can repeat the same high-level intuitions, it actually sounds like you're an expert. So this is why I call it a trap. Knowing intuition not only makes you feel like you know something, it also makes you really confident about this fact. And then because your ego wants to maintain this confidence, you'll start making crazy statements like the theory and implementation are not important because you already understand the intuition. But as you know, this is completely backwards. Let's summarize this lecture, since that was a lot of information to take in. Remember, this lecture is all about how and why you should code by yourself. First, we talked about why. This is because it ensures you are thinking about the details and filling in the blanks using your own pattern recognition skills. It ensures you don't just assume you know what's going on, but that you actually know what's going on. There's a big difference, especially if you're the type of person that likes to assume you know everything. Next, we talked about how. We talked about how all data is the same, and it doesn't really matter what domain or industry your data is from, the same algorithms all apply. Next, we looked at the interfaces to the algorithms, which are also conveniently all the same. So we have a kind of mix and match type of scenario, where we can input any kind of data into any kind of model. For example, you can use linear regression with financial data, or you can use a neural network on ecological data. All data is the same and all models have the same interface. Next, we talked about a strategy for how to actually apply this. You've probably already seen that we always alternate between theory and code. First, we discuss the theory, and then we implement that in code. Sometimes you might have to go back and revisit the theory, or sometimes you might have to look things up on the internet. That's perfectly normal. This is pretty much the day in the life of a university student. We're trying to build the same level of mental toughness and initiative taking in this course. So the strategy is, stop after you learn the theory and try to code yourself. Sometimes you need a little more detail, so you might want to watch a little bit of the coding lectures to see what's going on, and then try to implement the rest yourself. If you can't get it by yourself, then maybe try watching the whole thing, or looking at the expected result, and then trying to implement it from memory. This by itself is a great learning tool because it allows you to ask yourself, what did I get right and what did I get wrong, so you can understand the mistakes you were making. Finally, it's important to understand the difference between intuition, theory, and implementation, and how they reinforce each other. It's important to not fall into the trap of only understanding intuition written by someone else and then assuming that this equates to actually understanding everything. In many cases, it's not about waiting for someone to tell you some nice phrases that trick you into thinking you understand the intuition, but rather you should seek intuition by working through the theory and the implementation. And lastly, don't forget, when it's time to code, you must code. In this lecture, I'm going to talk about Jupyter Notebook. Occasionally, I get this strange question from students asking why I don't do things in Jupyter Notebook. Let me explain why I think this is strange. Firstly, it's my position that it's completely unnecessary and actually doesn't change anything to use Jupyter Notebook or not. Let me repeat that. Using Jupyter Notebook is exactly the same as not using Jupyter Notebook. There's no difference other than the fact that it looks different. In other words, the screen is a different color. Obviously, such a difference is trivial. In this lecture, I'm going to demonstrate how that's the case. One major reason I dislike Jupyter Notebook is because it causes too many students to be unaware of how Python really works. If you're only comfortable inside Notebook, and when you see Python code in a text file or anywhere else, and you get scared or intimidated, that's not good. That Python code that's in the text file is exactly the same as what would be in the notebook. There's really nothing scary about it. Programmers working at real jobs eventually need to write code that's going to be deployed and run automatically. In other words, your final code is going to sit in a Python file that runs by itself without Jupyter Notebook. So if you're going to have any hope of using these skills in a real job, you had better be comfortable with writing Python code outside of Jupyter Notebook. You would also better be aware that there's actually zero difference between writing code in a Jupyter Notebook and writing code in IPython or the console. Here's one example I like of how you might use Python in the quote-unquote real world. Let's say you write a script that emails your boss to tell him you're going to be late for work. And let's say you don't actually want to send this email manually, but you want it to get sent automatically every Friday morning so that your boss doesn't yell at you for coming into work late after you had partied too hard Thursday night. Well, that's very simple. All I have to do is, on my server, create what's called a cron tab. In it, I just enter the code for when I want this command to run, and then to the right of that, I specify the command that I want to run. That's just Python space and then the script name. As you can see, it's simply how you would run this Python script from the command line. And now, every Friday at 9:45 a.m., this script is going to send the same email to your boss to tell him you'll be late. Well, let's not get off track here. The point of this is, you really don't want to be using Jupyter Notebook for something like this. I think one perceived advantage of Jupyter Notebook is that you can see the results of intermediate calculations. However, this is merely a perceived advantage and not a real advantage, because you can do the exact same thing even when you're not inside Notebook. Firstly, as I'm sure you've seen by now, IPython also prints out the results after you enter a command. IPython is called a REPL, which stands for Read Eval Print Loop, and that's generally what they all do, no matter what language you're in. So whether that's Python, Ruby, PHP, or any other language. The keyword here is print. Why is that? Well, one of my golden rules for writing and debugging code is when in doubt, print it out. I can't tell you how many times I've gotten a question on the Q&A when it could have been easily answered by inserting a print statement into the existing code. Anyway, what's the point of this long discussion about printing things out? Well, it's that if you think Jupyter Notebook is the only program that helps you do this, you need to expand your horizons a little bit. You should, in fact, always be doing this. If you're not using an abundant amount of print statements while coding, you are not doing it right. Remember, programming is not philosophy. You're not supposed to be running a program in your head. That's like trying to do long division in your head when you have a calculator in your hand. So just by printing things out, you can be more efficient. Stop trying to guess what a program will do, and just let the program itself tell you what it's doing. The key takeaway here is, you should always be printing things out. The fact that Jupyter Notebook shows you the result of each block of code is not simply a happy surprise. But another important lesson here is that if you want to use Jupyter Notebook, there's absolutely nothing stopping you from doing so. In other words, using Jupyter Notebook is 100% compatible with everything we are already doing. In fact, if you recall, your goal in these courses is not to run my code, but to write your own code. And of course, since it's your code, you can write it however you want, including Jupyter Notebook. In the rest of this lecture, I'm going to prove to you that you can take any script from our course repository, which we know runs in the console, because that's how I always demonstrate it, and show you that this exact same code runs in Jupyter Notebook. Let's begin. Okay, so let's say I'm in the folder NumPy class, and I'm interested in the code inside classification example.py. As you can see, what I have right now is this code inside a text editor. Now, if you're not aware of what a text editor is, it's just a program that shows you the contents of a text file and lets you edit those contents. It's the ideal program for writing code. Now, occasionally, if you're writing in a language like Java or Swift, you might want to use an IDE, but even then, it's totally optional. These days, I prefer to write Java in a plain text editor like Sublime Text as well. In any case, normally, one does not need to use an IDE for writing Python code. Now, about Jupyter Notebook. Well, let's start up a Jupyter Notebook. So I'm going to go Jupyter Notebook. All right, so now I've got Jupyter Notebook running, so I'm going to start a new notebook. Also, notice that we started the notebook in the same directory as the relevant Python file. So that's something you want to keep in mind for the future. Now at this point, what I'm going to do is, I'm going to prove that everything in this Python file works exactly the same in the notebook as it does in the console. So let's start with the imports. Actually, let's grab this one too. All right, paste that in. Run it. So everything's fine so far. Now let's load in the data. Okay. We've loaded in the data. Now I'm not sure what its type is, so I can check it by using the type function. So let me try that. Cool, so I get sklearn.utils.bunch. So that's the type of the variable data. Now previously, you recall that we did this example in IPython, but as you can see, the result is the same in Jupyter Notebook. Alternatively, if you wanted to run this Python file in the console, So you wanted to type, let's say, you wanted to type in Python classification example.py, then you could just add some print statements if you wanted to show those same lines while this file was running. Now, I'm not going to go through such elaborate detail for the rest of this example since you've already seen it, so let's just get through the rest line by line. Let's say I want to check out the keys in the data variable. Okay, looks good so far. Let's check the shape of the data attribute. Okay, looks good so far. Let's check the targets. Okay, still what we expect. The target names. Looks good. Target shape. This should be 569, yep. And let's check out the feature names. Okay, that's the same as well. Now let's do our train test split. Okay. Now let's instantiate and fit our model. All right. Now let's check the train score and the test score. All right. Now let's see how we can make new predictions. So you see how if you assign to a variable, it doesn't print the result. But if you have an expression, then it does print the result. So those are some predictions, and this was an alternative way to calculate the accuracy of the predictions. So we get the same answer as before. And we also have this other example where we can use a neural network to do the same thing. So let's build the model, train it, and print the train score. And let's print the test score as well. All right, so everything works the exact same way as it does without using Notebook. Now, another thing I could have done was I could have just taken this whole thing and copied it and pasted it in and run it. So that's another possible thing you can do. But the downside of that is you don't get to see the intermediate outputs. But again, that's what print statements are for. All right, so what can we conclude from this exercise? Well, we can see that this code runs exactly the same inside Jupyter Notebook as it does everywhere else. That's why I always say Python code is Python code no matter where it is. If you want to use Jupyter Notebook to run the course code, there's absolutely nothing stopping you from doing so. Hey everyone, and welcome back to this class. This is a short lecture to explain that you are free to use whichever version of Python you want in this course. Just one side note before we begin. While I've updated all the code in the repository to work with Python 3, you still need to git pull to ensure that you have the latest version. I know that some people fork the repo on GitHub, but I strongly recommend not doing this as you won't get the latest updates as easily. If you do have a fork, consider just getting rid of it, or at least make sure you pull the latest changes often. A lot of people consider Python 3 to be the new version of Python, and therefore it's the one everyone should use, but that is a very limited perspective. First, Python 3 is actually not that new. In fact, at the time this lecture was made, 2018, Python 3 is almost 10 years old. In fact, Python 2.6 was released at the same time as Python 3. So Python 2.6 and Python 3.0 are actually the same age. Some people think that because 3 is a bigger number than 2, that means we should use 3. Of course, you can see why this is a somewhat superficial way of reasoning. The bigger issue is this. If you join a large company using Python today, and they built their technology stack many years ago, they are probably using Python 2. And if you're in a large company, it's not easy to just recreate your entire codebase. That might take months or years of effort. No reasonable company that makes millions of dollars per day is going to halt their operations just so they can switch Python versions. Consider your choices if you are a manager or a business owner. You have a list of things to get done. Your clients want these things done, and they're going to pay you lots of money to get them done. So if you have a choice between your engineers working on something that will make money versus working on something where you not only get paid no money, but that actually costs you money because you have to pay the engineers to do the work, which are you going to choose? Most people I know would choose the option to continue making money. And so for better or worse, a lot of folks are still using Python 2. That means if you join such a company, you'll be forced to learn Python 2 syntax. There will simply be no way around you having to learn Python 2. At the same time, the differences between Python 2 and Python 3 are usually trivial. For example, instead of print with a space after it, print works like a function, so it has to have parentheses. Another example is that we use range instead of xrange, which both return generators rather than lists. In Python 2, range returns a list, which can be inefficient, so we try not to use that when we're using Python 2. In Python 2, division using a slash can do different things depending on what its arguments are. So for example, if both the numerator and denominator are integers, then the result will be an integer. But if at least one argument is a float, then the result will be a float. This is the same way division works in C-style languages, so it's pretty typical behavior. In Python 3, a slash always does float division, so even if your numerator and denominator are both integers, the result will be a float. If you want to do integer division, you have to use a double slash. Other examples are given on this page on my website, lazyprogrammer.me/Python 2 to 3 tips. Of course, aside from these things, there are a lot more less frequent discrepancies you may come across. So if you come across something that doesn't work, you're encouraged to use the Q&A since that is the best place for you to get help. However, you most likely won't need help since the changes are trivial 99% of the time. So there's no need to give up if you see that the code you're working with is for Python 2 and not Python 3. Most likely, just a few lines need to be changed as per the error messages you get, and you'll be up and running in no time. Hey everyone, and welcome back to this class. In this lecture, I'm going to answer a question that I get pretty much multiple times per day, and that is, what order should I take your courses in? This is a great question, and it's something that even I have to think about sometimes. What is the best way to learn all this stuff? So I think that what you'll find is, this ordering makes a lot of sense in that we're always building on skills we learned before. So it's just like learning calculus. First you learn calculus 1, then you learn calculus 2, which is kind of the opposite of calculus 1. Then you learn calculus 3, which expands on the ideas from both calculus 1 and 2. And then from there you can go on to even more advanced topics like probability. So this is a process based on skill building. Now it's important to keep in mind that this lecture is not just about my courses and how to navigate them, although that is the question I'm answering, since that's a question I get multiple times per day. But this is also a lecture on how different machine learning topics are related and what depends on what else. So even if you end up not taking any of my courses, it doesn't change the fact that these topics are still related to each other in these ways. So in some sense, this lecture isn't really about my courses at all. It's a general lecture about how different types of machine learning models are related, and in what order you might want to learn them from a skill-building perspective. Now I want to show you this stuff in a visual way. I've actually set up a web page where you can go to and look at the chart I made for yourself. So what I want you to do is go to this website, deeplearningcourses.com. Now I want you to click on the catalog link. And from there, you want to click on the click here link. Okay, so this brings us to the course order webpage. So at the top, you have sort of this linear chart, right? It's just one course after the other after the other. But this is not really what I want to look at in this lecture. This linear chart gives you a basic overview, but it's not ideal. The reason is the relationships between courses are way more complex than this. Sometimes one course gives you the skills you need for 2 other courses. Sometimes there will be a course that's so complex that it depends on multiple different courses. So this is the perfect opportunity to use a graph. So if you scroll up at the top, you can use this link to just jump down to the bottom, and we have this graph where you can see the dependencies between each course. So what I'm going to do is I'm going to go through each link in this graph and explain to you why it exists and why it's important. So let's look at the SQL course first, since that has no links. So it might show up in the middle, so you can just drag it out to the side. That's the coolest thing about this graph, because you can just pick stuff up and drag it around. It's very interactive. So SQL has no links. This isn't a prerequisite to any other course, nor is any other course a prerequisite to it. It is standalone. You can take it at any time. Next, you'll notice that there are courses that have no links going into them. So for example, the NumPy course. This is because none of my other courses are a prerequisite to this course. This course was just designed to give you a basic understanding of the syntax and tools we use in data science and machine learning. The goal is actually to not do any machine learning in this course. Believe me, it was actually quite difficult to accomplish that because it's so easy to use something in machine learning as an example. It was very hard to avoid talking about it. You'll also notice that there are some courses with no outgoing edges. You can think of these as the most advanced courses. They are at the top of the ladder. So for example, this one right here. Of course, that could change in the future as I create more courses, in which case I will update this lecture. So let's start with what's coming out of NumPy. You'll see that there are 2 links. One goes to linear regression, and one goes to Bayesian machine learning A/B testing. And by the way, you can zoom into this graph, so that's what I'm going to do right now. Okay, so here's linear regression, here's Bayesian machine learning. So while NumPy goes to both of these courses, I'd actually strongly recommend linear regression as the next step. Bayesian machine learning doesn't depend on any other courses per se, but it's still more advanced. It requires a more advanced understanding of probability and of real-world engineering problems like optimizing the click-through rate of a link on your website. So linear regression would be my #1 recommendation for your foray into machine learning. Now after linear regression, we have logistic regression. So why do we go from linear regression to logistic regression? Well, the basic idea is both of these are linear models. In other words, the model is of the form y equals mx plus b, which is a line. The difference is that linear regression does regression, while logistic regression does classification. We want to learn classification because that's one of the central tasks of a neural network, which is what comes after. Now you might notice that linear regression also has 2 outgoing links. So there's one to logistic regression and one to reinforcement learning. This is because my reinforcement learning class makes use of linear regression, so naturally, if you don't understand linear regression, you won't understand that part. But again, this is a much weaker link than going from linear regression to logistic regression. This is because reinforcement learning is actually conceptually more difficult. It doesn't depend on the content of any other courses directly, other than what we've shown, but the ideas behind it are more advanced. You really want to have some experience with both supervised and unsupervised learning before jumping into reinforcement learning. It helps to build the proper perspective on the subject. We will get back to reinforcement learning later, but for now, let's go along the deep learning path. So on the deep learning path, we last discussed logistic regression. This is also known as a neuron. This is very important because in order to build a neural network, we must first know how to build a neuron. A neural network is just a bunch of neurons stuck together. So this leads us to Deep Learning in Python Part 1, which is the bright green logo. This course teaches you how neural networks work and basic fundamental operations like backpropagation. Once you know the basics of deep learning, you can move on to Deep Learning Part 2, or Modern Deep Learning in Python. This is the same image, but in a darker color to signify that it's a continuation of the previous course. As the title suggests, this course is all about modern developments in deep learning. So we go over ways we've improved basic backpropagation, like momentum and adaptive learning rate techniques like RMSprop and ATOM. We talk about modern regularization techniques like dropout and batch normalization. And most importantly, we look at modern deep learning libraries like Theano and TensorFlow. We also take a look at Keras, PyTorch, MXNet, and CNTK. You'll see that once you know the fundamentals, things don't change that much from one library to the next. It's all the same concept. Now, learning about these modern libraries sets the stage for the next level, which is applying deep learning to certain special data formats. The two fundamental types of data are text and images. These are special because they have unique structural properties, and we can make use of our knowledge of those properties in order to build better neural networks. For example, we know that text is made up of sentences, and sentences are sequences of words, so sequential modeling is important. We know that images are two-dimensional objects, but importantly, each pixel is very likely to be the same as nearby pixels. For example, if you pick a random pixel on an image of a red car, if that pixel is red, then most likely the pixels around it are also going to be red. There is also no question about the practical applicability of text and images. The internet is made up of text, so by doing machine learning on text, you're learning techniques that essentially allow you to write models of the entire world's knowledge. Images are also everywhere. Snapchat, Instagram, Facebook, self-driving cars, home security systems. Knowing how to deal with images is super important, and billion-dollar companies exist because they are good at it. So that brings us to the next course in the deep learning series, Convolutional Neural Networks, or Deep Learning in Python Part 3. This is all about how to incorporate convolution into neural networks and what convolution is in the first place, and how that helps us make use of the structure of images. Let's scroll up a bit. So after convolutional neural networks, we take a detour into unsupervised deep learning. Unsupervised deep learning isn't very popular with beginners, but it should be. If you look at the experts of deep learning like Yann LeCun, Yoshua Bengio, and Geoffrey Hinton, they all talk about how important unsupervised deep learning is. This course introduces us to several new ideas. First, the idea of latent variables or latent causes. These are factors that you don't directly observe in your data, but that you can learn about by studying the structure of your data. Second, modern techniques for data visualization like t-SNE. This will be very important since, as I discussed earlier, along with images, text is a really important data format. In order to visualize text in later courses, we will be making use of t-SNE, so it's good to know what it is and why it's useful. Third, unsupervised pre-training. Unsupervised pre-training is the foundation of modern ideas like transfer learning, and we make use of it both in NLP and with convolutional neural networks. Fourth, the vanishing gradient problem. We demonstrate the vanishing gradient problem directly so you understand where it comes from. Vanishing gradients are especially important in the context of recurrent neural networks. And it just so happens that recurrent neural networks is the next course in the deep learning series, Deep Learning in Python Part 5. So recall that our two fundamentally interesting data types are text and images. We've looked at images, and in this course we start to look at text. Why might that be? Well, recurrent neural networks specialize in modeling sequences, and text is just a sequence of words, so it's the best type of data to use to demonstrate the principles of RNNs. Once we've studied RNNs, we can go even deeper into how deep learning can be used on text. That's the next course, Natural Language Processing with Deep Learning in Python, or Deep Learning in Python Part 6. In this course, we look at a very important concept called word embeddings. These allow us to turn words, which are categorical variables, into vectors, which are numbers that a neural network can read. This is why it's very important to have studied unsupervised learning before this, because finding word embeddings is actually an unsupervised task. Word embeddings also allow us to make use of pre-training, which was discussed in Deep Learning in Python Part 4. In this course, we also look at a very advanced model for doing sentiment analysis, called a recursive neural network or a tree neural network. This is an example of a dynamic neural network because it changes its structure based on what input you give it. Most deep learning libraries are not equipped to handle dynamic neural networks, and I demonstrate what happens if you try to build one the naive way. You basically end up building a separate neural network for each of your training samples, and it's going to eat up all your RAM and make your computer slow down to a crawl. So you get a first-hand perspective of why working with dynamic neural networks is not easy. But luckily, we are able to make use of our knowledge of recurrent neural networks, and remember that's the prerequisite to this course, in order to convert a tree into a sequence, which an RNN is capable of handling. So that's why RNNs is a prerequisite to this course. Now you'll notice that this course, Deep NLP, has no outgoing edges. This is because it's the most advanced course that I have on this path for now. I certainly plan on expanding in this direction in the future. However, this is not the last deep learning course in the series. After this, we have deep reinforcement learning, which is Deep Learning in Python Part 7. With that said, I think now is a good time to go back and start exploring the reinforcement learning path. So you'll notice that I have Bayesian machine learning feeding into reinforcement learning. On the surface, these two courses might seem unrelated, but there is a very important concept you'll learn that applies to both, called the explore-exploit dilemma. In Bayesian machine learning, you learn this idea in the context of trying to optimize a click-through rate or a conversion rate. Or in other words, the number of times people buy things from your website versus the number of times people visited your website. Very practical concept, I think, if you do anything related to e-commerce. Now, in reinforcement learning, we look at the explore-exploit dilemma again, but in the context of playing games. Reinforcement learning is like a third branch of machine learning, whereas the other two are supervised and unsupervised learning. The main difference is that supervised and unsupervised learning look at static data. In reinforcement learning, the idea is more like you have a robot living in the real world. It can take the experiences it had today and, based on them, behave more intelligently tomorrow. So the learning paradigm in reinforcement learning is sequential. This is opposed to supervised and unsupervised learning, where your dataset usually resides in some file on your hard drive. So in reinforcement learning part 1, we get all the basics, as you might expect. This is a prerequisite to deep reinforcement learning, since deep reinforcement learning applies those concepts to more difficult games. But you'll notice that this is not the only prerequisite to deep reinforcement learning. As the title suggests, this is also dependent on knowledge of deep learning, in particular, convolutional neural networks. But as we know, in order to build a CNN, we have to know how to build a regular neural network, which means we have to know what a neural network is and why it's useful, and so on. So in deep reinforcement learning, these two paths converge. You combine your knowledge of both reinforcement learning and deep learning in this course. Now the reason it depends on CNNs and not, say, RNNs, which is over here, is because we'll be learning to play visual games. So for example, we can learn how to play a video game like Pong or Breakout, which are classic Atari games from the old days. And so those are images because they're basically screenshots from the screen. In the future, we might end up applying RNNs, in which case RNNs will become a prerequisite to that course. So that's the end of the reinforcement learning path for now. I'm very excited to bring you more updates in this area in the future. Let's now jump back to logistic regression, where we can see another outgoing edge to supervised machine learning. So why is this edge here? Well, you may recall that linear regression and logistic regression are both linear models that do regression and classification respectively. These are both supervised learning tasks. And so it makes sense that now that you know one model for regression and one model for classification, it's time to dig deeper into supervised learning. The thing with linear regression and logistic regression is that they aren't really different models, they're both just a line. Because they do different tasks, the techniques and interpretations are slightly different though. And there are, of course, different models that are not linear models that can do these tasks, and that's what this course is all about. In this course, we look at classic supervised machine learning techniques like k-nearest neighbor, decision trees, the perceptron, and the Bayes classifier. Much like how logistic regression was the basic building block of the neural network, classic models like decision trees are the basic building block of ensemble methods. So that's why this course is a prerequisite to ensemble machine learning. Again, we use the same logo with a different color to signify that these two courses are very closely related. In ensemble machine learning, we learn how to combine multiple decision trees in different ways in order to make some very powerful classifiers. What's really remarkable about these methods is that they are very easy to plug and play on data. So if you're looking for a plug and play solution without having to learn a lot of theory, then deep learning is most likely not for you, but ensemble methods are a great fit. Deep learning is very dependent on hyperparameters, and if you choose incorrectly, your model will perform very poorly. Sometimes it requires immense computing power to find good hyperparameters. This is an active area of research. It is not yet solved. This is why you can implement what you see in a deep learning paper, but suppose the author left out some seemingly insignificant detail, so you end up having to make an assumption, and then your results end up totally different. So deep learning is fragile. But luckily, ensemble methods are not. We focus on two very famous ensemble methods, the random forest and AdaBoost. So that's everything on the supervised machine learning track for now. Next, we see an edge going from supervised machine learning to unsupervised machine learning, in particular cluster analysis. The reason we study supervised learning before unsupervised learning is because unsupervised learning is a little more abstract. It takes more effort on the student's part to realize why it's practical and what it can be used for. Cluster analysis shows us how to model data that does not come with targets. As you might guess, we do this in the form of clustering. The idea behind clustering is very simple. We want to know how many naturally occurring groups of data there are, and what are the relationships between the data in these clusters. So for example, if you were clustering books, you might find a book about Steve Jobs and a book about Elon Musk in the same cluster. This cluster is probably about tech companies in Silicon Valley. But you don't need a label in your data to tell you that. You can discover it yourself by looking at how the data naturally groups together. Now, as I mentioned earlier, I think once you learn about both supervised and unsupervised learning, you'll be ready to jump into reinforcement learning. I haven't made cluster analysis a prerequisite to reinforcement learning since none of the material depends on this course, but it's good to know about these techniques so that you have a more mature and experienced view on machine learning. What is sort of a sequel to cluster analysis is hidden Markov models. The reason might not be clear at first, so let me give you two reasons. Number one, they are both unsupervised machine learning models, just that HMMs is harder, so it's natural to learn about clustering first. Clustering is also about static data, whereas HMMs are about sequences, so it's similar to the process we did in deep learning. We looked at static data like images, then sequential data like text. Reason number two, in cluster analysis, we learn about a technique called the Gaussian mixture model, which we make use of in the HMM course. One key point is they both learn by using the expectation maximization algorithm. So it's good to first see the EM algorithm on a simple model, and then when you see EM again on a more complicated model like the HMM, it won't be as intimidating. One key concept you learn in HMMs is the Markov assumption.
That just means the current state depends only on the previous state, but not any states before it. This is a simplifying assumption that usually makes the math easier to work with. You will also notice that we encounter the Markov assumption in reinforcement learning. However, it's not too hard to learn it from scratch. And so for that reason, I do not consider HMMs to be a prerequisite to reinforcement learning. The Markov assumption is really the only thing they have in common. There is also a slight connection between cluster analysis and unsupervised deep learning. So I'm not going to draw the link right now, but I sometimes consider this to be unsupervised machine learning part 1 and this to be unsupervised machine learning part 2. We also see that HMMs feeds into the RNN course, which is about deep learning. So why might that be? This is of course because both these models are models that can learn about sequences. In particular, in both these courses we model text as sequences. But whereas the HMM makes use of the Markov assumption, the RNN does not, and hence the RNN is a more powerful model. And so this just goes along with the main theme that we always go from simple basic models to more complex models. This is also something you should do in your work as well. If you start with a simple model, you often find that it is faster and more robust. Complex models sometimes break down, but they are also more difficult to implement and might not even be fast enough. Of course, that's just a generalization, so you always want to analyze engineering trade-offs individually for every problem you have. Now, there is one last link in this part of the graph here that I want to explain, and that's the first NLP course. You can see that it depends on supervised machine learning and feeds into deep NLP. The main purpose of this basic NLP course is to apply basic machine learning models to text. So that's why supervised machine learning comes before it. It's because that this course was all about basic machine learning models. The important skill for NLP was not the implementation of those models, but rather a bigger picture perspective on how machine learning is used. What is the interface between the data and the model? What does the model do? What is its input and output? How is the output interpreted? And so we take those principles and we apply them to text. In this way, we can see that text can be treated in such a way that you don't have to think about it any differently than any other data. This reinforces the principle that all data is the same. The machine learning model doesn't care what your data is. All it sees is a table of numbers. It doesn't care if it's text or images or radar signals from space. The model just does what it was designed to do on the numbers that you give it. So this course gives you a high-level systems perspective on working with machine learning models in text. This easy NLP course also feeds into deep NLP, which is of course not so easy because it depends on a lot of background in deep learning. One of the main questions I get in the NLP course is, how do I improve the results of these basic models? And a lot of the time the answer to that is, well, you have to use a more complex model, but of course that necessitates learning how that complex model works. And deep NLP is an example of that because we learn a state-of-the-art method for sentiment analysis, whereas in easy NLP, we used only a linear model. So it's important to understand that while yes, it's possible to improve the predictive ability on simple basic models, as you can see, it's not always an easy path to get there. So you have to make sure you're prepared. Case in point, just look at all the time spent just to get to deep NLP. It's not an easy task. Let's now scroll over to GANs and variational autoencoders. Just like how deep reinforcement learning is not related to deep NLP, this isn't really related to deep reinforcement learning either. This is Deep Learning Part 8 by order of creation only. It is the spiritual sequel to unsupervised deep learning, which was Deep Learning in Python Part 4. Okay, so just to reiterate, this is Part 6, Part 7, and Part 8 by order only, but they are not related to each other conceptually. Although it's always nice to know all these things because more context makes future things easier to learn. So the reason this is linked to this is because GANs and variational autoencoders are also unsupervised deep learning models. But whereas unsupervised deep learning was all about how to improve supervised learning, GANs and variational autoencoders don't have any direct benefit to supervised learning at all. although we do make use of supervised learning within the course. In this course, the focus is on generating images. We've seen that GANs can create photorealistic images based on a dual neural network system. That's pretty cool because before GANs, we didn't have any kind of machine learning model that could generate real-looking images. Nowadays, GANs are able to generate high-resolution, high-quality images of people that you can't even tell are not real people. It certainly makes the idea of the matrix seem very possible. Alright, so I hope you found this lecture helpful. We saw that these courses are related to each other in some pretty complicated ways. Learning machine learning is not exactly linear. Sometimes you have to take one course before you can take the next. Sometimes one course might just be related to another course by some key concept, but maybe in one context it's a lot easier to understand. So remember to keep in mind that these arrows do not all indicate strong prerequisites, but rather there's just a relationship between the two courses. I hope that this lecture explained any nuances between what is a prerequisite and what is not, and I hope I did a good job of answering which order should you take these courses in and why. Hey everyone, and welcome back to this class. So one question I get very often is, when are you going to release your next course? And when are you going to do your next promotion? The best way to keep track of when I'm releasing courses is to sign up for my newsletter at lazyprogrammer.me. I'm always going to announce things here first, so if you want to be first, this is the place to be. I also give out a ton of free material on my newsletter, so you want to make sure you're signed up for it. I also release coupons on social media, so you want to make sure you're following me on my Twitter. My username is @LazyScientist. Another place I post things a lot is on my Facebook page, so if you want to follow me on there as well, that's facebook.com/lazyprogrammer.me. I'm on various other sites as well, including Pinterest, YouTube, Vimeo, and so on. So if you're already on those sites, just look for me and you'll probably find it. So aside from coupons and announcements, a very good reason for you to be following me on all these channels is so that you can get your hands on exclusive free material. A lot of people make requests, like for example, they want to learn about time series, or they want to use neural networks for regression, or they want to see a TensorFlow implementation of some neural network architecture. If you're waiting for me to add lectures on these topics, it might take a very long time, depending on when I can get around to it. But it's a lot easier for me to write some code and write up a short tutorial. If I do that, there's a good chance I'll release it as free exclusive material, but these are time sensitive, which means I'll offer it for a short period of time and then it will be taken away forever. It's a thank you for being signed up, so if you're not signed up, you won't know and you won't be able to access the material. Finally, a lot of people are interested in coupons. If you want coupons, just email me at info@lazyprogrammer.me and I'll send them to you for whatever course you ask. You don't need to wait for a specific promotion or anything. Just email me personally and I will send you coupons.